Okay, so welcome back to the lecture. Today we'll be looking at vision transformer for the first time in the series, and we'll be trying to understand the intuition behind vision transformer, how vision transformer is different from transformers that are used for text-based data. So once we have that intuition, we'll be coding one from scratch. So when I say coding, we'll write every aspect. Wherever PyTorch libraries are applicable, we will use those. And training also will be done from scratch. So at the end of today's lecture, if you are coding along with me, you will have a vision transformer built and trained by your own on one particular data set. So at the end of the lecture, that is where we are expecting to be. So first, let's look at who proposed vision transformer. So vision transformer paper idea was proposed in this paper, which was originally out in 2020, but this paper on archive or the conference ICLR was appearing on 2021. This paper 3 months ago had 65,000 citations. Now it has 76K. So I assume that few years down the line, this will become one of the, not the most highly cited paper in AI, but one of the highly cited papers in the entire history of AI. And this paper came out 3 years after Attention is All You Need paper, which was also from Google. So one thing you should note is that I remember in 2022, many people were commenting on LinkedIn and all that when OpenAI came out with ChatGPT. Google is not doing much in AI, but Google they have been doing a lot of things in AI. It's just that many of those things were not in the consumer space necessarily. Many of those things were in the research domain. And they had amazing papers, which are seminal papers. And they still do have many other papers coming out of different AI teams within Google. So this paper was titled An Image is Worth 16 by 16 Words. So what they did was they proposed the usage of transformer architecture for image classification. And in their architecture, they had very minimal changes or modifications compared to the original transformer architecture that was proposed in Attention is All You Need paper. This is a dense but well-written paper. I am premiering a 3.5-hour lecture video on reading this paper and properly dissecting the vision transformer paper. If you are interested, you can check out our YouTube. But today we are not going to be going through this paper, but what we are going to look at is how does vision transformer differ from transformers for text, which we have been exploring as part of the series. And we just want to see where the key differences are and where are the similarities. So a transformer for text works like this. You have a text input in the form of a prompt. Then this input is tokenized. Basically, sentences are divided into tokens. You can imagine when I say token, you can imagine words, but tokens can be words, subwords, etc. And then each token is converted into a vector. If it is a GPT-2 small architecture, it was of 768 dimensions. So each vector was in a 768 dimensional space. So every single sentence which we input into GPT will be converted into n number of tokens, and those tokens, each of them will be converted into 768 vectors. And to each token, we add one thing called position embedding, which we have discussed in the past. But the main difference between a text-based transformer and vision transformer comes in the part where attention is calculated. So in text-based transformer, we use something called as masked self-attention. So we have discussed the reason why this masking is done. So if we have a sentence like the cat sat on the mat, and if we are dividing a sentence into words, this consists of 1, 2, 3, 4, 5, 6. 6 tokens are there, which means there are 6 queries and 6 keys. And we construct this thing called as attention weights matrix, which we have discussed in detail in the past. But you will have 6 queries here along the row. The cat sat on the mat. And you will have 6 keys. The cat sat on the mat. And what we have discussed in the last lecture was about masked self-attention and multi-head self-attention, where in masking, we prevent current queries from paying attention to future keys. So if cat is a query that we are looking at currently, cat can only pay attention to itself and to the. Cat cannot pay attention to sat on the mat. The reason why we did this was because of the task that we were trying to accomplish. The task that GPT was trying to accomplish was next word prediction. So in next word prediction, your current query should not pay attention to keys that are yet to come, keys that are in the future. So to accomplish this, what we did was we constructed an upper triangular mask, something that looked like this, where all these elements in this attention weights matrix were 0. So this was 0, 0, 0, 0, 0. This was 0, 0, 0, 0, then 3 zeros. Only the last query, which is the query corresponding to mat, will pay attention to all the keys because there is no more query after mat. So the query mat will have 6 keys to attend to. So this is what we discussed in the last lecture. But you should also know that GPT is not the only modern architecture that utilizes transformers. There is one more architecture which is super famous called BERT. In BERT architecture, what they were trying to do was not next sentence prediction. Can you please erase the writing on the board, because on Zoom setting I cannot disable this. So my only option, if you guys draw, will be to kick out whoever is drawing. I'm sorry about that. So in BERT model, what we will have to do is, or what they were trying to do was, you will have a sentence which looks like this: the mask sat on the mask. So in BERT, which also utilized transformer architecture, they were not trying to do next word prediction, but rather they were inputting sentences, and there they were trying to predict what the value of these mask tokens were. Now, in this case, can you guys comment in the chat whether we need masked attention or not? Should we have like causal attention, which was there in the last lecture where GPT for next word prediction was used? In this case, will we use an attention with mask or will we use an attention without mask? Most of you are saying without mask. And that is correct, because in this case, you are not trying to predict the next word, but rather you are trying to take the entire context of the sentence, which means if you mask the future query, if you mask the attention between current query and future key, you won't have the full context available. And this is one reason why, if you open this paper, attention is all you need figure. Just look at this figure. Let me actually copy paste this. Now focus on this part. So this paper is not GPT paper, okay? This paper is purely attention is all you need paper. This has got nothing to do with GPT. But look at this left-hand side section and look at this right-hand side section. And tell me, where do you find the mass self-attention? Is it on the left or right? It's here in the right. There is masked multi-head attention over here. On the left, there is no masking, which means which one is GPT, which one is BERT? Is left one or is it right one? So essentially, this transformer architecture has both encoder and decoder. But in BERT model, they were just having this left-hand side part. So masked multi-head attention was not there. The input embedding was passed through attention, was passed through transformer blocks. Each transformer block had one multi-head attention without masking and one feed-forward multi-layer perceptron. And that was repeated a number of times. On the other hand, right-hand side, which is GPT-like model, it's a generative model. BERT can be converted into a generative model, but BERT is primarily not used as a generative model. It's used as a model that can learn language. So it can create very nice embeddings corresponding to a language because it has so much power to learn language. But since next word prediction is not the task in unmasked attention, BERT is not a really good next word prediction model, or rather, BERT is not a really good generative model. But GPT is that. Now, yeah, so somebody is asking, why is there skip connection? Yes, it is exactly like RESTnet. So RESTnet has skip connection to prevent gradient vanishing when you are performing back propagation. Exactly the reason why you have these skip connection, this. We have discussed this in detail. Now, let me ask you a question. Let's say I want to build an image, a transformer for images, okay? And what I am going to do is, I will somehow convert image into tokens. You somehow converted a sentence into tokens. So you had cat sat on the mat, which you converted into some vectors. Each vector had 768 dimension, okay? We will do the same thing. We will take an image and we will somehow tokenize it, which we will discuss soon. Now, if my task is image classification, what kind of architecture would you rather pick? Left-hand side architecture or right-hand side architecture? Okay, many of you are saying left-hand side. Why? Why is it left-hand side type architecture? Why not right side? Want a representation, want to understand the representation of the image. The main thing is you are not trying to predict the next, image token or anything like that. You are just trying to classify. The current task that we are discussing is image classification. We are not trying to generate anything. We are not discussing about generative image models. We are trying to understand what is there in an image and try to classify into one label. Hey, this image is a cat. This is a dog. Which means if we perform masking, that is a problem because then the full context is not available. That is the reason why in vision transformer, you will not use a masked multi-head attention. You will use an unmasked multi-head attention. And that is one of the first differences that you should note. In text-based model that we have discussed so far, in BERT, they use unmasked self-attention, but in GPT, they use masked self-attention. In vision transformer, also they have transformer, but they used unmasked attention. So self-attention without masking. So this is the number one difference between image transformers for image and transformers for text that you should understand. Especially I'm talking about GPT versus vision transformer. Now there is one more difference, one more major difference, which we have to take a look at. We discussed that for next word prediction, we are using context vectors, correct? Our singular goal was to convert tokens into context vectors. Tokens had very limited information. Context vectors had much better information. And how was the context vector constructed? Context vector was constructed using this softmax of query.key transpose divided by square root of dimensionality of key multiplied by value. This was context vector matrix. And the reason why we constructed context vector was because context vectors were rich in information compared to the original input tokens, which we denoted by X. Now, tell me, if you had attention weights corresponding to, let's say, 6 queries and 6 keys, and I want to now generate the 7th token, how many context vectors do I have here, by the way? If I have a matrix like this, how many context vectors do I get as an output of this? I get 6 context vectors, correct? Because I have 6 queries, and corresponding to each query, I will have 1 context vector. Now, if I'm trying to predict the 7th token, which out of these 6 context vectors do I use? I use the last context vector. To predict the 6th context vector, we could use the 5th one, or to predict the nth token, we can use the context vector from n minus 1th query. So the information about the next token and the entire context is embedded in the last context vector. So essentially, the context vector corresponding to mat is used to predict the next token. And let's say the next token is the cat sat on the mat and something else. So then the context vector corresponding to mat will help you predict and. This is what is done in text-based transformer. In vision-based transformer, what they did was something different. They tried this. They tried an idea where an image was converted into multiple n number of tokens. Each token was a vector. Let's say 1, 2, 3, etc. up to n. They tried using one of these tokens itself to predict what the image was, but the accuracy of that was not very good. And because of that, in Vision Transformer, they introduced one additional token called as classification token. We can call this as classification token. So apart from the n tokens, which correspond to the image, you had one more token called as the classification token. And this classification token's context vector, so this classification token will be converted into corresponding context vector. And this context vector was used for saying whether this image is that of a cat or dog or whatever. So this is the second biggest difference that you have to notice between transformer for text and transformer for vision. So transformer for text, GPT-like model for generating the next token uses the context vector of last token for next token prediction. So this is the second difference. On the other hand, transformer in vision transformer uses context vector of 0th token. So this class token was introduced just before all the other tokens. So we can call this as class token or 0th token. It was also there in BERT. Yes. So it was the class token here was actually inspired from BERT. So BERT, what they did was if you had two sentences, you had, let's say, sentence number A and sentence number B. They started with a CLS token, and then you had T1 or TA, TB, TA1, TA2, etc. up to TAN. So you had n number of tokens corresponding to sentence A. In between, there were masked tokens. Some of them were masked. Then there was a separator token separating between two sentences, sentence A and sentence B. Then you had another set of tokens, TB1, etc. up to TBM. There are m number of tokens. And then again, a separator token. So this classification token was introduced in BERT. And this same token, this was the inspiration for classification token in Vision Transformer. So essentially, what Vision Transformer relied on was whatever is the context vector corresponding to this classification token, that context vector holds the entire information about what is there in the image. Just like how the last token holds the entire information about your sentence in a GPT, just like that, the 0th token, so now instead of last token, it's 0th token. 0th token holds the information about the entire image in Vision Transformer. So two differences. In Vision Transformer, you use classification token rather than the last token. Second thing is, unlike GPT, you don't have masking. Your self-attention is unmasked self-attention. Please note these two differences. Now, essentially, if you look at the task, okay, if you look at the GPT task, it is also sort of like a classification task. Why do I say that? Why is it a classification task in GPT-2? How could you imagine next token generation as a classification task? Basically, there is a dictionary or vocabulary in which there are a certain fixed number of tokens. So let's say there are 50K tokens, roughly 50K tokens in GPT-3. Now the goal is to say whether the input sentence, so if you have an input sentence, you will try to predict the next token, right? This next token will be one of the tokens from your dictionary consisting of 50K words. So essentially what you are trying to do is you are trying to classify whether this sentence considering all the tokens is classified into one of these 50K tokens or not. You can think of it that way, although it's not the right way to think. You can essentially think in GPT, you are trying to classify the last context vector corresponding to the last token to say which among the 50K words or which among the 50K tokens in your dictionary could be the next word. So it can be matched depending on the probability distribution. So you will get a softmax probability distribution, something that looks like this. If you add up all these probabilities, it will add up to 1. One token will have highest probability. So with highest likelihood, that token will be picked as the next token. Same thing happens in vision transformer. In vision transformer, depending on the data set that you are using to train, there are data sets with 1K image labels like ImageNet 1K. So ImageNet was a very famous data set consisting of labeled images. So there was an ImageNet small version, which was of 1K labels, and ImageNet larger version with 21K labels. So essentially, what vision transformer does is, vision transformer tries to classify the classification token into one of the 21K labels. Conversely, text transformer like GPT tries to classify. Classification is the wrong word. I'm fully aware of it, but I'm saying this just so that you can imagine the similarity between vision transformer and GPT. What GPT does, you can imagine it to be, you are classifying the final context vector of the last token into one of these 50 tokens. Because the next word, so if you have vision models are not generative. No, I did not mean that. Vision transformer model is not generative. Vision transformer model originally proposed in Google's paper is not a generative model. It's a model that learns about images and it can primarily perform classification. But there are other vision models which are generative, right? Just like how BERT is. BERT is not primarily a generative text model. It is a model that can really nicely understand language. Now, with these similarities and differences in our mind, let's look at the image, which is directly taken from the vision transformer paper. So this figure, what you see is directly from the vision transformer paper, which very nicely explains what happens to an image when you input it. So first, you have an image, and this image is converted into non-overlapping patches of same dimension. So this image, in this example, you can see it's divided into 9 patches, which means there are 9 tokens which result from each patch. So 1, 2, etc. up to 9. Now, we perform a linear projection, which is simply a matrix multiplication. We will see how this matrix multiplication works to convert each of these 9 patches into corresponding token embedding. So this is token embedding for patch number 1. This is token embedding for patch number 2, number 3, 4, and so on. In addition to these 9 tokens, you have one more token here. And what is this token? What is this token? It's the classification token, or CLS, or class token. Now, in text-based transformer or in GPT model, just the initial token embeddings were not enough. We were adding one more thing. We were doing token embedding plus one more thing to get the input embedding. What was that? We were adding position embedding. We were adding the position information. Same thing is done here. A vector is added to the converted tokenized patches corresponding to the position embedding vector. Now, these vectors were learnable vectors. So the value inside these vectors were not fixed. But the way it works is, if each patch, let's say your patch is of size 16 by 16, this might be converted to a 768 dimensional vector. To this vector, your position embedding will be added, which is also of 768 dimension, but the values inside this vector will be a learnable parameter. In vision transformer paper, if you read the paper, they have tried both. They have tried fixed position embedding, meaning you can easily construct a position embedding considering the fact that 0th token is at the top left corner, last token is at the bottom right corner. So you can nicely try to construct some vector which captures the idea that which captures the relative distance or relative position between these patches. You can definitely do that. So they have tried both. In the paper, they tried fixed position embedding without learnable parameters and learnable position embedding. And both were giving similar accuracy. And in the main paper, they used learnable position embedding. Now, once you have learnable position embedding, you also need to add learnable position embedding, by the way, to your classification token. So this is the class token, CLS token or CLASS token. To that, you add 0th position learnable embedding. So now you have position embedding plus tokenized patches, plus you also have the same thing for CLS token. Now you have the entire tokens available. Then what you do is you pass these tokens to your transformer encoder. Class comes from the label of labeled images. No, this class has nothing to do with label at the moment. At the moment, it is just an extra token that is added, whose value during the backpropagation will be changing. I'll tell you how it changes. Right now, don't think about that versus labels. This classification token is simply 0th token. That's it. And that token's context vector will be used for classification. Then transformer encoder looks exactly like the left-hand side, or almost exactly like the left-hand side of the attention is all unit paper. So this left-hand side was BERT-like model or vision transformer-like model. And LX means this block, transformer block, will repeat L number of times. The value of L can be 12, 24, etc. In the paper, they have tried 3 models, vision transformer base, large and huge or something like that. 3 models, if I remember correctly, they have tried. The only difference is the location where this layer normalization happens. So in the attention is all unit paper, this layer normalization was happening after multi-head attention. This layer normalization was happening after feed-forward neural network. So this was called post-layer normalization. Here, on the other hand, they tried pre-layer normalization. So this is before multi-head attention, and this is before multi-head attention, multi-layer perceptron. So this was the only difference. Now, if you ask me what difference this brings in accuracy, I have no idea. If I were the one who was building vision transformer, I will try both. I will see which one works better. That is the only way. Otherwise, it's very difficult to say which layer normalization works better. But you should note that this is the primary difference. So this is now the transformer encoder used in vision transformer. And this left-hand side is the encoder proposed in attention is all you need paper. This was repeating n number of times. So nx means the transformer block was repeating n number of times in series. Here it was repeating same, just they used a different variable name. That's it. L number of times in series. But you see that these two things are almost exactly the same, except for the position. Pre-layer normalization in this case. In this case, it's post-layer normalization because it's done after the MLP and after MHA. Now, the images, the way it is tokenized, it's converted into patches is not based on number of patches, it's based on patch size. So here, the title of the paper is an image is worth 16 by 16 words. So here they use patches of size 16 by 16. What that means is if you had an image whose dimension was 64 by 64, or let's say your patch size is P by P, and image height is H, and width is W, you will have H by P patches along the height, and you will have H by W patches along the width. So total number of patches would be, sorry, my bad. W by P patches along the width. And total number of patches would be HW divided by P square. Number of patches, where P is the patch size, H is the height, and W is the image width. Now, if image size is like square, and if we call that using IMG size as the variable, you can simply say IMG size square divided by P square. This will be the total number of patches. And if I call N equal to IMG size divided by P the whole square, what is the total number of tokens that go into my transformer encoder in vision transformer? Number of tokens that let's say multi-head attention should expect in the vision transformer equal to. So my question is, this is the number of, this N is number of patches. Isn't that correct? Total number of patches. how many tokens will enter the multi-head attention, MHA? It will be n plus 1. So it will be 1 plus image size divided by patch size, the whole square. Why? This 1 is for classification token. These n number of tokens correspond to the images. So that many tokens will be entering into my transformer encoder. Okay. Now, after transformer encoder, here, based on what I have mentioned, what comes here? What is passed into this MLP head? I'll tell what this MLP head is, but tell me what goes here. From transformer encoder, what goes here? What goes here is, we can call it as, so if input we call as X. So X0, let's say it is CLS tokens input. Let's say this is X1, etc. up to X9. And let's say after each transformer block, X will become Z. So let's say after first block, it's Z01. After first block, first token will become Z11. Like that, ninth token will become Z91. Like that, I have L layers, which means Z0L, Z1L, etc. up to Z9L. So this Z is the context vector corresponding to Z0 is the context vector corresponding to 0th token after Lth transformer layer. So Zij is the context vector of ith token after jth transformer block. And I runs from 0 to 0 is the classification token, and it runs from 0 to HW by P square. And J runs from 1 to L. You have L transformer blocks in series. You have n plus 1 number of tokens. The 0 token you can call as 0, and then the last token will be HW by P square. H is the height, W is the width, P is the patch size. So n equal to, it is the same. So it is, see, if your image size is 64 by 64, and if patch size is 16 by 16, right? This is 16 by 16. This patch can be fit 4 times along the row and 4 times along the height, right? Which means I can have H by P number of patches along the height multiplied by H by P patches, W by P patches along the width, which is HW by P, which is image size. Image size is either height or width, the whole square divided by P. If it's a square image, if it's not a square image, H need not be equal to W always. It just needs to be divisible by the patch size. So what goes into my MLP head will be Z0. What will go into my MLP? Z0L. This is the context vector corresponding to 0th token, which is the classification token, after the Lth transformer layer. So this is what goes into my multi-layer perceptron head. And this will be a 768 dimensional vector. Now this vector is passed into MLP head, which will simply look something like this. I can simply say I have 768 that multiplied by 1 layer. And then let's say my output, in the output, I have 21K classes. If my data set belongs to ImageNet 21K data set, then I'll have 21K nodes here. So the dimensionality here will be 21K multiplied by 1. And I can have fully connected connections. Every node is connected to every other node. So how does this transformation happen? How do you go from 768 by 1 vector to 21,000 by 1 vector. What do you use for this? You use a matrix. Let me just stop sharing and I'll reshare. Yeah, you will use a matrix of dimension 21,000 by 768. So 21,000 by 768 matrix. You multiply this with 768 by 1 vector to get 21,000 by 1 vector. So you can use this now this matrix will be again learnable parameters. So that matrix will form the weights here, W11, W12, etc. up to W1 21,000, then W21, 22, W2 21,000, W31, 32 like that. So basically these weights are the values inside this W matrix. So essentially W multiplied by Z0L will give us our Y. And we can take softmax on this Y to get probability distribution. Hidden layers, I don't think it's needed. Hidden layers are there in the multi-layer perceptron over here. But in the MLP classification head, it's just a classification header. But here there is a hidden layer. All right. So this is essentially what a vision transformer is doing. Now we have to do coding, right? Now let's see if we were coding, what all things should we focus? Let's write down. First, we should have datasets. So MLP head is different from MLP in transformer layer. Exactly, it is different. Here, see, MLP is simply a neural network, feed-forward neural network. So it will not have any convolution operation or anything like that. So MLP head is just transformation or linear projection of your, in fact, I won't say linear because it has non-linearity. It's a projection from your classification token after the transformer encoder into whatever is your number of classes. So if your number of classes is 10, in our case, in fact, we will be having 10 classes, not 21K classes. You are projecting your 768 dimensional vector into 21K or into 10 or whatever your number of classes are. But this multi-layer perceptron has a different purpose. This multi-layer perceptron is used to enhance or enrich the context vectors themselves. So in this MLP, what was done was, let's say your context vector is, let's say in Lth layer, your context vector Z looks like Zi or Kth layer, Zik with 768 dimensions. So you will have 768 dimensional, these many nodes. This will be projected into a higher dimensional space, 768 by 4, typically a 4x dimensional space. And then you will project it down again into 768 dimensional space. So this projection into a higher dimensional space and back into its original dimension, this can enrich the features because in this space, you have 4 times more dimensions and all these are learnable parameters. All these weights are learnable parameters. So this is the opposite of like variational autoencoder. I mean, autoencoder. In autoencoder, you encode into a lower dimensional space and then you try to decode. Here you are trying to project it into a higher dimensional space in the hope that your context vector will become much richer. And in fact, there was an assignment which I had posted, and there is also a video which is coming out today at 2 p.m. on our channel, where you will see that this MLP carries almost 2/3 of your total number of parameters. Total number of parameter means if you have 175 billion parameters in your GPT-3, for example, 2/3 of that belongs to your all multi-layer perceptrons in the transformer blocks added together. Only remaining 1/3 of the parameters are found in multi-head attentions. And very, very small fraction, like 2% is only found in the rest of the architecture. So here, in GPT, basically, 1/3 was found here, GPT-3. 2/3 of the parameters of 175 billion is found here, not in just one, in all the 96. So in GPT-3, they had 96 layers. So all the 96 combined, MLP will take up almost 2/3, MHA will take up almost 1/3, remaining will take up 2% roughly. So multi-layer perceptron carries a very big role. Okay, now let's think about encoding this. What all do we need? First, we need dataset. Second is we need to have some way to tokenize the dataset. Okay, there's a question, why can't we stack the context vectors and send to MLP just like normal transformers like sentiment analysis? For stack up, you mean concatenating the vectors from different multiple heads? That's not what you're asking, right? You're asking about all the tokens, right? All the context vectors somehow either added or concatenated. Is that what you're asking, Sandeep? I don't think in GPT anyways, they were not doing that. They were doing that in multiple heads of the attention head. In inside one transformer block, you will have, let's say, 96 attention heads. Each attention head will take care of 1 by 96 dimensionality, whatever should be the output dimension, and then you will concatenate. But at the end, you are not concatenating all the context vectors. You are simply using the last context vector for next word prediction. So same thing is being done here. So in Vision Transformer, they explicitly mention at one place that they wanted to introduce minimum change to the already popular transformer architecture, which was introduced in Attention is All You Need paper. But I mean, yeah, I wouldn't be against trying just like don't use classification token at all. Try if the context vectors corresponding to the rest of the tokens, if you have n+1 tokens, don't use classification token, don't introduce it in the first place. Just use the n token somehow and see if you are able to represent the image to get good classification accuracy. It is something worth trying. In the paper, they have tried it, but their accuracy was not good. In an image 640 by 640, what do you mean by token? Yeah, so in 640 by 640 image, the total number of patches will be 640 divided by 16 multiplied by or square of this, which is what, 40 square, right? So 1600. So each patch will become one token. So each 1 by 40th of the or 16 pixel patch in that big image, this will become one token, this will become one token, this will become one token, and so on. So that is what I mean by tokenization. Patch will become vector. Patch is just a two-dimensional image. Vector is just a multi-dimensional numbers. So yeah, so we need data set. Next, we need to convert data set or images into patches. So we need some sort of patch embedding algorithm. Then we need transformer encoder. So this is the second part of this. This is the part 1 of the vision transformer. This is part 2 of the vision transformer. Fourth is we need MLP classification head, so or MLP head. This is the part 3 of the vision transformer. Then perhaps we can have one class written in Python where we can just say have one vision transformer class which combines part 1 plus 2 plus 3. Part 1, 2, 3 we combine. Then we need a training loop, or before that we have to define like device equal to CUDA, optimizer, device. We have to define, let's say, epochs and bunch of things. So that I forgot to mention, let's say variables, bunch of variables we have to define. Then we can also have a validation data set, and we can see how much is the validation accuracy. And then finally, we can have some sample test on some sample images. So display some images from our data set and see what the vision transformer is predicting for classification. So sample classification prediction. How to do regularization in transformer? Layer normalization is the particular technique. So layer normalization is one, but in transformer, they also use dropout right after the, okay, meeting room. Yeah, so they also use dropout right after the multi-head attention. They also use dropout. I think they use it optionally after multi-layer perceptron also in the transformer block. But the other technique is layer normalization, sample classification, prediction. So if we can do these many items in today's lecture, we can say at the end we have built and trained the vision transformer architecture, right? So that is exactly what we are going to do now. So what I suggest is I don't have any single line of code written yet. I'm going to write, I'm starting from this empty Google Colab notebook. So you can also open Google Colab and you can write the code along with me. Can you see my Colab first of all? Can you see the Colab notebook? All right. So now I'll tell you what may happen. While writing the code, maybe some mistakes might happen on your end, and there are 100+ people in this call, and it's impossible for me to look at everybody's, let's say, syntax issue or some error that might have happened. Ideally, if you are coding exactly the same as what I'm doing, things should work, but I'm foreseeing some errors to happen to people. In that case, just post the error and you guys please try to help out yourself. I'll try to maximum help, but I can foresee that some issues can happen. That's the first thing. Second thing is, I don't think you need GPU or anything. The code is reasonably fast. We will be working on the MNIST dataset, which is one of the simplest datasets to work on. So MNIST is simply this handwritten digit classification. So it's like a 10-class classification dataset. And if you don't have Colab Pro, you can still have, I think, one of these T4 GPU, I think you will have. I have all of them because I have Colab Pro. But in your case, I think you should have CPU or T4 GPU. Just check that. Whichever is available, you can use that. But in either case, even if you just run with CPU, I don't see it will take too much time for you. It should be fast. So now let's start writing the code. We will start from the very basic. Let me also take some notes so that I'm not making random silly mistakes. The first thing we can do is import some packages which we will need. Not all of them. Some of them we'll import now. Some of them we'll import on the go. All right. So we will need torch, PyTorch. Then we will need data loader, import torch. Then let me increase my font size. I hope this is better. Import torch utilities utils.data as data loader. Let me just have these two things for now. Remaining, I know that there are bunch of other libraries that we require, like nn.module. Maybe I can import that also. Import torch.nn as nn. So all these three are basically from PyTorch. Okay, so just have this ready and run the code. I will just switch to maybe TPU. Then the next thing is, let us get the data set. So download data set, basically MNIST data set. And this can be done from Python image library or PIL, PIL. So Python image library has a bunch of data sets. It's not just MNIST, there is fashion MNIST and many other. Yeah, training and loss forward and back. Yeah, it will all fit over in the training loop. So first of all, I'll tell you where we don't have to do some things from scratch, which is the whole reason why we are using NN. But I'll also tell you the training loop part. Okay, so we have these three libraries, but we will need a few more libraries. We'll figure out on the go. Now we have to download some data set, which is MNIST. So train underscore data set. So this is the training data set. And this we will download from Torch Vision, which means we'll have to import Torch Vision also. So import Torch Vision. So PyTorch for computer vision. Just run this. So these four, please ensure that you have these four. Torch Vision dot datasets dot MNIST. So we are getting MNIST dataset from the datasets in Torch Vision. And we want the dataset to be stored somewhere. We can say root equal to dot/data. So in the folder over here, it will create a data folder in which the MNIST dataset will be downloaded. This can be pretty much anything, but just give dot/data or something like that. Then this is the training dataset, which means I have to say train equal to true. And that's it. Similarly, copy paste this. Yes, you can use any dataset, your own dataset. It's fine. MNIST, the reason why I choose is I know that MNIST dataset can be trained in a reasonable amount of time. So you can see, you'll be happy to at the end of the day see a good accuracy, right? At least by the end of the lecture. That's the only reason why I choose MNIST, but otherwise you can choose any dataset. Next is validation dataset, torch.datasets.mnist. Everything is the same, train equal to false, which means this is not a training dataset. So this is the dataset download part. Let me put it here. Now there is one issue here. This dataset is taken from Python image library or Pillow, but we need to convert this dataset into tensor format because PyTorch or neural networks defined using PyTorch will expect tensor format input, which means we have to define certain transformation here. So transformation or transform equal to, it's expecting something. So let's define what this transformation is like. So data transformation for converting PIL to tensor format. So define the transformation earlier. So data transformation, you can define whatever variable you want here. Variable name is not an issue. Here it should be transforms dot compose of transforms dot to tensor. So we are defining the transformation from PIL to tensor format. And here we will have to also import torch vision dot transforms as transforms. So from this transforms is where we are calling the to tensor function. So just define this data transformation. Transforms is not defined. It's because I have not run this block of code. So now see, I have these 5 things, okay? Just make sure you also, everything is from PyTorch or Torch Vision. Then I have to just pass this transformation, data underscore transformation, we pass here. So transform equal to data underscore transformation. Do that for both validation data and training data. So train dataset equal to torchvision.datasets.mnist. Then root, we define the folder path. Train equal to true for train data. Train equal to false for validation data. Transformation is the transformation that we have defined here, which is converting the PIL data to tensor format. And then you run the code. Download equal to true. Yes, we need to mention that also. Download equal to true. So mention download equal to true for both training and validation data. All right. So hopefully so far it should work for you. It's very basic code. Now we need to do one thing. In neural network training, we usually use dataset in batches. We don't train one image at a time. We train one batch at a time, which means we have to create batches using training dataset and validation dataset. So create batches for neural network training. This is where we use the data loader, which we have defined here. So now we can say train underscore loader equal to something, val underscore loader equal to something. Now what will this be? Data loader dot, from this we call the function called data loader. So data loader is imported here. So torch.utilities.data is imported as data loader. From that, we are calling this data loader function. And into this, we pass, for train loader, we pass the training data set. And then since we are creating batches, obviously we have to mention the batch size equal to, let's say, 64 or something. And we have to say shuffle equal to true to shuffle the training data. But for validation data, we don't have to shuffle it because we just need to see what's the validation accuracy. So this can be kept true or false for validation data set, doesn't matter. Now, one more thing that will be nice is instead of this batch size being a fixed thing like 64, it'll be great if we can have some variables defined. So now let's see what all variables do we need. So I can maybe define variables up here. Variables that I need. Yes, val loader should contain val dataset. Yes, thank you. So variables I need, let's define what all variables we need. Firstly, we have image size. And we know that this image size, we don't have to calculate since we are using MNIST dataset. We know that image size is 28 by 28 or something, right? That we can just define. But if we are changing the dataset, it's better to use it as a variable, but here it's okay. So image size is 28, which means a good patch size to choose will be a number that perfectly divides the image size. So patch size we can keep as 7, which means along the height there will be 7 patches, along the width there will be 7 patches. So totally there will be 16 patches. But if we keep patch size as 14, there will be 4 patches per image. And then we can say number of patches equal to image size divided by patch size. And this we have to do 2 times. So this is along the width and this is along the height. Or we can simply say this raised to 2. Raised to 2 is 2 times multiplied symbol, raised to 2. But this will have one problem. Can anyone tell me what problem this might have? This line might have a small issue. Yes, floating point. So what we can do is either we can convert to an integer or we can just use this floor operation. So floor operation, what it does is if the image size was 30 and patch size was 7, 30 is not perfectly divisible by 7, there is a remainder. But float operation, this floor operation will pick the lowest integer, the integer just before. So we can do this. And then if we print number of patches, it should be 16. Otherwise, it will be 16.0. If this is not there, it will be 16.0. 16.0 is not the number of patches. It has to be an integer. So let's use this. No, we are not losing information here because patch size and image size, this number is perfectly divisible. We have picked the patch size such that it's perfectly dividing image size. Okay, now what we need is dimensionality of the token. So token dimensionality, let's say it is something like 32. So each token will be 32. Then we need number of heads, which is number of heads in the multi-head attention. Let's say it is 4. So this is what? This is L, right? The parameter L. No. So this is not L. Number of heads is a number of heads in each attention head. Attention heads is the transformer blocks is the value of L. So this will be, let's say this also is 2. So this is L. This one does not have a variable name yet, but images are not color. This one is black and white, just grayscale image. Shouldn't the token dimension be 10? No, token dimension is the dimensionality of the vector, which we said has to be 768. Number of tokens is 10, or number of patches is this, but token dimension should not be 10. Token dimension can be anything. Number of tokens is also not 10. That was my bad. Number of tokens is whatever is your total number of patches plus 1. Token dimension is whatever should be the vector that corresponds to each token, the dimensionality of the vector. It can be anything. It need not be equal to the number of classes. So token dimension is equal to, let's say 32 for now. Number of classes is 10. Num classes equal to 10. Yes, number of heads here, I think it should be, ideally it's better if it's divisible. 32 and 4 are divisible. So each attention head will take care of 8 dimensions. And if you concatenate 8 4 times, you will get back 32. But if this was 30 and this was 4, I think it will cause an issue. So, or if this is 32 and this is 5, I think it causes an issue. So this 32 should be, whatever this is, should be divisible by this. Number of head y0 is the transformer blocks number. So transformer blocks is the number of times. Let me go back to my board. Transformer block is different from number of attention heads. Transformer block is how many times does this thing repeat? How many times does this whole thing repeat in my architecture? Here it repeats L number of times. So the value of L is whatever is the number of transformer blocks. But here in multi-head attention, you will have multiple attention heads here. That is different. So multiple in GPT, they had 96 attention heads here itself. 96 attention heads here in each transformer block. And like that, these transformer blocks themselves were repeating in series 96 times. And these attention heads were operating in parallel. Like that, you have 96 attention heads in block number 1, in block number 2, in block number 96. So this is the number of blocks. This is the number of heads. And in our code, the variable name is number of heads is equal to 4, which means this is 4. This guy, the number of heads parallel here. Number of transformer blocks is also 4, which means the number of times this whole gray color block will repeat in series will be also 4. Now, how does multi-head attention process your input? Your input comes, and let's say input is having 16 dimensions. Output that comes out of multi-head attention is also 16 dimension. And let's say you have 4 attention heads in your multi-head attention. Okay. Let's say there are 4 attention heads. The final 16 that you get here is the result of concatenation of the output from 4 attention heads, which means each attention head was taking care of a 4-dimensional query key vector. This was taking care of a 4-dimensional query key vector. This was taking care of a 4-dimensional. And how do you get that 4? It is 16 divided by your number of attention heads. So if your attention heads was 5, it would have caused an issue because 16 and 5, you cannot divide 16 by 5 perfectly. So you cannot define how many dimensions does each attention head take care of. So each attention head, whatever output you get from each attention head. So let's say this is 16 and you have attention head number 1. This is query key value. And like that, let's say there are 4 attention heads. Then what comes out of here, the query vector is 4-dimensional. This is 4-dimensional. This is 4-dimensional. Query, so this is QKV, QKV, QKV. So these are all 4-dimensional. 4-dimensional, 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 4, 4, 4, 4, 4, 4. And then this query and key, you take dot product to produce attention weights matrix. Eventually, which will be 4 by 4. And then you multiply that with the value vector to produce your context vector matrix. Okay, here you can't say it's 4 by 4 because I don't know how many tokens are there. But attention weights matrix and then the context vector. Context vector will be 4-dimensional. Here also it will be 4-dimensional. Here also it will be 4-dimensional. And this also will be 4-dimensional. And then after the 4 attention heads in multi-head attention, you concatenate these such that 4-dimensional, 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 4-dimensional. This will be back into 16 dimensions. So this is how it goes through. 16-dimensional input comes into and goes into 4 attention heads in your multi-head attention. So now this is your MHA with 4 heads. And when it comes out of MHA, you concatenate it to get back 16-dimensional vector. This is why, so this 4 equal to, the way you get 4 is, so MHA dimensionality is equal to dimensionality at the output, D out, which is 16, divided by number of heads. So MHA dimensionality in this case will be 16 divided by 4. If there were 2 attention heads, it would have been 16 divided by 2. Each attention head would take care of 8 dimensions each. So that is the reason why here number of heads is 4 and token dimension is 32, which means each head will take care of 8-dimensional query. The query key space is 8-dimensional. Okay, number of classes is 10. Why do I use D out? You use D in. So the reason why I explicitly said D out is sometimes D out can be different from D in also, although in GPT, D out is equal to D in. So for the case of GPT, instead of saying D out, I can say D in. But you can technically have D out to be different from that of D in also. That's the so the right thing to say is D out, because after the concatenation is where you get D out. So technically, D out divided by number of heads is the dimensionality of each attention head. It need not be exactly same as D in, although in GPT it is exactly same as D in, but it need not be that way. Okay. So now, how is L combined? L is not combined. L is just put in series. We do not combine the L dimensional. Oh, let me connect my charger. We do not combine the inputs from each of the L transformer blocks into one thing. That we do not do. All right. What else is there? We have to have number of transformer blocks. Yes, MLP hidden dimension. So this hidden dimension is the number of dimensions of the NLP in where? In this one. In this MLP here. And that we can say, let's say it is, let's keep it bigger than the token dimension. In GPT, it is 4 times token dimension. So it is usually 4x token dimension. But here I don't care about that. Maybe I can keep it as 64 and then we can play with this. Then maybe we can say learning rate during my backpropagation, 3 times 10 to the power of -4 or something. This we can play with. Again, it's a hyperparameter. Number of epochs equal to, let's say, 5. I don't think I'm missing any other parameter. I think that's pretty much it. Number of, oh yeah, one more thing is number of channels. So if it's an RGB image, number of channels will be 3. This is a color image. This is a black and white image. So, or rather grayscale image, number of channels equal to 1. So these are my variables. If I need any other variable, I'll define it later. So this is the image size 28 by 28, number of channels equal to 1. It's because it's a black and white image. Patch size is 7 by 7, which is the dimension of each patch of the image. Number of patches will be image height divided by patch size multiplied by image. Oh yes, batch size. Very good. Excellent. Batch size equal to 64. 64 or 32, whatever, I can pick anything. But here, then I will use this variable instead of 64. All right. So I think these are the variables that I need. I don't need any more. If we need any more, we'll figure it out. So just define these variables before you run the train loader and val loader. And here, just pass the batch size variable rather than passing the, number 64. Okay. Now we need to define 3 things. So first is part 1 of vision transformer, which is patch embedding. Then second thing is part 2 of vision transformer, which is transformer encoder. And next, part 3 of ViT will be MLP Head, Classification Head, MLP Classification Head. And then I can say part 1, 2, 3 combined. So these are now the 4 things that we have to write. And after that, we can run the training loop. Should the batch size be multiple of total number of tokens per patches from each image, or that doesn't matter? So batch size is nothing but, so batch is not related to tokens. Batch is related to number of images. I'll ask you one question. Let me come to that. Does query for CLS token attend to all token keys patches? Yes, it does, because it's not a mask attention. Query from every token, including CLS token, attend to every patches, including CLS tokens and all the other patches. Import needs to be corrected from torch.utils.data import. So here what I'm doing is I'm calling this import torch.utils.data as data loader, and from here I'm calling data loader dot data loader, or otherwise I could have just written like this, torch.utils.data dot data loader. So either way it works. All right. Now let's write patch embedding. So this will be a class. Now here, what token dimension means here when we have image, it's about pixel. No, it's not at all about pixel. See, if we were treating each pixel as a dimension, now imagine if you have a high resolution image, your number of dimensions will be so high. Here, token dimensionality is what do you convert your patches into? What dimensional vector do you convert your patches into? Is it 1-dimensional vector? Is it 2? Is it 3? Is it 768? You essentially are converting into vector. Now, what should that vector's dimension be? It is not directly related to input image embedding. Input image pixels. So now here we are going to write 4 classes actually. Part 1 will be a class, part 2 will be a class, part 3 is a class, and part 1, 2, 3 combined will be another class. So this class we call as patch embedding. Now there are a few things which I want you to note here. Firstly, in patch embedding, we will be passing something called nn.module. So nn.module is very important. So there are certain properties for classes. Classes can inherit properties from its parent class. Classes can pass properties to some other class. So here, essentially what we are doing is, if you remember, import torch.nn as nn. So we are inheriting certain properties from PyTorch's nn for neural network. So this, if we pass nn.module into this class, then whatever neural network we define inside this class will be defined according to PyTorch compatible format. So whenever, and you will see this almost always, whenever you are writing or building neural networks from scratch using PyTorch, to most of the classes, you will be passing nn.module, or the properties which are there already defined in PyTorch's nn, you are importing it here. So class patch embedding, into that you are passing nn.module. Now the first thing that we have to do for every class is define init. So this is 2 underscores, okay? So underscore init underscore self. And I'll tell you what exactly we are doing here. So first thing, in Python class, what happens is, the reason why you are defining classes so that you can later instantiate the class by creating objects. And whenever you create an object, that is when you will initialize the functions that are defined in the class. So when you are defining a class, this thing will you will always again and again you will come across this. The more you use this, the more the intuition will be. But basically, whenever you are creating a class, whenever you are creating an object corresponding to a class, it is called, or it is in Python, it is referred to as, that object is referred to as self. And then this self is passed into this init constructor. And this is one of the default things which you will come across in almost all classes. You can write Python function also, but the easiest way to do to take properties from nn.module is to define it as classes, because there is now a parent class, now there is a child class. So now I'll show you how to inherit some parent class properties. So super dot underscore underscore init underscore underscore then functional bracket. Now what this tells is, so this init belongs to which class? Patch embedding class. But there is one init in nn.module also. So this super tells that you are now initiating, or you are now calling the init constructor from your parent class, which is whatever you are inheriting from nn.module. So two things, and this in all the 4 classes that we are writing today, these 2 lines will come again and again. Okay, so please note this. So first one is defining the init constructor for our current class, which is patch embedding class. Second thing is we are asking it to look at the parent class, and the parent class is nn. And in that there would be another init constructor defined by whoever wrote PyTorch, whoever wrote nn. And then this super is saying you initiate the init constructor from that class. Okay, super, then functional bracket dot underscore underscore init underscore underscore. All right. Now we say self dot patch underscore embed. So this is now the defining the action of patch embedding. Now let's see what exactly do we need to do in patch embedding. Let me go back to my whiteboard. So I have an image of size 28 by 28. And like this, I have a batch of how many images? 64 images. So my batch, not patch, batch B. So I have batch size of 64. I have number of channels per image of 1. I have image size of 28 by 28. So this is how my dimensionality will look like. So this is batch underscore size. This is number of channels in the image. This is width of the image, height of the image. Now, what do I want this batch to become? Batch size should not change, because if I have 64 images in one batch, that batch size should remain the same, correct? But what should each of these images, what should it become? Ultimately, this whole thing, each image should become 16 patches. Each image should become 16 patches. Why? Because my patch size is 7. If patch size is 7, I have a rectangle like this here, 14, 21, 28, and like that along the width, along the height also. So each image should become 16 patches, and each patch should have a dimensionality of what? 32, correct? That is what we have defined here. Token dim is 32. So I want my input of dimension 64, 1, 28, 28. After my patch embedding, this is what I want it to become. So now this is the batch size. See, think about this. Before I add my classification token, what do I have? Before I add my classification token, I simply have 16 patches, correct? And classification token is added to 16 patches whose vector dimensionality is 32. 32 can be 128, 768, whatever it is. But here we have defined 32. So I have 64 images in a batch. So this is batch size. I have 16 patches in an image. So this is number of patches, num patches. Each patch becomes a vector. So this is embedding dimension or input dimension. Now this is what I want to become. Number of channels, it doesn't matter whether we are inputting RGB image or color image. At the end of the day, whether the number of channels are 3 or 1, it should become this, right? If my batch size was 1, then I will simply have one image in my batch. Each image will become 16 patches. And then each patch will become 32-dimensional vector. Now let's see how to make this happen. My image has one channel of dimension 28 by 28. Now, first, what I can do is, let's say, now we know that this is not a convolutional neural network. This is vision transformer. And one of the biggest value propositions of vision transformer itself is that it does not use convolution operation, right? But we can very cleverly use one convolution operation, which is essentially a matrix multiplication, to convert your image into patches. Now, let's say I had a convolution operation whose kernel size is this much, is 7 by 7, whose kernel size is 7, whose stride is 7. Okay, so let's say I had a conv2D operation whose input number of channels is 1, whose output number of channels is 32, whose kernel size is 7, whose stride is 7. I will write these numbers. So this is input channels. This is output channels. This is kernel size. And this is stride. Okay. Let me make you understand how does RGB image get converted to, in any convolution operation, how does an RGB image get converted to an output? So let's say I have an RGB image. Yes, currently we are assuming we don't have RGB channel, but let's keep it as an RGB image for once. Let's say this is an RGB image. So number of channels is equal to 3. Dimensionality is 28 by 28, correct? And let's say I have one filter, one convolution filter, whose dimension is 7 by 7, whose stride, there is no padding, I'm not adding any padding. Stride is equal to 7. Okay. What will be the dimensionality at the output? Let's say this is my input. This is my convolution operation. Now I have to have an output. What will be my output? So stride is by how much will your this thing jump. So stride looks like this. This is by how much will your convolution filter jump in each convolution operation. First it will be here, then it will be here, then it will be here, then it will be here, like that. So can you tell me what will be the dimensionality of my output? Spatial dimension, what would that be? Spatial dimension will be 4 by 4. There is no doubt about it, right? Because you have a 7 by 7 convolution kernel with stride 4 acting on a 28 by 28, but spatial dimension will be 4 by 4. But my question is not about spatial dimension. That is very easy. What should be the Z stack dimension? What should be the number, the number of stacks? So this is 4 by 4. Will the number of stacks be 3, or will it be 1? My question is this. Spatial dimensionality of the output is 4 by 4. Anybody can see that. What should be the Z stack dimensionality? Will it be 3 or 1? For those of you who said 1, why is it 1? So the way it works is your number of channels. So one thing I have not shown here is your number of channels here in your convolution filter will be 3. And the way it works is, let me just combine this. First, it will operate here across all the 3 layers. Then it will operate here across all the 3 layers, all the 3 layers, all the 3 layers, like that, to produce 1 channel output. It does not produce 3 channel output, it produces 1 channel output. So this convolution filter will have 3 channels, but the number of filters, so channels in the convolution filter, in the convolution is equal to 3, but number of filters equal to 1. And the number of channels at the output should be equal to number of filters. So num channels or output num channels is equal to number of filters. Here you have only 1 filter with 3 channels, which means the output will be 1 channel output. If you want 3 channel output, you will have 3 filters like this. Filter number 1 taking care of first channel at the output, filter number 2, filter number 3. If we have something like this, then I will have 3 channel output. Then how does it work? This filter will take care of the first channel. This filter will take care of second channel. This filter will take care of third channel. Then the 3 filter values are combined by weighted addition. Just like how in convolution in spatial 2-dimensional, it is like a weighted addition, right? Same thing. Along the Z also, it is added. It's not average. Average also can be done, I guess, but usually it is addition is done. So this is how, if you had an RGB image. So now think about this. If I had just 1 filter, okay. So now let's come back to this. How 3 channels are converted to single channel. It's just like this: 1, 2, 3, 4. Let's say this is my image. This is my second channel, third channel. Okay. Now let's say my filter is looking like this. Filter should have 3 channels. And let's say the value here is 1. Then the output corresponding to first one will be 1 times 1 plus 1 times 1 plus 1 times 1. So first output will be 3. Second output will be 2 times 1 plus 2 times 1 plus 2 times 1 will be 2 times 3, 6. So the final output will be 3, 6, then what? 3 times 3, 9, 12. But now this output has only 1 channel. What if I needed 3 channels? Then I will have 3 filters like this. And now let's say my filter number 2 has values 2, 2, 2. Then my channel number 2 in my output will be 6, 12, 18, 24. And then let's say this value is minus 1, minus 1, minus 1 in the third filter. So now this is filter number 1 with 3 channels, filter number 2 with 3 channels, filter number 3 with 3 channels. This is input number 1 with 3 channels. But now this is the output which has 3 channels. And filter values are learnable parameters, exactly. Now these values will be minus 3, minus 6, minus 9, minus 12. So this is how, see, now look at this. This was an RGB image. And this RGB image can be converted to a 3-channel output. It can be converted to 1 channel output. It can be converted to any number of channels. It depends on how many filters you have. If you have only 1 filter, you will have 1 channel output. If you have n filters, you will have n channel output. The spatial dimension of each channel will depend on the filter size and stride. Okay. Now with this knowledge, let's come back to our goal. Our goal was this. We had 28 by 28 filter. Not filter, image. And just 1 channel. Now, I have 64 images in my batch. So let's forget about the batch for a moment. Let's assume that my batch size is 1. What I want is, first, I want to convert this into patches of 4 by 4. So how do you go from spatial 28 by 28 spatial dimension into 4 by 4 spatial dimension? So 4 by 4 spatial dimension means I have 4 patches. So along the height and 4 patches along the width. How do you go from 28 by 28 to 4 by 4? You can do two things. One is you can use a filter of size 1 by 1. Okay. And you can use a stride of 7. It is possible. But then what's the problem? You lose a lot of information because 1 by 1 filter, if you are jumping by 7 pixels at a time, the pixels in between you are not considering. Right? So instead of using 1 by 1 pixel, 1 by 1 filter with 7 stride, you pick 7 by 7 with stride equal to 7. So initially your filter will be here. And you need non-overlapping patches. Patches should not overlap. So that's the reason why we pick stride like this. So then after second stride, it will be here. After third stride, it will be here. After fourth stride, it will be here. So then your filter size should be what? Your filter size should be 7 by 7. And stride should be 7. That much is clear. If you use filter size of 7 by 7 and stride 7 on an input image of 28 by 28, you will get 4 by 4. Now 4 by 4 what? 4 by 4 patches. Now tell me this. What is the dimensionality of each patch? Each patch is equal to 1 token, correct? So what is the dimensionality of each patch? It's not one. Okay, patch has X, Y, and Z dimension. Tell me the spatial dimensionality of each patch. Spatial dimensionality of each patch. I'm not talking about 16 patches, each patch. Each patch is simply 1 by 1. This is one patch. Spatial dimensionality is 1 by 1. But how many channels does each patch have? (32 channels. It's not one channel because each patch we are now converting into a 32-dimensional vector. So now each patch, it will look something like this. So this is patch number 1. Let me just clean it up a little bit. So assume that this is 32. I'm just copy pasting it 4 times. So this is patch number 1, patch number 2, patch number 3, 4, like that. Now I have totally what? 16 patches. Each patch has a dimensionality of 1, or if I write it in the language of number of channels, comma, width, height, it will look like 32, 1, 1. Each patch has 32 number of Z channels. It has spatial dimension of 1 by 1, but I have totally 4 patches in height and 4 patches along width and 4 patches along height. Now, tell me how many filters do I need now? So this is the filter dimension that you have agreed. 7 by 7 it should be the filter size. And you can, this is obvious also, right? See, the 7 by 7 filter will be standing in front of another 7 by 7 set of pixels. So those 7 values can just have a weighted addition, right? To just produce one number. But like that, how many filters should I need? I will need 32 filters because I have 32 channels at the output. Let me clarify this once more. Maybe I can draw proper rectangles this time. So my initial image is not RGB image. I'll tell you what to do if it was an RGB image. If it was an RGB image, it will look like this. So RGB 28 by 28. Now my kernel will look like, since I have 3 channels, kernel will look like 7 by 7, but it will have 3 channels also, 7 by 7 by 7. And like this, let me just group this. I will require, let's say I had 2 filters like this. If I had 2 filters, my output will look like 1 by 1 by 2. And like this, I will have 4 by 4 outputs. 1, 2, 3, 4. This second row, third row, and fourth row. Now think about this. If I had an RGB image, this is what would have happened. Okay, let's go backwards. How many patches do I have here? What's the patches distribution? It's 4 by 4. I have 4 patches along the row, 4 along the column. Each patch is of how many number of channels? 2 channels. This is 2 channel, 2 channel, 2 channel, 2 channel. Right? This is the first channel. This is the second channel. What is the spatial dimension of each patch? 1 by 1. 1, 1. So each patch is 1 by 1, but they have 2 channels. Why are there 2 channels in these patches? Why did it become 2 channels? Because there are 2 filters. But there are 3 here. So why do you say 2? What is this 3 then? Those are 3 channels. Why do you need 3 channels? Because you have 3 channels at the input. But these 3 channels combined form filter number 1. These 3 channels combined form filter number 2. This filter number 1 will produce this guy, will produce this guy, this guy, this guy, etc. So filter number 1 will take care of these top channels. Filter number 2 will take care of bottom channels. Now, what is the only change? I want to, let's say at the output, I want the exact same thing. Okay. This exact same thing I want at the output, but my image happened to be black and white. What is the only change I have to bring? At the output, I want the same thing, but input happened to be an instead of an RGB image, black and grayscale image. Then only change I should bring is I don't need 3 channels here in the filter. I just need 2. So sorry, I just need 1 with 2 filters. So I can just remove this and just have a filter of number of channels 1. Spatial dimension will still be 7 by 7. That's it. So this is the only difference. The difference when you have an RGB image versus a color image is the number of channels in your filter. Now, in our case, the actual dimensionality at the output that we are expecting, let me just delete this, is something like this. This is 4. Let's assume that this is 32. Let's assume that the channel size is 32. Okay, so now I have my output. There are 16 patches. Why are there 16 patches? Each image was 28 by 28. We wanted to divide it into 7 by 7 patches. So 28 by 28 is image divided into 7 by 7 patches. Each, you will have total 16 patches. But yes, there are 16 patches, but here we are representing each patch as a vector of 32 dimensions. A vector of 32 dimension, you can also imagine to be an image of spatial dimension 1 by 1 and Z stack 32. Basically, it's a 32-dimensional vector, but here we are imagining it to be an image of 1 by 1 spatial dimension and 32 dimensions along the channel. So totally, you have 1 by 1 by 32. And input image is not a color image. It's a 28 by 28 black and white image, which means if my kernel size is 7 by 7, I will have just how many channels in my kernel? In each kernel, how many channels do I have? 1. Why is that? Because my input has only one channel. It's not RGB. But like this, I will have 32 kernels. Kernel number 1, 2, 3, etc. up to 32. First kernel will produce these outputs. Last kernel, 32nd kernel will produce these outputs. Okay. So this is what we are going to do. But this much, if I did not explain, you will not understand what I'm going to write in the next line. So self.patch embed is equal to nn.con 2D. So here we are performing a convolution, 2D convolution. And we need to define the number of channels. Number of channels is 1. And number of channels will define, number of channels in the input will define number of channels in my filter. Then I have to define my token dimension. Token dimension will define what? Dimension will define the total number of filters I need. Then I will define my kernel size underscore size. Kernel underscore size is nothing but patch size, which is 7. Then stride is equal to 7, which is same as patch size. If filter is 7 by 7, then the stride can be less than 7. Won't the patches overlap? Yes, correct. If filter is 7 by 7, if stride is less than 7, patches will overlap. So we should not use overlapping patches. That's the reason why here stride is 7. It's not less than 7. Now tell me this. My output will have certain dimensionality. Actually, we can see that what the output dimension will look like. Let's first write this function. Okay, so now we have the patching algorithm, but we have not implemented it yet. Now, in all the 4 parts, part 1, part 2, part 3, part 4, we'll be defining a forward pass. So in the forward pass, we are passing the self. So this self we are passing everywhere. Along with that, we are passing x, where x is the input. So define forward, and into that we pass the self. Self is the current object corresponding to the class. X is the input. To this, we say x equal to self dot patch underscore embed of x. So what happened to x? X was the input, which originally will be the input image itself. It will undergo patch embedding. Now x will become something of dimension. Let me go back to my whiteboard. The input dimension of x was 64, 1, 28, 28. 64 was the batch size, 1 was the channel dimension, 28 was the image height and width. After going through my current batch embedding formula, this will become 64, 32, 4, 4. Where 68 is the batch size, so that part remains the same. 32 is the dimensionality of each token, so this is token dimension. 4 by 4 because I will have an array of 4 patches along the row, 4 patches along the column, because 28 by 28 was a 2-dimensional thing. 4 by 4 is also 2-dimensional. It's just that this 28 by 28 guy only had 1 channel, but this 4 by 4 guy has 32 channels. That's the only difference, right? So please note this. This 28 by 28 became spatially, it became 4 by 4, but each 4 by 4 is now like a 32 channel thing, where you just have one, in each of the patch, you have just one spatial, 1 by 1 as a spatial dimension. So what we really have to do is, we don't care about having patches arranged as a two-dimensional array. We want patches as a sequence of 16 items, right? And then as the 0th item, we add the classification token. So what we have to do is X should now become, so now after patch embedding in this, it will become 64, 32, 4 by 4. But I want X to become initially 64, 32, 16, because this 4 by 4, I just want as an array of 16 items. I don't want it as a 2D array or anything. So here, what we can do is X equal to X dot flatten of 2. So what happens is everything starting from the second dimension will be converted into a single one-dimensional thing. So this is 0th dimension, this is first dimension, and this is second dimension, and this is third. So if I say flatten of 2, this, whatever is there after this, will be converted into a one-dimensional thing. So 4 by 4 will become 16. But that is not yet enough. I need to do one more thing. So I have batch 64 items in each batch. Then ideally, I should have 16 tokens. Then ideally, I should have 32 dimensions per token. But here, this is flipped. 32 and 16. I want ideally the token dimensionality to be here and the number of tokens to be here, not like this. So ideally, I want 16 to be here and 32 to be here. So this we can easily do by transpose. So now we say X equal to X dot transpose of, we are transposing 0th dimension is untouched, first and second dimension we are transposing. So 1, 2. And then we say return X. So now what will happen is X would have become, so because of the first operation, X would have gone from 64, 1, 28, 28 to 64, 32, 4, 4. Then after flattening, so this is the con 2D operation. Here there are learnable parameters. Where are the learnable parameters? Can anyone tell me where are the learnable parameters found in this? Because here the patches are being converted into vectors, but it has to be found somewhere. It is found here. These are learnable parameters. In each of these 32 kernels, you will find your learnable parameter. Each kernel is 7 by 7. If you have 32 kernels, and if you have 7 by 7, learnable parameters, assume if batch size was 1, would be 7 by 7 by 32. Then here you do flatten, and then here you do transpose. So now you get 64 batch size, 16 as the number of tokens per batch, per image, and 32 as the dimensionality of each batch. Otherwise, you will be looking at 64. This is the logical representation, right? You have images first, then batches contain image, image contain patch, patch contain token. So first item should be batch dimension. Second item should be number of patches per image. This third item should be token dimension. But here right now, it is batch dimension first, token dimension second, and number of patches third. So that's why we are doing the transpose. Okay, so now I could have done this just by saying X return patch.embed of, I could have written it like something like this, patch.embed of X dot flatten of 2 dot transpose of 1, 2. But then the problem is, if I had written this, nobody will understand anything. It's just one line, but there is so much going on behind this one line. So that is the reason why I split it into 3. Okay. And with this, our patch embedding class is done. That's it. Now you can just run this to make sure that there are no syntax errors or anything. But right now the class will not do anything because we have not instantiated it with an object. Now we write the class for transformer encoder. And obviously there also we pass nn.module. And then we define these two things. So these two are common for all. So I can just copy paste. Now in transformer encoder, what all things do I have? I have layer norm 1. I have layer norm 2. Then I have multi-head attention. Then I have multi-layer perceptron. One more thing is there, which I did not discuss in detail. One small thing. Dropout, let's say we don't have to do dropout. CLS token, we have not done yet. Position embedding, we have not done yet. But in the transformer encoder, there is one more thing, residuals. Where are the residuals? These two connections. Whatever comes here also has to pass here. And whatever comes out of this also should go here. Okay. So we should have those two residuals. So let's first define these things. Self dot layer norm 1 equal to nn dot layer norm. And layer normalization happens along the total number of dimensions in my input token. So this should be such that token dimension, whatever is the token dimension, that many number of normalization parameters will be constructed. So we just pass the token dimension here. Self dot layer norm 2 is also exactly the same. So we can just repeat it so that we have that many number of learnable parameters. So layer norm 1 and layer norm 2, we are just defining it. We are not yet using it. Then self dot multi-head attention equal to, so here is where we actually utilize Python's, nn dot multi-head attention, this function. If we did not have this, we would have had to define the whole thing from scratch, which is an unnecessary thing because they already have defined the class. We just need to train it by defining the token dimension and number of heads. So token dimension is 32, number of heads, if I remember, is 4. So self dot multi-head attention equal to nn dot multi. So now wherever you see nn, those are all trainable parameters. nn dot con2d, there are trainable parameters. nn dot layer norm, trainable. nn dot layer norm, trainable. nn dot multi-head attention, trainable. Then multi-layer perceptron, self dot MLP equal to, so now here in multi-layer perceptron, you have input layer, hidden layer, and output layer. So nn dot sequential, so you can add layers in sequence. And first layer is a linear projection from your input dimension to hidden dimension. So input dimension is token dimension, and hidden dimension variable was MLP hidden dim. So that is the hidden dimension. In between, there is a activation function. It's not ReLU, it's JLU, what is used in the vision transformer paper. You can see that here. So JLU is very much like ReLU. JLU graph, it's just smoother. So ReLU is the sharp version. This orange, JLU is this blue smooth version. It's a smoother differentiable function. And in vision transformer paper, if you look at third or fourth page, yeah, so here they say MLP contain 2 layers with JLU nonlinearity. So that is what we are adding here. nn dot JLU, and then you have another linear transformation from hidden dimension, MLP hidden dimension, to token dimension itself. That's it. So that is MLP. MHA is done. MLP is done. Residual is not done. But residual we can define. We don't have to. Residual we are implementing. We are not defining. These we are defining because these layers, after training, these layers we'll just have once. But then once you have these layers values fixed, you have to execute it on each token. That's the reason why we are writing the separate forward function, because into this we are passing each input. Now in forward, we can say residual 1. Here I am storing X. Then first is, let's go back to our image. After I'm storing the residual X, I have to go through layer norm 1. So X equal to self dot layer norm 1 of X. Then after layer norm 1, I'm going to multi-head attention. Then X equal to self dot this guy multi-head attention of. Now here I have to create query key value space. And the way you can pass X is one so that you can construct query, one so that you can construct key, and one such that you can construct values. You pass the same X. And the final context vector will be found in the output of this in 0th index. So you have to put a 0 index here. So in the 0th index is where you will find the output that you require. The output that you require is the final context vector matrix. And then in the image, you have residual added. So now you add X equal to what? X plus residual 1. So with these 4 lines, you have finished norm, multi-head attention, and this residual addition. Then you say residual 2 equal to also X, and X equal to self dot MLP of X. So it goes through MLP. Actually, there is layer normalization. X equal to self dot layer norm 2 of X. X equal to self dot MLP, and then X equal to X plus residual 2. So now I have residual 2 also added. This part is now the residual plus layer normalization plus MHA. This is now the residual plus layer normalization 2 plus MLP. And then we return X. And that ends the transformer encoder part. So layer normalization, MHA, followed by addition of residual, layer normalization 2, MLP, followed by addition of residual. Now we can, we have not added 2 things yet. I'll just explain what is this. So we need X is getting converted into query, key, and value. And here, the way I'm pretty sure this can be done in a separate way also, but X comma X comma X means the same X is sent for converting to query, same for converted to be converted to key, and for value. So that is why we pass X 3 times. One to be input so that it can be transformed to query, sometimes to key, and sometimes to value. I think the reason why this is done is sometimes in, for example, there is a concept called visual BERT or will BERT, not visual BERT. In will BERT, the query is from the text, but from the key and value are from the image. So then if you use the same X for query, key, and value, it will not work, because in my multi-head attention, I want query to be coming from image and key and value from text. And similarly, for text, I want query to be coming from text and key and value from image. So I think that's the reason why they designed it like this. And the reason why this index 0 is there, because at the end of the day, we want the context vector matrix, which happen to be stored in there, whatever is returned from this function. In that return, in the 0th index item is where we see the context vector. That's the reason why I put 0. Will X also contain patch for CLS token? Yes, X will contain patch of CLS token. Only thing is we have not defined CLS token yet. I will show you where we do that. Okay, now let's go on to multi-layer perceptron MLP classification head. This is the easiest. So class MLP head of nn.module. Again, we need these 2 things. We need constructor for the same class and for the parent class. This part is very simple. So one thing that is actually a bit confusing, which because of the way in which this figure was constructed in the paper, is that there is a additional layer normalization happening over here. In the multi-layer perceptron head, there is one layer normalization happening. It's not shown here, but it is mentioned in the paper. So if you go to the paper, this one I was initially confused. What is this layer normalization of? So this is now the context vector corresponding to classification token, which is why it's 0, after Lth transformer block. So there is a layer normalization happening to the context vector corresponding to the classification token before just before you go through classification head. But this was not shown in the image, so it will be very confusing if you just look at the image but don't read the paper. So that is the reason why I will add or define a layer normalization here. So self.layer norm But this layer norm is not shown anywhere in the image. Ideally, if I were making this figure, I would have just shown maybe one layer normalization somewhere here. That way, it's less confusing to the people who are coding. Yes, two things we have not done yet: position encoding and classification token. We are yet to define, but I'll show you where to do that. Self dot layer norm equal to nn dot layer norm of token dimension. Then what else do we need? We need one sequential linear layer. So self dot MLP equal to nn of linear between embed dimension to number of classes, right? So nn dot linear of embed dimension is same as token dimension and num classes. So here we project from a 32-dimensional vector to number of classes. I don't know what was the variable name. Yeah, number of classes. So here we go from 32 dimension to 10 dimensions. And then we define forward. So define forward of self comma x. And here we implement x equal to self. So this is Gemini's suggestion, what is popping up, but I'm just ignoring it. I'm writing the same thing only, but it'll be fun to write from scratch. Then x equal to, so here what we should do is x equal to self dot MLP of x, and then return x. Now we are ready to, now this x is what? By the time we are returning, what is this x? Forward spelling, yeah. Multi-head attention encoder block. Multi-head attention block will be too much for this lecture. I highly recommend you to look at the previous lectures because it will at least take me 1 hour. But this return x is the 10-dimensional vector, which we can use for, yes, exactly, logics, perfect, which we can use for softmax, right? Now let us combine all of this. Class vision transformer of nn dot module. Again, same two things, init constructor and the parent class init constructor. Now here we will do all the things which you have been asking. So first we have to do patch embedding. So let's define patch embedding, self underscore patch embedding equal to whatever is this class name. Where is that? Patch embedding. So this will be the patch embedding. Then self dot. Now we have to define CLS token. We have to define position embedding. We'll come to that. Position embedding. Then we have to define transformer blocks. Because we have multiple transformer blocks, we have only defined one transformer block here. So self dot transformer blocks equal to this. We have to define CLS token. We have to define position embedding. We have to define then self dot MLP. What was it called? MLP head underscore head. This is already defined. It is simply MLP head. So this is the classification head. Then what else we have to define? I think that's all. Classification is also done. Now let's look at the classification token. Classification token should have a dimension same as input embedding dimension, but it should have random numbers initialized and it should be learnable. So because it's learnable, it should be nn dot something. So it is nn dot parameter. This is a learnable parameter. Then torch dot rand n, which means we are pulling from a random distribution. Here we don't need dropout. For this data set, at least, let's ignore dropout for a moment. But ideally, if we were training for a bigger data set, I will definitely introduce dropout in multi-head attention. I'm not 100% sure if we can directly pass a dropout parameter here and dropout is taken care of inside this or not. I have to check that. I assume it will be possible. Dropout is a way in which you prevent overfitting. All right. So MLP head, what was the torch.random number from a normal distribution, and dimensionality is you have embedding dimension, but your patches, you had 16 patches. You had a 64 was the batch number. You had 16 patches. Each patch was of 32 dimension. You had 3 numbers to take care of. So you should have 1, 1, embed dimension. I'll tell you what to do with this. But I should have 3 items as part of dimension here. And this should be token dim, I think, in my variable convention. I'll tell you what to do with this. So right now I'm defining a classification token which has 3 dimension, and third dimensionality is where the parameter is coming. Then position embedding should be, again, it should be parameter. So nn dot parameter of torch.randn of something. And if I had one batch, I'll have 1 dimension for that. But here, what should be the next number? What should be the next 2 numbers, in fact? Position embedding, I'm defining position embedding, patch size and token dimension. Is it that, or position embedding is added to every single token? Correct? So it should be number of tokens plus 1, isn't it? Total number of tokens plus 1, because I have 1 position embedding for class token or classification token also, not just for rest of the tokens. So num, I don't know what was the variable name. I think it's called num patches. Yeah, num patches plus 1, comma, last dimension will be token dimension, because position embedding is also of dimensionality 32. Then number of transformer blocks. This we can write in 2 ways. nn.sequential, I can write it like nn.sequential of, what was the name of the class? Transformer encoder. And what was the number of heads? I think it was 4. Yeah, number of transformer blocks was 4, which means I could write it technically like this. This comma, this comma, this comma, this. 4 times I can write. But then what if I had 32? I cannot build it like this sequentially. So then the better way to do that is enclose this in square bracket first. Put star here at the starting, and then define a for loop. So transformer encoder for no variable name. So for underscore in range of whatever is the number of transformer blocks. So num, not num heads, transformer underscore blocks, I think. Yeah, transformer underscore blocks. So basically, I am looping a for loop 4 number of times, because the value of this is 4. And there I'm adding this transformer encoder sequentially. And this is the syntax for that. And MLP head is also done. So now there is one problem. The problem is my batch size is 64. So I need 1 classification token for each batch. I mean, each set of images should have 1 classification token. So if I have 64 images in my batch, I should have 64 classification tokens, right? But that is not provided here. Star basically does, that's the convention that is followed. Essentially what we are doing here is we are attaching 4 transformer blocks sequentially, so transformer encoder blocks sequentially in series. All right. Then we say, now we have defined these things, but we have to implement, we have to execute it for each token. So self define forward of self comma x. And then we can say, first we have to perform patch embedding for the token x equal to self dot patch underscore embedding of x. And then CLS token. So CLS token, what we need to do is CLS token equal to self.cls token dot expand. And we are expanding it along the batch dimension. So batch dimension is the first item. So then batch underscore size, comma, then the rest of the dimensions are untouched. Because I need if I have 64 batches, this first item should be 64. So I'm expanding it to fit the batch size. I'll tell you, there is one problem here, by the way. Can anyone tell me what might be the problem with this? The problem is specifically with respect to using batch size. If I directly use batch size, there is one small issue. Shuffling is fine. Of course, I'm shuffling. So here what we are doing is, see, CLS token is added to every single group of patches. Every single 16 patch should have one CLS token. But do I have 16 patches? No, I have 64 batches. In each batch, I have 16 patches, which means for each batch, I should have 64 CLS tokens, right? So the first dimension here should be 64. Remaining can be as such. So I don't have to expand the remaining dimensions. So this has to expand. So now the problem here is, if I directly write here batch size, what is my batch size, by the way? If I had 640 images, and if batch size is, let's say, 64, totally how many batches can I have? 10 batches, right? But what if I have 639 images? Then my last batch actually has how many images? It has only 63 images. It does not have 64 images. One image is less, which means instead of directly using batch size, it is better to use whatever is the actual batch size of that image. So I can just say number of images in current batch equal to x dot, we can take the x dot size of 0. Shape of 0 is also fine. X dot, yeah, actually shape of 0, let's use this. So the 0th dimension of my input, which is the actual number of images in my current batch. In all the batches, it will be 64, except the last one, because I don't know if the total number in my training data is exactly divisible by 64 or not. And this will cause a problem. And then this number, this variable I can use here. I can just use b or something instead of this huge thing. So b comma -1 comma -1. You can try running without this. You can try just running with batch size. You will run into some dimensionality issue. And now let's do one thing. Let's add position embedding. X equal to torch dot, we are performing concatenation, and nn dot parameter. So can you tell me one thing? I need 64 classification tokens for each batch. Should I also not expand position embedding to fit the batch size? So here I'm going to concatenate position embedding to, so x equal to torch.cat of CLS token, comma, x along dimension equal to 1. Not along the batch dimension, along the batch dimension. But my question is not this. My question is x equal to x plus self dot position embedding. Should I not repeat position embedding also along the batch dimension? The reason is position embedding, we don't have to learn it proportional to batch size. Position embedding, it is learnable for sure. It's a learnable parameter, but it doesn't matter whether you are in image number 1 or image number 63 in the batch. Position embedding, position is still the same, 1 to 16 or how many ever number of token patches you have, right? So I don't have to expand it. I don't have to have 64 different position embeddings. I can just use the same position embedding. Okay, so position embedding is done. Then you pass through. Now you have the ability to pass through transformer blocks. So x equal to self dot transformer blocks of x. Then after that, you have to pass through multi-layer perceptron, which is the classification head. Is there any mistake here? In this, is there any mistake? Exactly. From all the batch, I should only extract the classification token. So from all the batch, which is by x of colon, I'm extracting 0th index item in the second, in dimension index number 1. And then only I pass it to multi-layer perceptron for classification. And once this is done, I can simply return x. All right. So that is also done. So now we have vision transform, and let me just run this to make sure there is no syntax issue or anything. So now we have all the 3 ready, and now we can define some things for our training. So device equal to CUDA, all those things we can define. Model, optimizer, just 3-4 lines. So now most of the hard work is done. Now it's simple. And loss. So device equal to torch.device.CUDA if torch.CUDA is available. Else use CPU. Then model equal to model. For that, we just need to call this. So vision transformer dot to device. So whichever device we are using, GPU or CPU. Then optimizer, almost always we use Atom. Torch dot optim dot Atom. Into that, we are model parameters is what we are optimizing. Model dot parameters, comma LR equal to whatever is the learning rate variable we have defined, which we had defined at the beginning. And criterion will be cross entropy loss. So that's it. Torch.nn.activation. Let's see where is the issue. I might have missed to import certain libraries. Let me just check. Vision transformer has no parameter. It is parameters. In that con 2D, I think the issue is D should be small letter if I'm not wrong. Yeah, that D should be small letter. That's why. C should be capital, D should be small. Okay, that was a minor issue. So what I was missing was I was missing parameters. That was one thing. And in JLU, I had forgotten to put this functional bracket. That was the other thing. Those were the only errors that I had. Okay, now we can define the training loop. So now in this training loop part, it's not specific to vision transformer. It's for any code. So I would rather open my own collab from earlier. because training loop is not fun. It's just manual effort. Okay, so here what we are doing is we are running over 5 epochs, initializing loss and total number of epochs and how many we have gotten correct into 0. And I just want to make sure that here we are using the same variable name, train loader, images, labels, optimizer, outputs. I think variable names are fine. If I just run this, it should hopefully work. Yeah, now it is running. Yeah, this code I'll share with you guys. I'll just directly put it in the chat or maybe in gist. So the training part, you can just pick the code from here because this is not vision transformer specific. This is for any ML model. You simply run, calculate how many you have gotten correct, and for each epoch you print the accuracy. So here there is nothing transformer specific. But do you see my accuracy? It is really, really bad. And this whole thing, I know why this happens. It's just due to one single mistake. The single mistake is in just one line of multi-head attention. So in multi-head attention, where is that? In self.multi-head attention, we have to say that the first dimension that it is expecting is the batch dimension. So here we have to say a parameter called batch first equal to true. So I'll change the parameter, I'll stop the training, and I'll train this one more. See, 10% is the worst model, right? 10 class classification, random. This is like random picking, worst model. But now with that batch first, let me run once again. I'll show you the accuracy. See, it's much better, 95, 92%. So that batch first, yeah. So batch first is the multi-layer perceptron expects the first dimension that you're inputting bunch of things, by the way. You're inputting batch, you're inputting a sequence of tokens, you are inputting for each token, there is an embedding dimension, and you have to explicitly say that to the multi-head attention, you have to explicitly say that the first dimension is batch. Otherwise, it will take first dimension to be the instead of 16, it will think that 64 is not the dimension of the batch. It will consider first dimension as the sequence dimension, which is I think the number of tokens or something. But here the first dimension 64 is actually batch. So we are already passing batch as the first dimension. So this batch first equal to true will take care of that. Actually, in the last lecture, which I posted regarding implementing multi-head attention without using for loops, I had very nicely done a calculation of how to convert your dimensionality such that you are looking at items per batch by taking some nice transpose operation. So I will share that video is actually available. It's called Implementing Multi-Head Attention in Practice or something like that was the title of the video. You can just check on our channel. Yeah, I'll share actually this code I can share directly with you because this is also common. It's not specific to vision transformer. It's for any deep learning. But you see the accuracy now, 95% in just 5 epochs. And now I have one more code. Yeah, accuracy increased because earlier I was not explicitly telling my multi-head attention that the first item it has to consider is the batch dimension, first dimension. So that was missing. So now I added batch first in the multi-head attention as the third parameter. Then the next thing is type error 2 tensor object is not iterable in training loop. I think if you share screenshot, it will be better. I think maybe some function bracket might be missing. Then what else? Yeah, just validation accuracy. This is again, you just pass it through validation dataset. And so you are using val loader instead of train loader, and you can just print the validation accuracy. So I don't want to go through this code because this is not vision transformer specific at all. This is for any neural network training. but validation accuracy is 96.21. We can just see one more thing. I'll paste the validation accuracy here, but please paste it. Please use these codes separately. I'm putting a giant space in between. Yes, I will share the vision transformer once. So this is vision transformer. The only thing in vision transformer, I did not change anything, but I had patch embedding. So these things are to be defined wherever trainable parameters are there. And wherever you have repeated execution over tokens, you put it in this defined forward function. Then last thing, which will be cool thing to see, is just randomly predicting on some random images from your validation data set. So here I am again calling val loader. I'm randomly picking 10 items and I'm just printing what the predictions are. So now these are the images, prediction and reality. It will mostly match. It's very difficult to find mistakes here because the accuracy is very good. But if we did not have this this loader, if we did not have this batch dimension first, this will not work. Now let me see what kind of errors you guys are keeping. All codes in. Yeah, I will share all the code for you guys pro members. But what other errors are you getting? I think this two tensor image might be criterion is not defined. Did anyone manage to get the code working? That's the, I guess, more important question. Okay. And what about accuracy? Is it 95-ish, 95, 96? Okay, excellent. Okay, now some issues are about cross entropy loss issue. Patch embedding is missing the required forward function. Okay, so forward function, this forward function is there in all the 4 classes. We have 4 classes. Okay, so forward function is there in all the 4 classes. Please don't miss that. And in this init constructor, it should precede with 2 underscores and it should have 2 underscores after. Please check that. And you have 2 init constructors, one for the class itself, one for the parent class. Transformer underscore blocks is not defined, probably because this part is not executed yet. Now let me share this part of the code also just to display some images. This will be fun. Yeah, just use this code also just to display some random images for your. Yeah, I will show my MLP head class. MLP head is actually the easiest class. It has just layer norm and one linear projection from 32 dimensions to 10 dimensions. One thing we can try here is this. What if I did not have multi-head attention? What if I had a single head attention? Then number of attention heads will be 1. What if I had 1 transformer block? Let's keep it that way. What if my token dimension is really bad, 3-dimensional token? And what if my MLP hidden dimension is only 6? And batch size, let's keep it that way. So now see, I'm having a very bad transformer architecture. Let's see what the accuracy is with this kind of a setup. I'm very curious. I have never tried this myself, but not great, but 27, 30. So 1/3 of the items hopefully should be correct in my validation data. Okay, and so this is the worst transformer architecture. Okay, and you can clearly see that it's making mistakes. So here prediction is 0, but true is 2. Prediction is 7. This is actually 4. Some of the easy ones are getting correct. And then here we can do some sort of ablation studies. We can just change some items here and see what works best. Let's say I don't want multi-head attention. I want single head attention. Token dimension I increase to 32. MLP dimension I increase to 64. Transformer blocks is 1. So let me see how this works now. So instead of 3-dimensional embedding, I have now 32-dimensional embedding. And I think this will be better. Yeah, you see, I don't even have a multi-head attention. I just have single head attention. It works kind of well. Not as good as early, but kind of well. All right. So this is good. I just want to see where it is making mistake. Yeah, only difficult images it's making mistake. Rest of them are kind of straightforward images. This is an easy image in my opinion, but see, the prediction is sensible, right? It's 4, it's getting classified as 9. Here 9 is getting classified as 4. Here 5 is getting classified as 6. It's making sensible mistakes, not like senseless mistakes. All right, so this is pretty much it. Now, we haven't explored yet. If we need only CLS token, why are we still calculating context vector for all patches? Because you can't calculate context vector just for one query, right? You calculate context vector, you calculate attention weight matrix. And using attention weight matrix, at the end of the day, we are only taking the context vector from the CLS token over here. Where is that? In the vision transformer class, we are only taking finally CLS token, this one. But for constructing the context vector for any token, you need the whole attention weights matrix. Because context vector is equal to attention weighted average of your value vectors, which means you need attention weights matrix to produce the attention weighted average of value. Not attention weighted average, attention weighted sum. Attention weighted sum of value vectors is a context vector. How is CLS token helping in classification? Could you give intuition? So in vision transformer paper, actually they tried, you can think of it this way. CLS token has some parameters that are learnable. Now, how does this learnable parameter values evolve? It evolves in such a way that if CLS token was not doing a proper classification, the error due to the learnable parameters inside the CLS token will be so high. So naturally, CLS, the weights and query key value weights inside the transformer head will adjust in such a way that the CLS token value will become so favorable towards classification. Now, if I were to try this for the very first time, and if BERT model was not existing, I don't know if I would have tried CLS token as the first thing. What I would have tried was, I would have tried using all the other tokens somehow, maybe creating a combined embedding using all the other tokens context vectors, and I might have tried classifying. In vision transformer paper, they mention it somewhere. Let's see, class. I think somewhere in the supplementary. Yeah, similar to BERT's class token, we prepend a learnable embedding, which serves as this, both during pre-training, but not here. I think it's somewhere later. Yeah. You see this? In order to stay as close as possible to the original transformer model, we made use of an additional class token, which is taken as image representation. So this class token contains the whole representation of the image. The output of this token is then transferred into a class prediction via a small multi-layer perceptron. This is the MLP classification head with tan-H nonlinearity in the single hidden layer. So here, I think they are mentioning about some other variant. Otherwise, it is JLU. This design is inherited from transformer model for text, and we use it throughout the main paper. An initial attempt, so read this sentence, an initial attempt at using only image patch embedding, so without CLS token, using global average pooling them, followed by a linear classifier similar to the MLP head, just like ResNet final feature map, performed very poorly. However, we found that this is neither due to extra token nor due to gap operation. So here, actually, they have done 2 experiments. So these 2 graphs are, this orange one and green one are without CLS token. And in one case, they saw better accuracy. In other case, they saw worse accuracy. But they're saying the accuracy difference was not due to CLS tokens presence or absence. It was due to the learning rate difference. So in my, can you see this PDF? I'll just share the, okay. So in my intuition, I don't have a great intuitive answer for why CLS token is 100% needed. I can understand what CLS token is doing. It is creating a representation, a vector representation of the whole image, just like how the last context vector in text is creating a vector representation of the whole sentence or whole context window. Same thing what CLS token is doing. But can we work without CLS token? In my mind, I don't see any issue, just like what is shown here. You can work without CLS token also. Can we pick any context vector from any random patch for classification? That probably not, because we don't know what each patch is attending to. Maybe some patch is attending more to some other patches. So just taking one single patch representation might not give you, but these guys are doing pooling, global average pooling from all the patches. So they are not just using one image patch embedding, all the patches. So if we implement something like this, where we somehow pool the values from all the patches, it might be better. Is this due to gap being not learnable? No, I mean, patch embeddings are anyway created as a result of learnable weights, right? So I don't know if that is the issue. And I don't see the issue, honestly, by the way. This green color graph with smaller learning rate is working better. Maybe the issue is that with smaller learning rate, it will be slower. You will need more computational time. But other than that, I don't see too many issues in trying in some cases without the CLS token. I think the main reason why they would have started CLS token is because BERT used CLS token and they were biased by the existence of BERT, maybe. But in any case, okay, wondering if there is a reason why not use MLP as at the last token. MLP at the last, we are using MLP at the last token. What do you mean MLP? What do you mean why not use MLP? We are using MLP, right? Last token is passed through MLP Classification Head. Oh, I see. Instead of CLS token, use it on the last token. Yeah. That reason is because, see, in text-based in GPT, last token contained the whole context because of the masking. Here, there is no masking. So we have no idea whether which of the patches have the highest context. We don't know that simply because we are not, this is not a left to right model. So models where prediction happens from left to right are called left to right models. BERT was a bidirectional model. The name itself was bidirectional encoder representation or something from transformers. So, so of course, we cannot pick any patch and use that. That much is clear. The only question is, can we create a combined embedding just using the patches and use that for classification instead of using classification token? That is a smart question. I think we can. I mean, that's what this graph is showing. I don't see much problem. And then when they say like accuracy is very bad, if we try that for our MNIST dataset, I don't think the accuracy will be that bad. I think it will be good. Can you please remove token and run? I mean, we can do that. We can try removing one of these tokens. Okay, that's a good experiment to run. So let me keep some of the transformer heads. Number of blocks is 4. Token dimension is 32. Channels is 1. Okay, all of this is fine. Now, let's say I did not have extra classification token. So I don't have number of patches plus 1. I only have number of patches. And CLS token is not needed, let's say. And this is not needed. And I'm concatenating. I don't need to concatenate CLS token. And let's say I'm passing some random token. Let's say I'm passing token number 1 to my MLP head, always for classification. I think this code, I don't see any logical issue right now. So now I don't have the classification token anymore. I'm just passing the representation from token number 1 into my final output. Let's see what the output looks like. Not bad at all, actually. Excellent output, in my opinion. So in this data set, it looks like we can take some random patches embedding also. It's not 96%, but not bad. Is CLS needed if we want to perform object detection? Very good question. So object detection, we will have to formulate it in a different way. We will see that when we are working on different models like detection transformer. So by default, the vanilla vision transformer is not good for object detection because training itself is in a different way, right? The labels are like the bounding rectangle coordinates and the class score. But see this very, very nice suggestion. Whoever suggested not using classification token, very good suggestion, excellent suggestion, in fact, because I'm getting very good accuracy. I don't know if I'm doing something wrong here. It's so good. But this data set is also very small. I'm pretty sure this will not work for bigger data set. We can also try generating a random number. So, and then pick that. Or maybe now that I have almost 100%, 96% accuracy, this is crazy, right? I'm picking randomly this token number 1. Where is that? Here. I'm randomly sending token number 1 to MLP Head. What if I send token number 4 to ML or 10 to MLP Head? Let's see if this works. Yeah, I mean, all tokens are having good amount of context. This is what it means. We could take mean also. X equal to mean of x comma, how do we take mean along the which dimension? Along not batch dimension, along dimension number 1, right? This is also working really well. Let me just take some random, just randomly take mean and send it to MLP Classification Head, and let's see if it works. Mean received invalid arguments. Okay, let's ask Gemini to fix the syntax. But this is cool. I really like this discussion, guys. The suggestion was really good. Suggestion to remove the classification token. I mean, really, really good. Yeah, now we are working with the mean. This is also working very well, surprisingly. I had not tried this, so thanks for suggesting to try this. Good to know. So this is just a normal mean. Okay, this is not even global average pooling. We can try global average pooling. Validation was also 96%. Last time it was 96. I'm sure this time also it won't be different. But let's stop after this. This was supposed to be a 2-hour workshop. It's become almost 3 hours, but I'm hoping that you guys are enjoying. But try this code, guys. I think this is very, very cool. We will meet again in the next week for Transformers for Vision series, guys. We'll be discussing. So there is one small plan change I have made. I initially wanted to talk about data efficient transformer and then detection transformer, and only before stable diffusion I wanted to discuss vision language model. But I have planned to change it to bring vision language model earlier, because that way you guys can directly understand VLM, because you have your understanding about transformers and vision transformers are fresh now. The code I'll be putting on the course dashboard, you can find it from there. But this is the validation accuracy, 96.1% without classification token. Thanks for suggesting this. This was very surprising. I thought the accuracy will be very bad, but it's good. But I'm sure this is also because dataset is too simple. For other datasets, I doubt we'll have such a good accuracy. In any case, we'll meet again next week. Try running the code. It's not that difficult to get it running. You guys can try this on some other either CFAR 10 dataset or some MNIST fashion dataset, or slightly more difficult, like some smaller versions of ImageNet or something like that. Just try that, okay? Next week, we'll be most likely working on vision language model. I'm yet to completely finalize whether it should be that or data efficient transformer, but most likely it will be vision transformer, vision language model. So thank you so much, everyone. Code I'm posting in the full code of mine. I'm posting in the course dashboard. See you next week. Hope you enjoyed it. Please, please try the code yourself if you have not managed to get it working. I hope you learned about vision transformer. I hope you understand about transformer in a much, much better way now. And I hope you understand the idea behind representing things using vectors, representing sentences using vectors, representing images using vectors. At the end of the day, it's all mathematics. If you really think about it, you're projecting it from a bigger space into a slightly smaller space. And then you are using that smaller space to produce output, either it's a classification or next word prediction, etc. So I hope you are slowly getting that intuition. By the end of the course, you will definitely have that. So let's meet next week. Thank you so much. Lunchtime. Bye. You can see my screen and hear me all right? Awesome. Thank you. So welcome to a new lecture. Today we'll be learning about data efficient image transformer. And first we will understand the intuition behind what was different about this model and what other models is a data efficient transformer most similar compared to. And in the second part of the lecture, we'll be building one from scratch. So we have already covered vision transformer. So the good thing about today's lecture is if you understand vision transformer and its coding properly, data efficient transformer, you will feel very much similar, because 95% of the things are very similar with respect to what vision transformer did. But data efficient transformer did something amazing, which made it significantly better in terms of training efficiency compared to vision transformer. One announcement that I have is we have migrated the website to a newer platform. And in this process, around maybe 5 to 10% of the students are not able to get access to their existing courses in their dashboard. So what you can do is you can just drop an email. I'm just putting it in the chat. Just drop an email here, just mentioning about the course name and that you are not able to have access. We'll fix it. All right. So now let's look at data efficient transformer. This paper was published in around 2021, and it was from Facebook AI Research. So the paper title is Training Data Efficient Image Transformers. So this DEIT is Data Efficient Image Transformer. So it is for images. It is making use of transformer architecture, and it has a few more things. So the other main idea that was introduced in the paper is distillation. You may have heard of the concept of teacher-student model. So we will look at it in detail today. What exactly is a teacher-student model in deep learning, and how that idea is also known by the term knowledge distillation, and how this knowledge distillation is utilized in data efficient transformer for making it significantly better compared to vision transformer. So if you think about vision transformer, the main problem with vision transformer, number one problem was that it required huge amount of data. The data set that was used for training the base vision transformer model was a 300 million image data set called JFT data set, which you will see in their paper. But this JFT data set mentioned in the paper, it's not a publicly available data set. It's Google's own data set. So this was a problem. Second problem was that the number of parameters in their state-of-the-art model in vision transformer, if I'm not wrong, it was around 600 million. So it was not a very small model, 600 million parameters, around 300 million images in the training data. And it also required multiple days of training using multiple GPUs. So computationally, it was very expensive. But the vision transformer, which was trained using all of these, resulted in SOTA, state of the art, at that moment. And it actually overtook what convolutional neural networks managed to accomplish up until that point. So you know that 2012 to, let's say, roughly 2020 or around 2021, those were the years when CNNs completely dominated deep learning or computer vision. But then around 2020, when Vision Transformer was introduced, transformer architecture started becoming popular. So the reason why we are discussing about data efficient transformer is that it is the next logical succession, since we already know how vision transformers work. So CNNs had something good going on for them, mainly called as inductive biases. But now we have models with billions. So yeah. So in the context of images and in the context of the speed with which you can operate, this is not a language model. This is a image-based model. So 600 million model compared to, let's say, data efficient transformer with only 84 million parameters, it is large. Today, there are even bigger models, but the whole idea here is that how do you train a reasonably good model with low number of parameters, with less input data, basically small training data size, and still achieve something close to state of the art. So this was the problem that researchers were trying to solve. So in CNNs, they have something called as inductive bias. That most two famous inductive biases are locality, and second is translation invariance or translational equivariance. There is a very nice GIF which I want to show you. If you search, and if you go to Google Images, I'm not sure if it is popping up right away. Let's search inductive bias. I'm not sure if it is showing up. Let me check if I can find it on my own Miro board. It was a very, very nice GIF, which would have been nice to show you. Anyways, we'll check it. It was showing up until yesterday. But basically, translational invariance is the idea that it doesn't matter where spatially in the two-dimensional space where your feature is located in an image, your CNN will capture it. So if you have a big image and let's say you have a CNN which can recognize circular features, it doesn't matter where the circular feature is located, it will capture it because CNN operation, the convolution operation covers the entire XY dimension as it goes from top left to bottom right. So the bias, the reason why this is called inductive bias is that inherently the operation of convolution is making some assumptions. It is assuming that features are locally present and features irrespective of in which locality it is present, those features can be detected using certain type of filter. But we have discussed this in probably the beginning part of this course that this is not necessarily always a good thing. For example, look at this example. Here, if you are in a self-driving car, and let's say there is a person who is crossing the road, despite it being a green signal for the cars, the pixel where the person is present, maybe the person is here. So person is over here and red signal pixels are over here. So the actual physical distance between the pixels where the person is and the pixels where green signal is shown, they are actually far apart. But still, in this context of the image, those two sets of pixels are highly correlated. So there has to be some sort of global attention mechanism, a mechanism where irrespective of the pixel distance in the image, you should be able to make meaningful things out of that full context. And only then, let's say in this case, you will have a self-driving car which may work based on certain architecture. It should not run over the person just because you have a green signal. So this is one reason why people were so interested in bringing transformer architecture to images, because in transformer, it doesn't matter what is the length of the sentence that you're inputting as long as it is within your context window. One famous example that we discussed in the early part of this course is if you have a sentence that looks like the teacher who was teaching a difficult concept to the students, I'm not writing the whole thing, smiled. So here the smiled action is performed by the teacher, not by the students, but the words, these two tokens are far apart. They are one is at the right at the beginning, one is at the end, but still the attention scores between those two tokens should be high enough for teaching your model that actually teacher and smiled are very closely related to each other. So same concept applies to images. When you convert your images into patches and patches into tokens, it doesn't matter the physical separation between the patches. You can learn relationships between the far apart patches. So this was the reason why people were pushing towards transformer-based architecture. But the problem was that in Vision Transformer, as I mentioned, you need huge data set and you need long training schedule. Simply means you need more number of GPU compute. So this was the main issue. And there is actually one sentence in the DEIT paper, which they have borrowed directly from the Vision Transformer paper. Look at this sentence. The paper concludes, transformers do not generalize well when trained on insufficient amounts of data. So this sentence in double quotes is taken directly from the Vision Transformer paper itself. So the paper itself says you can't have a good generalizable transformer model unless you have a huge training data set. So this was the problem that they were trying to solve. And this JFT 300 million is the data set on which Vision Transformer was trained. And it had 300 million images. And the size is also mentioned in, I think, one of the last tables of this paper. This is actually a very nicely written paper. I think if you try reading it, in fact, I am putting out a video on reading this paper sometime later. But if you read this paper yourself, I think 80% of the things you will understand in the first attempt itself. So how does patches solve inductive bias? Don't you need movement? Yes. So patches do not solve inductive bias. So inductive bias is not necessarily a bad thing. Inductive bias is a good thing because that way, even if features are present in different portions of the image, it can be taken into consideration. Inductive bias is a bad thing because of its locality. It's not a bad thing because of its let's say translational invariance. So inductive bias is some inherent assumptions present in the convolution operation, like the fact that features are present locally. And that's the reason why you could simply use a 3x3 filter on a 224x224 image, because this 3x3 filter will capture local textures, local edges, etc. And those extracted features are enough to represent the data that is present in the image. So that is one bias. Another bias is it doesn't matter where those features are present in the image, whether it is top left, bottom right, it doesn't matter. You will capture those features. So this was considered to be a good thing for a very, very long time. The only time when this was an issue was that convolutional neural networks could not capture long range dependency. It could not capture the fact that if you have a patch of pixel at the bottom right corner and another patch at the top left corner, and if they are having very high correlation, it's difficult to capture because the filters themselves are very local. It's constrained to simply 9 pixels. Yes, with multiple convolution blocks in series, you can increase the effective receptive field, but still CNNs struggle with the global context. And if you increase the effective receptive field by adding more layers, as you saw from the nano VLM lecture, the number of learnable parameters simply blow up in the later layers. So yes, CNN was the state of the art until certain point. And if you look at the comparison between CNN and data efficient image transformer, there is very high similarity, but the global context is still missing. Long range dependency is still missing. In one of the next lectures, when we discuss Swin transformer, which is shifted window transformer, you will understand how you can bring convolution operation along with the long range dependency capturing effect of transformer. So at that point, all the dots will be connected for you. But here, let's focus on just the transformer part, where we will try to figure out how to have smaller data set unlike 300 million images, can we just use a data set with 1 million image or 1.2 million image? So in DEIT, they said their value proposition is that they will only use one training data set, which is the ImageNet 1K. It's called ImageNet 1K because the number of classes is just 1000 classes. So it will be like a 1000 class classification problem. Total number of images is roughly 1.2 million, which you will split into train and validation. Now, the goal was, how can you meaningfully train a transformer like a vision transformer on such a relatively small data set and still get some results, some classification accuracy, which is comparable to state of the art. So this was the problem that Facebook was trying to solve at that time. So in DEIT, this paper, by the way, has around 10,000 citations, which is very respectable considering that it's only been around 4 years or slightly less than that. And so this is just the snapshot of the abstract part of the paper. I have just pasted it here so that you will recognize when you later want to read the paper. And this is the part which I mentioned where they were directly quoting from. This was interesting because vision transformer paper, they concede that, yes, for small amount of data, it does not work. Vision transformer model does not work. So what these guys did was they introduced the idea of teacher-student model in the context of teaching a transformer. So let me first show you a diagram, which before I go through this text to make you understand the idea of what is a teacher-student model. So this is also associated with this term called knowledge distillation or KD. And you might have heard of the term knowledge distillation in the context of large language models also. Most of the models have their distilled version available. So the idea is this: you have two neural networks. First one is a large neural network. Second one is a small neural network. Now, large neural network might be an already pre-trained one. So this is already trained. You are not going to train this anymore. But your goal is, how can you teach a small neural network with less amount of training data such that it can be almost as good as the large neural network? So in effect, you are trying to compress your teacher, or you're trying to compress the knowledge that your teacher has into a student model. So what is done is the following. You will have a training data set. Consider that the training data set is ImageNet 1K. So this is a significantly smaller training data set. Instead of 300 million data points, you just have 1 million data points. Now, what you do is you will pass the training data set. So let's say it's an image of a cat. It will be passed through the large neural network, which is the teacher model, and teacher will make its prediction. So let's say if it is a 3-class classification instead of 1000-class classification, you will get softmax scores from the teacher. So if the classification is, let's say, cat versus dog versus background, BG, your scores might look like 0.8, 0.1, 0.1, something like this. Now, these predictions made by the teacher, these are called soft labels. Why? Because if you were to make it into a hard label, you will say, teacher is saying with 80% certainty that it's a cat. And because of that, we will say it's a cat. But that will be hard label. Hard labeling would look like something like 100. So if we were to convert this using argmax into this format, like one hot format, it will be like a hard labeling. But this hard labeling, now you just tell me which among this has more information, B or A? Which one has more information present in it? Obviously, A has more information present in it. The reason is it tells you two things. One is, of course, it tells you that teacher thinks that this is a cat with high probability. But it also tells you that teacher thinks in this image, there is a 10% likelihood for finding a dog. There is a 10% likelihood that it's just a background. So these numbers actually give you slightly bit more information than the hard-coded or hard labels. So what is done is, let's say you denote the prediction made by the teacher by YT cap. Now, the small neural network, which will be randomly initialized. So teachers' weights and biases will be, of course, pre-trained weights and biases. So teacher, you will assume that it's already trained on a much bigger data set, right? Now your goal is, how can you have a student model which can learn a bunch of things from the teacher, not necessarily from the ground truth data. So now the small neural network will also make a prediction on the exact same image. Let's say it is the same cat versus dog versus background image. Now student will have its own predictions. We can call this as Y student cap. Now, usually what do? You construct a cross entropy loss. So usually we'll say loss due to or loss cross entropy equal to minus sigma I Y student times log Y student cap for the ith class. This is the cross entropy loss, where Y student I is the ground. Actually, here I don't need the S. It's just the ground truth. So I just need to say YI. So YI is the ground truth for the current image for the current class. So here YI would look like 1, 0, 0. So if I equal to 0, Y will be 1. If I equal to 1, Y will be 0. If I equal to 2, Y will be 0. And log of Y cap will be whatever prediction student is making. And let's say the prediction made by student is 0.7, 0.15, 0.15. Then you can simply construct a simple cross entropy loss. And this is what you normally do in the absence of teacher. But now in the presence of teacher, what you do is you don't just consider the ground truth, which is the actual label of your image. You also consider the predictions made by the teacher. So these predictions are considered to construct the loss function. We will see in a moment what exactly does the loss function look like. But just keep this in your mind that to construct the loss, you are considering, in this case, three things. One is the actual ground truth. One is the soft labels or hard labels by the teacher. You can do both, but basically the predictions made by the teacher, that is considered, and predictions made by the student, that is also considered. Now, what is this loss used for? Do we use this loss function to modify the teacher? Yes or no? We don't, because we are not training the teacher here. Teacher is anyway a big model. If our goal was to train the teacher, it would take a long computational resources, long time for doing the training. This loss is only used for training the student. So we perform the back propagation where the gradient of these losses with respect to weights and biases, basically parameters of the student, is calculated. And then based on that, we modify the parameters of the student network alone. Teacher will remain untouched. And if you do this, essentially what will happen is now student is learning two things. One is student is learning that, hey, I have to make predictions that are, not deviating too much from the ground truth. At the same time, student is also learning that I have to make predictions that are not deviating too much from what my teacher thinks is the ground truth. So yes, and we can do this just with soft label without the ground truth. So usually the way it is done is you will have a parameter. So total loss, let's say global loss, is something like alpha times cross entropy loss plus 1 minus alpha times. You will construct another loss. So let's say this is cross entropy loss between student and ground truth. And here you can construct another cross entropy loss between student and teacher's prediction. Let's call it as TP. So you will consider both of these losses, and then you will take a weighted sum of that using a parameter called alpha. If the value of alpha is 0, you are completely neglecting the ground truth. If the value of alpha is 0.5, you are considering the loss happening due to deviation from the ground truth and deviation from teacher's prediction equally. And if alpha is equal to 1, you don't consider the teacher's predictions at all. Okay, now there are a few questions. If proprietary images are present in our or teacher-student training, does not work right even if we have good teacher model. So if I understand the question correctly, if we are a company and we have a bunch of proprietary images and we have to train a student model, and for teacher, we pick some already trained model, and does it work very well or not, right? I assume that's the question you're asking, Manoj. It will still work to some extent as long as the baseline training data set on which teacher model is trained is similar to the kind of models that you have. If the kind of models you have is, let's say, synthetic data set, some non-naturally occurring images, right? Maybe it can be some, let's say, satellite images, which usually you don't have in training data set. But the pre-trained models that you have available on internet are mostly trained on ImageNet data, and ImageNet is mostly naturally occurring kind of images. So in such cases, just directly taking a pre-trained teacher may not be enough. You may have to do a little bit of fine-tuning of the teacher. Small amount of fine-tuning might be necessary. But otherwise, if the nature of images are very similar for your teacher and the student, then you will not need any fine-tuning for teacher. You can use pre-trained image as such. Then what are soft label? Yeah, soft label is basically the direct logits, actually softmax coming out of the teacher. Softmax or logits both. But it won't be like a one-hot encoding format. Like it won't be like 100, 010, etc. Is alpha learnable? Typically, alpha is not learnable. It's more like a, I would say, hyperparameter. I mean, yes, you can call it as learnable, but it's not a parameter. If anything, you can call it as a hyperparameter. So yes, you may try to find better and better alpha values for figuring out how much weightage to put for teacher, error due to teacher, how much weight to put for error due to ground truth. But in many cases, I have seen alpha values just 0.5. In today's lecture also, we'll initially use 0.5, but I'll just show you how to change the value of alpha and get varying validation accuracy. Okay, if we have hard labels, what are the consequences? Excellent question. I'll show you one. So this is one example that is mentioned in the original paper. This is not a difference between hard label and soft label. It's a difference between using labels from the ground truth versus using labels from the teacher. Let's say I have an image like this. And this image is a 3-class classification. So if a cat is present in the image, it will be cat. If a dog is present in the image, it will be classified as a dog. If nothing is present, it will be background BG. Now let's say I have a cat here in just the bottom left corner. Now you know that image augmentations are very usually routinely done for your training data set, so that by cropping, by randomly flipping, random rotation, etc., you can create more data points so that your training can be more efficient. More efficient meaning you get a bit more diversity. Now consider the fact that you are very likely in this case to crop like this. Okay, now your data point is this. What should be your prediction looking like? Should it look like 1, 0, 0? Or should it look like 0, 0, 1? The prediction. So the question is, this is your image. This red color thing is your image. In your image, there is a cat, but you did random cropping and your cropped window happened to be this. If that is the case, your prediction should look something like 0, 0, 1, correct? But let's say, now what are you comparing your predictions against? You are comparing your predictions against ground truth, let's say, normally. Ground truth is what? Ground truth is this is a cat, because there is a cat in the image. So ground truth is 1, 0, 0. Okay. Now the problem is, if the teacher is absent in this case, let's say a teacher model is not there, your student is just compared against the ground truth for this augmented data set also, because just data augmentation is not going to change your labels. Labels will remain the same. So ground truth for this image as well as for this augmented image, both are the same. But now if you don't have a teacher, for this input data point, your student will be forced to make a prediction saying it's a cat, although there is no cat inside this image, simply because the ground truth corresponding to this augmented data is 1, 0, 0. But now imagine the case where you have a teacher present. Teacher is anyway not part of training. Teacher is already pre-trained. So now if I was inputting this into a teacher, this augmented data into a teacher, and if the teacher is a very well pre-trained model, what kind of prediction will teacher more likely make? Will it make a prediction like 0.8, 0.1, 0.1? Or will it make a prediction like 0.1, 0.1, 0.8? First case or second case? Teacher will most likely make this prediction, because you are just inputting an augmented data point, and teacher is not part of training. So teacher is not looking at label or anything. Teacher is simply making a prediction based on its already pre-trained weights. So teacher is more likely to make a prediction like this. And now consider two cases. In one case, you train your student just by looking at the ground truth. In another case, you train your student just by looking at the teacher's prediction. You are better off by somehow considering teacher's prediction also into account. I mean, this is an extreme case that I'm saying, but in this particular case, it's very clear that you should not just be considering the ground truth, right? So on an average, you have to consider the ground truth as well as you have to consider the teacher's predictions. Where this, if you consider this cropping based augmentation as a special case. Now there are questions like, then what is the need for ground truth? Only teacher model should suffice then. Great question. The problem is teacher is not perfect. Teacher, you have no guarantee that for this data set, teacher has 99% accuracy. Teacher may have false positives, right? So teacher's accuracy may be 90%. You don't know. So as long as you have a good pre-trained model as the teacher, you assume that, okay, teacher has learned a bunch of things and it will take care of cases where augmentation will produce such problematic cases. And ground truth is your actual truth, because you also want your model to not deviate too much from your actual truth. So that's the reason why you will pick the loss function by considering deviation from the teacher and deviation from the ground truth equally or at the same time. All right. So that is the basic idea behind, is it possible to train SLM this way and bypass RLHF? Okay, great question. Actually, it is done. If you look at the DeepSeek R1 paper, if I remember correctly, they had a knowledge distillation also, which they did from a bigger model. So distillation is basically an idea where, okay, and before I come to that, just think about the good thing about this. Now, my teacher can be a CNN, right? Student can be a vision transformer. So although vision transformer does not have any advantages of the convolutions, translational invariance or anything like that, because vision transformer does not look at two-dimensional data. It simply considers patches, and only place where some positional or spatial information is coming is in the position embedding. Now, vision transformer, how can a vision transformer act like a CNN? Because we know that CNN is very good. What we can do is consider that this small neural network is a vision transformer, and consider that this teacher is like an already pre-trained CNN. We'll come to the loss function, how it looks like. But in principle, if this can be accomplished, then we can train vision transformer to make predictions similar to CNN. The way there is a great question. How does this differ from transfer learning? In transfer learning, the way it works is, the simplest way to think about transfer learning is, we have a model which is pre-trained. Okay. And let's say this is pre-trained on some public data set. Now I want to use the same model architecture. Let's say this is ResNet 50. And now I have some private data. Okay. And on this private data, I want to train a ResNet. Same model, ResNet 50. I want to train ResNet 50 here also. Now, in this case, transfer learning simply means you don't start from random weights. So instead of going with random initialization of the weights, you initialize the weights from the final stopping point of this pre-trained neural network. So in transfer learning, essentially what you're doing is you are transferring the weights which are non-random. Why is it non-random? Because these weights were the result of a public data set based pre-training. And then you transfer those weights and further you can train on top of it. So almost like fine tuning. And this is the idea of transfer learning. In this case, we are not touching the weights of this large neural network at all. We don't care about the weights of this teacher. We don't know about it. I mean, we may know, but we don't have to know. We simply have to know what prediction the teacher is making, right? We only know and we only care about the weights and biases of this small neural network. Now, teacher can be a big CNN model with large number of parameters, or it can be a 600 million parameter vision transformer itself. It doesn't matter as long as the teacher is well trained on a good data set. So it's completely different from transfer learning. In this, wouldn't we inherit all the biases the teacher model has, and how would we deal with any data drift? Yes. So this would inherit. Okay. We should not say that this will definitely inherit bias. We can only say that when we are training a model to make similar predictions as that of CNN, it is likely that some biases may be inherited. In fact, there is one paragraph in the paper over here. Just have a look at this paragraph. Our distill model is more correlated to convolutional neural network, CNN, than with a transformer learned from scratch. As to be expected, the classifier associated with distillation embedding. So forget about this. This I have not explained to you yet. But basically, there is a distillation embedding is closer to a connet, and there is another class embedding, which we have discussed in the vision transformer. I'm yet to come to this. But basically, here they are trying to answer the question, how do we know whether, does it inherit inductive bias that would facilitate the training, or does it not inherit inductive bias? And it's difficult to answer this actually, because the true definition of inductive bias is, are you inherently assuming a two-dimensional structure to your data set? Are you inherently assuming that if some features are present at location A of the data set, and even if it's present in location B, whether those features will be captured or not? Such inherent assumptions are not there if you are simply using a transformer-based architecture. The only thing that is inherently present is, since you have a unmasked self-attention, you can construct global long-term dependency. That is the only thing that transformer guarantees. Nothing else. There is no other guarantee. But since we are trying to train a vision transformer using maybe a CNN teacher, yes, we can think of, okay, maybe the vision transformer may act like a CNN. So they have a table in the next page. I don't want you to get scared by looking at the table, but look at there are 6 rows and 6 columns, and it's perfectly symmetric. So basically, they are comparing how much does the vision transformer deviate from a convolutional neural network, or how much does a data efficient image transformer deviate from a convolutional neural network. So if you are comparing predictions, I'll come to this table actually a bit later, because I want to talk about one important token. Otherwise, this table won't make too much sense. But just remind me once if I don't remember to come back to this table. And this is to answer the question of, how do we know whether inductive biases from CNN is coming to this student model or not, right? We need to answer that. So let me first show you the architecture, and then I will go through the text. What is the data efficient image transformer architecture? The simple architecture is this. You have one additional token called distillation token. But if you only had these many, what would that be? All the patches plus class token. What is this? This is simply vision transformer. Here you have one more additional token called distillation token. And at the output, the context vectors corresponding to 2 tokens are considered. Context vector corresponding to the classification token or class token, and context vector corresponding to the distillation token. Now, this context vector will be, both of these context vectors will be used for constructing losses. So first is the cross entropy loss. So now let's talk about a little bit of mathematical detail of how to construct the loss. Once we discuss all of this, we can come back to more qualitative arguments. So let's say my class token prediction is something like the CLS token predicts something like PCLS is equal to, if it is cat versus dog versus background, let's say it is P1, P2, P3, where this is like a probability distribution. Now the cross entropy loss and the ground truth will be yi. So in this case, if it's a cat, the ground truth will look like 1, y equal to y1, y2, y3, where the value of this will be 1, 0, 0, the ground truth. So now what is the loss due to cross entropy, which we calculate for the classification token? It will be simply minus sigma I equal to 1 to 3 yi log p CLS token I. So it will be minus, this will finally boil down to minus 1 times log P1. Basically, this will be the loss due to cross entropy loss. This is the, and what is this? We are comparing how far the CLS tokens based prediction is compared to the actual ground truth. In the vision transformer, we were using CLS token for predicting what is the image, right? We were using it for classification. Let me open the vision transformer paper just to have the figure in front of me. So this is the vision transformer architecture that we had discussed. So first we do patching. So images are converted into patches of size 16 by 16. In this example, it is as if there are 9 patches total. Each patch will be converted into vectors. And if the vector embedding space is of 768 dimensions, each patch will be converted into a 768 dimensional vector. And along with these patches, one CLS token is prepended. So this is the 0th item is the CLS token. And for each token, what is this 0, 1, 2, 3, etc.? What are these numbers signifying? The 0, 1, 2, 3, it's the position embedding, because you need to add position information somehow. And in vision transformer, they had tried both learnable position embedding as well as a position embedding based on 2D spatial positioning. And they saw that both are equally effective. So they went ahead with learnable position embedding. And that's what we also did when we implemented vision transformer from scratch. And then once you have all these 10 tokens, these tokens are passed into transformer encoder blocks. And then from the final output, you will have a set of 10 context vectors, right? Every token will have one corresponding context vector. So here at the end, there will be 10 context vectors. But you don't care about all the 10 context vectors. You only care about one context vector, the context vector corresponding to the CLS token. Then that is passed through a multi-layer perceptron classification head, which will project that vector into a hidden space of larger dimension. And then from there, it will be projected into, let's say it's a 10 class classification, it will be projected into a 10-dimensional vector. So in the example of MNIST dataset that we used, the final layer was of 10 nodes. Now here, the architecture is exactly same. So I have made a different diagram to explain this architectures in a slightly better way over here. So this is, let's just follow the path of this token. So you have input image. Input image is converted into patches. So patching is done using dividing it into a fixed size. So each patch will be 16 by 16 or whatever the size is. So if image size is img underscore size, and if patch size is p, total number of patches will be img size divided by p, the whole square. You will have these many patches along the width and those many patches along the height. So totally in the image, you will have image size by p multiplied by image size by p, that many patches. Then you have prepending of the CLS token. So this is the embedding, initial embedding of the CLS token. This is the position embedding. And when you add these two, you get the final token embedding for the CLS token. Like that you have for all the tokens. And then at the end, actually this distillation token, you can add pretty much anywhere. I don't think there is anything that preventing you from adding the distillation token as the token number 1 or token number 2. But here in the original paper, they added it as the last token. And then you will have several transformer blocks depending on how deep your transformer neural network is. In today's lecture, when we code, we can start with just a four blocks or something, and then we can play with it. And then you will have a classification head, which is only meant for CLS token. So here what comes is the context vector of the CLS token. Here what comes is the context vector of the distillation token. So this distillation token is for knowledge distillation. And then using the classification head, you will get what are the predictions made by your classification class token. So if it's a 10 class classification, you will have 10 logits. Similarly, for distillation token also, you will have 10 logits. Now, what is done is the predictions made by the, now you have to consider 4 things here to construct your final loss. One is predictions made by the CLS token, predictions made by the distillation token, predictions made by your teacher. Now, what is the teacher here? Teacher will be a CNN into which the same image will be input. And then that CNN will make a prediction. And you can take either the hard labels or soft labels. So if it is hard labels, it will look like one hot. If it is soft label, it will look like logits. So then you will consider these 4 things to construct your final loss: the predictions or logics from the CLS token, logics from distillation, then predictions made by your teacher, and the ground truth. So these 4 things now you have to consider to construct the final loss function. And this loss function is used only to train your vision transformer. This loss is not used to train your teacher. Teacher is untouched. You don't train the teacher, right? Okay, now let me look at some questions. Why we use 2 tokens, CLS and distillation? Take same CLS. Okay, excellent question. In fact, in the paper, they had done the exact same thing. Why do we need distillation token at all? Why not just use like basically two CLS tokens and just take the predictions from either one of the CLS tokens, something like that. So what they have done in the paper is, I think they might have answered a question from a reviewer looking at what they have done. So let me go back to that. Okay, so this is that section. Interestingly, we observed that the learned class and distillation tokens converge towards different vectors. So ideally, if CLS token and distillation token are learning the same thing, they should eventually converge towards the same vector. And how do we know the convergence? We will know the convergence by taking the dot product or cosine similarity. So the average cosine similarity between the distillation token and CLS token is 0.06. So here when they say 0.06, the average is considering different images. So you will input one image, you will see what happens to CLS token, and you will see what happens to distillation token, calculate the cosine similarity, do that for many different images, and the average cosine similarity is only 0.06. As the class and distillation embeddings are computed at each layer, they gradually become more similar through the network. So from going from the transformer layer number 1 till layer number 4 or 5 or 6 or whatever is the last layer, the cosine similarity between distillation tokens gradually increase. And in this model, for their base model, the last layer had high cosine similarity, 0.93, between distillation token and CLS token. But what they're saying is this is, but still it is lower than 1. And this kind of similarity, this kind of cosine similarity between CLS tokens context vector and distillation tokens context vector is expected since they aim at producing targets that are similar but not identical. And why do we say that? Because CLS token is aiming to produce targets similar to which one? Ground truth or teachers' labels? Ground truth. CLS token is aiming to produce something similar to ground truth. Distillation token is aiming to produce something similar to teacher. Then one thing that they did is they did an experiment. We verified that our distillation token adds something to the model compared to simply adding an additional class token. So this is what you had mentioned in the chat. Like, why do we need CLS and distillation? Why not take 2 CLS tokens? Then, so we verified our distillation token adds something to the model compared to simply adding an additional CLS token associated with the same target label. So what is the same? What does it mean by same target label? You have 2 CLS tokens. Both CLS tokens are now trying to learn ground truth. So instead of a pseudo teacher pseudo label, we experimented with a transformer with 2 class tokens. Even if we initialize them randomly and independently, during training, they converge towards the exact same vector with 0.999 cosine similarity. So it doesn't matter if we have 2 separate tokens. And if we are training both of them towards the same target, then it achieves nothing. Then because both context vectors will eventually converge to the same context vector. But here, the main key difference is that distillation token is not training on the ground truth. It is training on the teacher's labels, teacher's predictions. So that is the whole difference that is coming. Now you may have a question, which among these tokens, let's say I train my student model, which among these tokens will I use for classification? What do you think? Will I use CLS token or will I use distillation token for my predictions during validation? So in the paper, they have tried all the 3. They tried just with CLS token. We can also do that. They tried with CLS token alone. They tried with just distillation token. They also tried by taking a combination of both. And for their experiments, they found, I think if I remember correctly, they have a table. The combination of both worked better. Yeah, so this one was, so data efficient image transformer. This weird symbol they are calling it as alembic notation, but this denotes that they have the distillation process in the model. So here they are considering both class and distillation token. And interestingly, so this was the most counterintuitive part for me from the paper. For them, hard distillation of the teacher worked better than soft distillation. Then I was reading, why is that the case? Why do we, because in my understanding, if you really want to know what the teacher is thinking, you need to take the soft labels like 0.8, 0.1, 0.1. Instead of taking 1, 0, 0, because 1, 0, 0 is not giving you information about the teacher's thought process. It's just giving you the final answer. So my intuitive thinking was that we need soft labels to get best output. So if somebody was to ask me what would I try, by default I would have said, okay, I will use CLS token plus distillation token for prediction, but I will use soft labels. I will not use hard labels. But here they found that hard labels work best. And what I understood is that the reason why hard label is working is, if we were using same type of models, let's say vision transformer for teacher and vision transformer for student, so a larger vision transformer for teacher and small vision transformer for student, if that was the case, soft labeling would have worked because both models are now looking at features in a similar way. But here in this paper, they used a model called, I think, EfficientNet or ResNet. So this was the model that they used, RegNet with 16 gigaflops computing. So this 16 gigaflop is simply for processing one image, how many floating point operations do you need? So basically, if it is say 16 gigaflops, it simply means it's a bigger model compared to this one. But they are using CNN as their teacher. So because teacher is a CNN and student is a vision transformer, the way in which they are looking at the features are completely different, because CNN is looking at the features from the convolutions point of view. Transformer is looking at the features from an attention weights point of view. And because of that, and that's it's a very qualitative reasoning. I still don't know how to mathematically justify it, but qualitatively it says, because of this reason, hard distillation works better than soft distillation. Okay, does the hard label use cross entropy loss? Maybe the dichotomy of 1, 0 is increasing the error. Yes, it does use cross entropy loss. So we'll come to that. At that time, we can play with the numbers a little bit. Anyways, okay, but why distill token passed in student model? So distill token is nothing is passed into the student. Distill token is not passed into the student model. Distill token is initialized in the student model. So when I read the paper for the first time, I got a little bit confused that I thought the distillation token was initialized using the output of CNN. I thought some feature vector was used to initialize distill token, but that is not the case. If that was the case, then it's like a bit cheating, because then CNN is somehow coming in your architecture. But distill token is initialized just like how your CLS token is initialized. Starting point is random. So because of that, you are not giving any unfair advantage to your network. The only part where teacher is coming into picture is in constructing the loss. Your distill tokens predictions are just compared against your teacher's prediction. That's the only place where indirectly CNN is influencing the vision transformer architecture. So this distill token is simply, please don't get confused, because you may think like this is cheating. Why? Because you may think like, oh, I have a CNN, I extract features using this CNN, and using those extracted features, I construct a distill token. And then I have a CLS token and distill token. And both of these are now passed into a vision transformer model. And then I have, again, CLS tokens context vector and distill tokens context vector. Let me just delete this. And then this is compared against the ground truth. And this is compared against the teacher's prediction. So this is what I initially thought what they are doing. But this thing is not there. Teacher is not influencing the distill token directly at all, right? So please understand that there is no, then I thought, oh, but isn't this obvious? If CNN is influencing distill token, then isn't it obvious that this will be a good model? Because you are directly taking the features from CNN. But here you are not taking features from CNN. You are taking only the predictions from the CNN. All right. Okay, now let us look at the loss function, which is probably the most important thing here. So I have written some terms here, so I will go through it one by one. So now let's look at the loss, cross entropy loss. So LCE. This will be minus, this is the easiest one, I equal to 1 to C. If you have C classes, yi, where yi is the ground truth, log pi, where pi is the prediction made by the CLS token. So now this is the cross entropy loss due to disagreement between predictions made by CLS token and the actual ground truth. Now we need one more loss due to, let's say, student teacher, and this is called as KL divergence. It's very interesting the way it is calculated. So the formula is over here. I will give you the intuition behind the formula. So the loss due to disagreement between teacher and distillation token is given by this formula, T square. Please don't get worried by looking at this. I will explain every single term. But the formula is T square multiplied by sigma I equal to 1 to C. So sigma I equal to 1 to C is you are summing over different classes. So if it's a 10 class classification, the sigma will go from 1 to 10. Then this is prediction for the ith class, probability prediction for the ith class made by the teacher. Then log of PTI is probability prediction made by the teacher for the ith class. And here again, in the denominator, you have probability for the student for the ith class. Now I'll explain what this PT is. PT is simply the probability which you calculate from softmax. So let's say I have a teacher, I have distill, then I have CLS, and I have ground truth. And say I have 3 classes, cat, dog, and background. And let's say it is a cat. So ground truth is 1, 0, 0. Now, let's say my teacher, which is a CNN, is making a prediction like 0.8, 0.1, 0.1. And let's say my CLS token is making a prediction that looks like 0.9 or maybe 0.8, 0.1, 0.1. And distillation token is making a prediction like 0.9, 0, and 0.1. Now, LCE, which is the cross entropy loss, and this is for the loss between CLS and ground truth. For that, you compare these two. So finally, what will be the loss? If you can just give me one number, minus log. What should it be inside? Minus log 0.8, because it is minus sigma log minus yi sigma, sorry, minus sigma yi log pi. So yi is 0 for this, yi is 0 for this. So only one term will survive. So it will be minus 1 times log of 0.8, which is equal to minus log 0.8. Why do we have negative sign? Because probabilities are between 0 and 1. So logarithm of a number less than 1 will be negative. And to convert it into a positive loss value, that's why you have a negative sign here. So this will be simply the cross entropy loss. But this part is easy. Now let's come to the difficult part. Difficult part is how do you construct the loss between these two? Now tell me one very, I would say, bold thing your student is doing. So this is student. This distillation token is now the student, and this is teacher. Do you think this is a good thing? This 0. Student is saying that this item is 0. Is this a good thing or is this a bad thing? Why is it not a good thing? If it's a good thing, why is it a good thing? Not from a mathematical perspective. I want it more from a, I would say, qualitative or logical perspective. The reason why this is not a good thing is teacher is first of all not at all sure whether, here student is saying with 100% certainty that it is not a dog, right? That is what student is saying. I am 100% sure this is not a dog. But teacher does not have that kind of certainty. Teacher still has some doubt. Teacher still thinks this image is 10% a dog. So while teacher is making a, I would say, such a less confident probability score for this, student is saying something with high certainty. That cannot happen because we are trying to teach the student what the teacher already knows. So if student makes such a high confident prediction, it should be penalized heavily. And how heavily? How much should be the penalty in this case? It should be as close to infinity as possible. Because see, student is making a completely wrong, completely confident prediction here, while teacher does not have that kind of a confidence. And how does the penalty become minus infinity? Let's look at the formula. According to the formula, loss due to KL divergence, and KL divergence is used for constructing how much does one probability distribution vary from another. You can say it will look something like probability due to teacher multiplied by log pi. So probability due to teacher, which is 0.8 multiplied by log 0.8 by 0.9. This is the first item. So this 0.8 is this teachers, this 0.9 is students. So this ratio is students prediction by teachers prediction. And this vice versa, teacher's prediction by student prediction. And this 0.8 is P due to teacher. That is the first term plus 0.1 times log 0.1 by 0 plus 0.1 times log 0.1 by 0.1. Now this term, what would this term be? 0, because logarithm of 1 is 0. This would be very high number, inf kind of number. And this will be some finite number, okay? So see, we are penalizing the distill token heavily in this case because it is making such an overconfident prediction. What if student's prediction was something like this? What if student made this kind of a prediction? What should be the penalty for the distillation token in this case? And it will be 0. How? 0.8 multiplied by log 0.8 by 0.8. That's the first term plus 0.1 times log 0.1 by 0.1 plus 0.1 times log 0.1 by 0.1. So all these terms will be 0 because for every single item, teacher and student are assigning the exact same probability scores, which means whatever is there inside the logarithm, those ratios will be 1. So the loss will be 0. Now let's look at another case. What if my teacher was very confident? What if I had something like this? Now what would happen? Now my loss will be 0.8 multiplied by log 0.8 by 0.8, first term. Second term will be 0 multiplied by log 0 divided by 0.1 plus 0.2 multiplied by log 0.2 by 0.1. Now I'm just picking an extreme case, but tell me this. I have x and log x, okay? And in this case, let's say I have a formula that looks something like this. X log x, where x tends to 0. What is the output of this? Let's say y equal to this. Is this, what is the value of this? Can anyone ask ChatGPT or something and let me know? So x tends to 0, log of x. Why do you think it's not defined? Just think about it. Which one will decline faster? So log of a small number, you know, it's log of 0 is negative infinity. So log of x will be something tending to negative infinity if x tends to 0, right? But then to counter that, you have an x tends to 0 multiplication outside. My intuition says that this logarithm falls a bit slower compared to how this is linear and this is logarithmic. So my intuition says that this will be close to 0. This will not be close to negative, like undefined. But let me ask, what is x log of x if x tends to 0? Right, it should be a negative number, but it should be close to 0. So as x tends to 0, x log x tends to 0. The reason is the logarithm of x is not approaching negative infinity as fast as x is approaching 0. Because x is linear and logarithm of x it's logarithmic. So I think here, and here there is this rule, right? L'Hopital's rule. So you can write this as log x divided by 1 by x. And it's written as L'Hopital's rule, but it's pronounced as L'Hopital's rule. And then you can say that if this is x tends to 0, then you can take the derivative of both. So if you take the derivative of both, what is derivative of log x? If it is natural logarithm, it's 1 by x, right? If I'm not wrong. And the derivative of the denominator is minus 1 by x square. So then this will be minus x square by x, which is equal to minus x. And what is minus x if x tends to 0? It will be a negative number and it will tend to 0. So even in this extreme case, this formula is still okay. I mean, what I'm saying is there is no mathematical instability in this formula. Even when teacher is making a confident prediction, it is okay. But when student is making a confident prediction, there is no mathematical issue. It's just that the error will blow up. So now you can add those two errors, those two losses to create your final loss. One thing I forgot to mention here is you will have logits first before you get the probability, right? So how do you get the probability? You will first have logits like Z1, Z2, and Z3. And from this, you take softmax to get P1, P2, P3. Now, usually, how do you do softmax? E raised to, so Pi equal to E raised to Zi divided by sigma E raised to Zi, where I runs from 1 to 3. Now, one thing that is done is, let's say I divide this by a t, and if t is greater than 0, will my softmax become 1 more sharp or less sharp? If t is greater than, sorry, I don't mean to say t greater than 0. I meant to say t greater than 1. If t is greater than 1, will it be more sharp or less sharp? Softmax will become less sharp because now you are taking exponents of smaller numbers. But if t is less than 1, if t is a positive number that is less than 1, then this number is increasing. So whatever is inside the exponent will become a big number if t is less than 1. Then softmax will become more and more sharp. So a temperature parameter is introduced here in this calculation. Just look at this formula. In the construction of softmax probabilities, you are taking exponent of Zi divided by sigma exponent of Zi, but you introduce a temperature parameter so that the softmax distribution is made less peaky. But there is one issue with this. One issue with this is that when you take the derivative of softmax, because for back propagation, you need dou L by dou weights, where softmax will be somewhere there inside the loss function, right? The problem is a 1 by t square will pop out. A 1 by t square term will pop out, which means if your temperature value is so high, if it's higher than 1, then it has a tendency to kind of reduce the magnitude of your gradients. So what is done is finally, if you look at the final formula, they have a t square term outside to cancel this t square effect when you are finally taking the derivative. So the final formula is something like this. Loss due to teacher is P probability distribution due to teacher multiplied by log of ratio of the teacher's probability divided by student's probability prediction. This we already saw. But this probability itself is calculated from logits using softmax. But inside the softmax, there is a temperature smoothening or temperature softening. And to minimize the effect of gradients getting lower in magnitude while taking derivative, because while taking derivative, you can mathematically show that an extra 1 by t square term comes. To cancel that 1 by t square term, you introduce an extra t square term. Now your total loss is simply LCE plus L teacher. What is CE? Cross entropy loss. How is it calculated? Between CLS token and ground truth. And how is teacher's loss calculated? It is calculated between distill token and between teacher's prediction. So how do you say Y teacher cap? So, and then you can combine those two. And while combining, you can also do something like this. So L equal to alpha or lambda times LCE plus 1 minus alpha or 1 minus lambda times L teacher. We can define this to be 0.5 so that equal weightage is given to both. But if it is not, then teacher and student will have different, I mean, teacher and CLS token will have different weightages. So this is the final loss function. So this is essentially how data efficient image transformer works. It's very simple, completely same as vision transformer. The only points you have to discuss notice is distillation token is randomly initialized. It is not initialized using CNN. It is as randomly initialized as the CLS token. So there is no, I would say, discrimination between these two. For teacher, in our experiments, we will use pre-trained CNN. And in the paper also, they tried pre-trained CNN as well as pre-trained vision transformer, a bigger vision transformer model. They saw that pre-trained CNN, using pre-trained CNN was better. Next is the CNN, which is the teacher, can be used for producing soft or hard targets. In the paper, they tried both soft targets as well as hard targets. And these targets are how you compare your distillation token against. And they saw in the paper that hard target was better. Maybe one thing I'm curious to know is if instead of CNN, if they used a vision transformer, will the soft target be better to use? That question, I don't think the paper has answered. Then one more thing to note, CNN does not directly influence the value of distill token. CNN only indirectly influences. How does it happen? The CNN's predictions are tried to be matched with distillation prediction. If the predictions is mismatching, that will cause a huge loss. The loss will result in changing the parameters inside your vision transformer. And based on that change, now the next prediction of distill token will be different. So that is how distill token is influenced by the CNN, not directly, it's indirectly. Just keep these points in your mind. This graph is the figure 1 of the paper, which showed their result. So what they have is this red color dots are all data efficient image transformer with distillation. And you can say that with distillation, the accuracy, so y-axis is accuracy, top 1 accuracy for ImageNet dataset, validation set. And here it's the speed with which it can process images. Basically, how many images per second you can infer on. So here you can see that. So in general, if you are on the right-hand top corner, you are good. If you are on the left-hand bottom corner, you are bad. It's not a good model. And here, unfortunately, vision transformer, the vanilla vision transformer, which we learned 2 lectures ago, they happen to be on this bottom left corner. They are relatively slow for the same comparable architecture size. And their accuracy is also slow, but they had a vision transformer model which was very big with 600 million parameter. That was, of course, the state of the art with 88% accuracy. It's beyond this. But here, if you compare it with EfficientNet, so among the CNNs available, EfficientNet was one of the best state of the art models. Your data efficient vision transformer performs better than EfficientNet. And I think this is also data efficient vision transformer without the distillation token. So distillation token is clearly taking you from here to here. So this is just like a vision transformer with a teacher. But this is vision transformer with a teacher and distillation token. So distillation token is indeed playing a huge influence. Just to answer how the distillation token is influenced, it's not directly influenced. See, distillation token's prediction, let's say the prediction is diverging from CNN prediction. Loss is high. If loss is high, gradient is high. If gradient is high, during gradient descent, weights will be modified. If weights and biases are modified in the architecture, for the same input, distillation token will now produce a new output. So that is how it is influenced. So CNN does not directly ask distillation token to change its values. CNN says, okay, here are my thoughts about the current image. What are your thoughts? Then distillation token will give its probability distribution. Comparing these two, loss due to KL divergence will be constructed. And if loss due to KL divergence is high, dou LKL divided by dou weights, where weights are the parameters of your vision transformer, this will be high, which means the way in which weights will get modified, Wi plus 1 equal to Wi minus eta, which is the learning rate, multiplied by dou LKL, or this is the total loss, but I'm just mentioning dou LKL here, divided by dou Wi. This will be a big number. So weights will get modified significantly if the gradient is high. When will the gradient be high? When the loss is high. When will the loss be high? When there is huge disagreement between distillation token and CNN's prediction. So that is how indirectly CNN influences the distillation token. It's not direct. It would have been direct if you were somehow pumping the values from CNN features here itself. But if you do that, that will be cheating because you are directly using the features from the CNN. Here you are not using features from the CNN. You are using only the predictions from the CNN. Okay, according to loss function, we are penalizing heavily distilled token confident prediction. What is the intuition? So that's what I said. So distilled token is a student. And ideally, students should never make confident prediction unless teacher is confident. So unless teacher thinks that the labels are something like 0.80 and 0.2, here teacher is very, very confident that 100% it is not a dog. So if this is cat, this is dog, and this is background, teacher is 100% confident it's not a dog. If teacher has that kind of a confidence, then student is allowed to this is the basic principle of knowledge distillation. Then student is allowed to make a confident prediction. Otherwise, confident predictions can very well become wrong. So being confidently wrong is the worst thing a neural network can do. And how do you prevent the neural network from making confidently correct prediction? You prevent neural network from also making confidently, how do you prevent neural network from making confidently wrong prediction? You also, as much as possible, try to prevent it from making confidently right predictions. So high confidence for student, you penalize basically. All right. Now I think we know all the things that is there in the data efficient transformer. We'll get to coding, but let me look at a couple more questions. How does it work on custom data set, which is completely different from public data set on which teacher model was trained? Or do you think teacher's predictions will be incorrect here, mostly due to data drift? Yes, exactly. So if you think teacher is trained on a completely different data set, it will tremendously benefit to slightly fine tune the teacher on your custom data set. Now, what is the advantage of this? Fine tuning is not expensive. Fine tuning is an order of magnitude less expensive compared to pre-training, because you may be running for few epochs. You are starting with not random weights. You are starting with already existing good pre-trained weights, right? So in that case, you can start with a teacher which is slightly fine-tuned on the new data set. And then you try using that teacher for teaching the student. Otherwise, if you use just a vanilla teacher, which is randomly trained on some random internet data set, it will not give you any good results, right? Good question. It's a good question. So now I think what we can do is please open your Google Colab. We can start coding. You will, of course, notice that there is a lot of similarity between how we coded vision transformer and how we coded data efficient transformer. But it'll be fun nevertheless, because the more you code these things, the more comfortable you will get. So DEIT coding from scratch. Okay, so I will share the notebook link, but I guess it will get, so you will have to type along with me. Otherwise, it will take time to get updated. All right, so first is import module. So one nice way to put title is you can just put like this. So it will come as, hash also is needed. So imports, now let's import all the required libraries. Import torch for PyTorch, torch.nn, because you want to have nn.module passed into your classes, torch.nn as nn, then torch.nn.functional as f. So this is for getting various functions like cross entropy loss, and also for, if needed, for converting vectors into unit vector. You had seen that during the nano VLM lecture. and torch vision for PyTorch for computer vision. Then from torch.utilities.data import data loader. We will also need something called subset. The reason is I'll show you. Initially, I wanted to actually, let's remove this for now. We can train on the whole data set. So just data loader. Then from torch vision, import transforms, datasets, models. So transforms or data transformation, this is for loading batches, and models for constructing your neural network model. Import numpy as np, then import matplotlib.pyplot as plt. I think those are the only items we need. Then we can define device equal to CUDA if torch.CUDA dot is underscore available is true, otherwise CPU. So then just run that. Next is we can define some variables that we are going to use. So what are the variables? Batch size we will need. Let's keep it at 12. Image size probably, if we are using MNIST, it was 28 by 28. Patch size, last time in Vision Transformer, we used 7 by 7 patch. Then attention heads in that Vision Transformer, attention underscore heads, let's say 4 attention heads. Then embedding dimension, let's say it is 32 or something. And let's say number of classes in our final classification is 10. It's a 10 class classification. We'll be using MNIST. We can use other data sets also, of course. Then epochs for training. So here we are not fine-tuning the teacher. We are only fine-tuning the training the student. If we are fine-tuning the teacher, we may have one set of small number of epochs for teacher also, but here epochs for student, let's say 5. Then learning rate for student is something like 3 times 10 to the power of -4 or something. This we can play with. Then I'm going to define something called number of channels. Actual number of channels for our data set is 1. It's a grayscale image, but I'm going to define it as 3 because the neural CNN that we are going to use, it will expect 3 channel input. So let's keep it at 3. I'll show you how to expand the number of channels from 1 to 3. Then attention heads is fine. This is in the multi-head attention. Transformer layers. We will require, let's say 4 transformer layers are there. And then the temperature parameter that we are going to use in the KL divergence equal to, let's say, it should be greater than 1, let's say 2. Then lambda or alpha, which is the scaling factor for alpha or 1 minus alpha, let's keep this at 0.5. So equal weightage is given to KL divergence loss and cross entropy loss. I think that's pretty much it, most of the variables. Next is importing the data. Now we have to define some transformations for this. We had done last in the Vision Transformer coding also, but let's first import the data. So train data set equal to, it is imported from datasets dot MNIST, and we want it in the root folder, and which is named subfolder named as data. Then train equal to true, and same thing for validation. So or testing, we can say test ds or val ds should be a better way to call this. Datasets.mnist train equal to false. Then we have to download this. So keep it as download equal to true. And copy paste that for validation. And then we have to define some transformation to convert it into tensor format. So transformations or transform actually equal to data underscore transformations. We are yet to define this, but we will define it soon. Transformations. So you transform both of these data sets. And then here we define data underscore transformations equal to transforms dot to tensor. But before that, we have to have transforms dot compose. And so converting to tensor is one transformation. Another transformation is you have one channel input. You want to expand it to 3 channels because that is the input that CNN is expecting in this case. So transforms dot lambda, then lambda t, then t dot repeat. I mean, this is just basic syntax. No need to, spend too much time on the exact syntax, but basically it's just expanding into 3 channels, the input. And just close the bracket. So you have 2 transformations. First is transformation to tensor. Second is expanding the number of channels. I think I have an extra bracket. Yeah, I think we are good to go. And then we have to create our batches. So create train and val batches. Then we say train data loader equal to something, val data loader equal to something. And what is train data loader? Data loader of train ds. So we are loading it from train ds. And here we have to pass the batch size equal to batch underscore size. And shuffle equal to true. For validation also, it is exactly the same, except shuffling we don't do, and we are passing val ds. Shuffling is not needed. So now let's run these two, hoping that it works. So batch size is 12. Okay, there is some batch size not defined. Okay. All right, so now training and validation data set is ready. Now we can define our teacher model. So title teacher model. So teacher has to be a pre-trained model. So teacher equal to models dot ResNet 50. So we can simply use a ResNet convolutional neural network. Then what weights are we going to use? We are going to use some weights where pre-training is done on some ImageNet 1K or some data sets like that, public data set. So weights equal to models dot ResNet 50 underscore weights dot ImageNet 1K version 2. So one particular set of weights. So ImageNet 1K version 2 is a specific data set. We are just using those weights. Then what do we have to change here? Can anyone tell me in the chat? Okay, we imported the teacher model, but then we have to make a change to the teacher model, right? What is that? We can't use this as such. There is a small issue. Exactly. You have to remove the last layer because last layer here will have how many nodes in this case? 1000 nodes because it's a 1K class classification, but we don't need 1K nodes. We only need number of nodes equal to classes, 10 nodes. So teacher dot fully connected equal to nn dot linear teacher dot fully connected dot input features. So in the last fully connected layer, we just need the input feature, how many ever nodes it has, but output features should be same as classes. So output feature will be 10. And so if we keep it as 1000, it will be exactly same as what it was before, but here it will be classes. Then we say, since we want teacher also to be processed using whatever GPU or CPU, whatever we are using, we say teacher dot to device, whatever device is being used in our training. Teacher is anyway not being trained. We removed the last layer of the classification head. We did not remove the entire classification head. We removed the 1000 nodes. We removed the output features from the last layer. Input features, we kept it as such. So input features might be whatever, let's say 2048, whatever that number is. So it was a fully connected connections going from 2048 nodes into 1K nodes. Here we remove those 1K nodes. So 2048 is the input number of features going into that, into the final classification head. 1000 was the output nodes. But here we don't consider the output nodes. Output we keep as number of classes, which is 10. So we are not removing the classification head. We are removing only the last 1000 layers. But you need to use those same classes, otherwise need fine tuning. Not necessarily, not because you can think of CNN as a sort of like a feature extractor. So yeah, I mean, I agree that the last layer will be completely randomly initialized and its output may not be as good. So you may want to do a freezing of your neural network where all layers are frozen except the last layer. So these nodes should have some good weights. In this particular case, we are avoiding this entire pre-training altogether simply because the data set is a simple data set. So even the existing teacher model is able to extract data set in a good way. It's the most simplest data set. But if you were to use, let's say, CIFAR 100 or some slightly more complex data set, you will have to do one round of fine tuning. And I don't want to call it as fine tuning. You would have to do just one round of final classification layer training where everything is kept frozen except the last classification head 10 nodes, right? It's a good practice. Otherwise, you will not get a good teacher. Your teacher's predictions will not be good. But here, the good thing is we are not just relying on the teacher, right? We are also relying on the ground truth. Teacher, we are just relying to see what kind of feature extraction this teacher is capable of on our data, and finally, what kind of softmax probabilities are coming out of it. That's it. But it's a very, very good point. Okay, so now let's run the teacher model. Then now we can define the student vision transformer. So student ViT, and this fairly something that we had done before. We need a patch embedding. And earlier we had defined the MLP head separately and the transformer embedding separately. But this time, let's not do that. We'll just say ViT class. So we have one class for patch embedding, one where we simply have the ViT vision transformer class. So class patch embed. And into this, we have to pass nn.module. So it inherits the properties from this class. Then define underscore init constructor underscore, and then here we pass self and bunch of other things also we have to pass, but we'll come to that. Then super, so that you are now calling the init constructor of your parent class also. So this init constructor belongs to parent class. This init constructor belongs to the current class. And then we have to do a few things. First is we should create patches from input images. So I hope you remember some things from the vision transformer lecture where we created a conv2D. So 2D convolution for patch extraction. So nn.conv2D. where this 2D convolution had input features equal to number of channels, which was, in this case, it is 3. In the vision transformer, it was 1 because there was no CNN. There we were just using a vision transformer, and we did not mind whether number of channels is 1 or 3. But here the input that goes into our ResNet is 3 channel input. Just because of that, we expanded the number of channels from 1 to 3. So instead of just writing it 1 here, writing 3 is better, but I'm going to pass it as a variable. So classes we are passing. And here we say classes equal to classes. Then we need to know what should be the embedding dimension, because the each embedding dimension looks like a one output layer of the 2D convolution. So then we say embed underscore dim, and that we have to pass that also. Embed underscore dim equal to embed dim, which is 32, I think, as we defined above. And then this will result in width equal to number of patch. Now we have to define stride and kernel size. So kernel size will be equal to patch size. So we just need to say patch underscore size. So this we pass. Patch underscore size equal to, I forgot the variable name. Yeah, patch size only. Because we have to create non-overlapping patches. So kernel size should be same as patch size. Stride should be also same as patch size. So this we had discussed in detail in Vision Transformer lecture. If you want a brush up, just revisit Vision Transformer once. This part we had at least spend maybe 20 minutes on this section. Then we need to know how we don't add channel argument. So channel we are adding, channel is basically number of classes only. It's just that the value of this is 3. So number, excuse me, number of input channels in your input is 3. Number of output channels is equal to embedding dimension. Kernel is equal to, my bad. I did not mean to pass classes here. I mean to pass channels. Thanks for, this is not classes, this is channels. Okay, thanks for catching. Otherwise, this would have caused a lot of issues in the downstream. But yes, this is channels, not classes. Because it's starting with C in my mind, suddenly I was thinking it has class channels. So this is channels, which is 3. Embedding dimension 32. Patch size is kernel size. This is stride. Then number of patches. So self.n is equal to, this should be image underscore size divided by patch underscore size. Where is that? Patch underscore size. And for this to be an integer, we use this floor operation and raise to 2. And image size is not defined. So image size we pass, image underscore size equal to image underscore size. And what else? Patch size is already there. Okay. So, and then we can define the function where this is executed for every single input. So forward pass self comma x. Then we say x equal to self dot projection of x. So this will create patches, but I hope you remember what we had done last time. We had to flatten these patches. So x equal to x dot flatten of 2, so that all the patches will now look like one. If there are 16 patches, it will look like along one dimension. And after flatten, if you remember, we had one more operation called transpose of 1, 2. The reason was we have a batch size. Our batch size is 12. We had a certain number of patches. Number of patches were image size is equal to n, but image size divided by patch size raised to 2. Then we should have embedding dimension. But by default here, embedding dimension will come first, and then only number of patches will come. But we want those 2 dimensions to be flipped. So there are totally 3 dimensions. First is the number of items in each batch dimension. Second item up until this point will be the embedding dimension. Third item will be the number of patches, but we want number of patches to be in the second dimension. That is why we are flipping or transposing along dimension number 1 and dimension number 2. Dimension number 0 is batch dimension. So far, we have used only one filter here. No, the number of filters, I mean, manually we have defined only one filter, but the number of filters will be embedding dimension. So number of filters is equal to 32 here. Please remember, number of channels in the filter equal to same as number of channels in your input. Number of filters is equal to number of channels in your output. So here at the output, number of channels is 32. So this operation will define 32 filters automatically. We don't have to do it manually. Batch first equal to false. So batch first equal to true we have to define, but that comes in the multi-head attention part. Here, I don't think we have to do that yet. And then just return X. So now the batching is done. No, not batching, patching is done. Then we define the class for vision transformer, which we can write separately. So here, patch embed. Then next will be student vision transformer class. So class ViT, where we pass nn.module, then define underscore init, constructor where self is there and bunch of other things we may have to pass. We'll come to that. Then super init. And okay, now we have to define a few different things. First is let's define the patch embedding by creating an object for patch embedding class here itself. So self.patch embed equal to this class. So equal to patch embed. And then we need what? CLS token, we need embed token, we need token embeddings, we need position embeddings, all these things we need. So yeah, not embed token, dist token. Thanks for that. Yeah. Okay, so now let's define self.cls. Self.cls token was initialized as learnable parameter. So nn.parameter. So it will be initialized randomly, but it will be learnable. Then torch.zeros. Here it's actually not initialized as randomly. Otherwise, it would have been torch.nn.random, rand.nn. It will be sampling as a random numbers from the normal distribution. But here we can initialize as zeros, 1, 1, dim. So this one belongs to embed dim. This one belongs to batch dimension. This one belongs to the fact that you have n number of patches. And this embed dimension is the fact that each patch is of the dimension embed dimension. So embed dimension we'll pass here. Embed underscore dim. Okay, so that is self.cls. Then self.distill or distillation equal to also nn.parameter. It's pretty much exactly the same. There is no difference in the structure, but they will learn different things. So distillation is done. Then let's come to position embedding first. Self.position embedding equal to nn.parameters meter of torch.zeros. Again, we can initialize is at zeros, but then it will be learnable of 1, comma, what should the next dimension be? Last should be obviously embed dim. What should be this middle dimension? What should this number be? Just a number. What should that be? Or if not number, just give me like a variable that represents this. It should be number of patches plus 2, because n number of patches result from creating patches from images. But then you have CLS token in addition. For that, you have to add a position embedding. Then you have distill token at the end. For that also, you need position embedding. So whatever is the number of patches, you have to do +2. So let's say n plus 2, where n is the number of batches which we are yet to define. So n equal to, or self dot n equal to, we can say patch embed, or patch embed dot n, right? Where is it? Yeah, n. So this will find the property of dot n from patch embed. I'm not sure if there is any. Okay, self dot patch embed dot n. Yeah, okay, now it's fine. And this, maybe we have to define this as self dot n, but let's see, self dot n plus 2. Or this can be just since it's independent of, I think this is also fine. So n equal to self dot patch embed dot n. Self dot patch embed is the object that we are currently looking at, and patch embed dot n is this n from here. Patch embed is the object corresponding to this class. Okay, position embedding is this, and then we have to define self dot transformer blocks equal to nn dot sequential. And here we have to actually add bunch of things, right? So one interesting thing is, actually, let's not write it here. It will come later. We just need to define what is this. So nn dot transformer encoder layer. So here we are calling this transformer encoder layer. In Vision Transformer, we did not call transformer encoder. We just called multi-head attention. Then we constructed the transformer encoder by adding residual, adding multi-layer perceptron, etc. separately. But here, by calling transformer encoder, all of that is internally taken care of. We just need to pass the embedding dimension, number of attention heads, number of blocks, just those three things, and batch first equal to true. So embed dim, we have to pass. Then attention heads, attention underscore heads, we have to pass. Then number of, or rather dimensionality of dim equal to 4, which let's say is the dimensionality. I don't know if it is divisible by. Okay, let's keep it. We'll come back to this, whatever the dimensionality of my query key value space should be. This one I'm doubtful. Let's keep it. Attention heads we have not defined. So attention underscore heads equal to attention underscore heads. Then dimension equal to 4, and then batch first equal to true. I think that's mostly it. But then you need how many such transformer blocks? So this dimensionality is now the dimensionality of the key query value space. I think it is better if I just say this is equal to dim equal to something divided by attention head. So embed dim underscore dim divided by attention heads. And then this I can just pass here. QKV dim equal to this. Okay, so I think this is better. And I just need to now ensure embedding dim and attention heads are divisible. So embedding dim is 32. Where is that? 32. And number of attention heads are 4. Okay, 32 by 4 is fine. But if we use 32 and 3, this will cause an error because number of heads and embedding dimension, they should be divisible. But one more thing is, but I need bunch of transformer blocks, right? This is just one transformer encoder. So how do I write this? We need to sequentially add. So one thing is we can say nn.sequential of, then I can write this 4 times. I can copy paste whatever is this 4 times, but oh yeah, batch first equal to true. That automatically came. Temperature, it's not temperature, it's true. So I can copy paste this 4 number of times to say that, okay, now I have 4 transformer blocks in my vision transformer, but what if then I have 20? I can't copy paste this 20 times. So then I can do something like this. Inside this, I cut and paste this. And for dash in, what was it? Attention or no, transformer blocks, I think variable name, transformer layers. So I can pass layers here, layers equal to this, and then I simply have to do a for loop where I'm looping through these layers. And I hope that's it. I'm missing something in the syntax. No, batch first should be true because the first dimension that the transformer should encounter is the batch dimension. For dash in layers, what am I missing? In range of layers, but then still I'm missing a bracket, I think. Range typo. Okay. How about now? Why is this coming? I'm not understanding. Self dot transformer blocks equal to nn inside, but that I have here, right? Am I wrong? I think this should come afterwards. Yeah, obviously. Yes. Yeah, for sure. Yeah, I think now it's fine. So we have now transformer blocks where each of these transformer encoder layers, which will include attention head as well as multi-layer perceptron, repeated n number of times, where n is the number of layers. Okay, and now we need self layer normalization. So self dot layer norm equal to, do we have option to give hidden size of MLP? Yes. No, I think it's by default it's 4x, but I'm pretty sure it's that option exists for sure. Yes. Self dot layer norm equal to nn dot layer norm of dim embed underscore dim and self dot head underscore CLS. So now we are coming to the CLS tokens classification head, and we need one like this, self dot distill underscore CLS. So CLS, distill underscore head. So we have 2 classification heads, one for distillation token and one for CLS token. Now this will be the item number 0. This will be item number last. So nn.linear of, and here we are going from embedding dimension to, what are we doing in the classification head? We go from embedding dimension to something. What is that something? Number of classes. Embedding dimension is maybe 32, 64, whatever. Classes is 10. So we go from that to classes. So classes we have to pass here equal to classes. And same thing applies for this. This is also the same. So these are all learnable parameters, by the way. Whenever we have nn.sequential, nn.linear, everything inside that is learnable. I think that is pretty much it. Layer norm. Yeah, sure. I think that's all. Now we just need to do the forward pass for every token. So define forward of self comma x. And then we say x, or first we need to extract the batch size, because this we had discussed in the last lecture. If we do not extract, if we keep using batch size as a variable, there might be some batches towards the end whose number of elements may not be 12. Maybe it has only 9 elements. Maybe it has only 7 elements. So the safest thing always to do is extract the number of items in your current batch by looking at the 0th dimension of your input variable. Then x equal to self dot batch underscore embed this one of x. So now you have patch embeddings. X is converted into patches. Then you define CLS token. So CLS equal to self.cls. But one thing you have to do here is CLS token. How many CLS tokens do you have? Here you have only one CLS token, but you have to expand it along your batch dimension. So say self.cls.expand, because you need one CLS token for every items in the batch. B comma minus 1 comma minus 1. You are only expanding along this dimension. Rest of the dimensions remain untouched. Second dimension is the number of patches. Third dimension is the embedding dimension. Now, distillation token, dist, equal to self dot distillation dot expand b comma minus 1 comma minus 1. Same thing. So class token and distillation token they have no difference. The only difference is where you are appending them. Class is appended, prepended. Distillation is appended at the end. Now we say torch dot concatenate. So torch dot cat. Here you are concatenating three things: CLS, comma, following CLS. What should you write? CLS, comma, something, x, comma, dist. Can you do something like this? Can you do dist, comma, x? Can you do this? You can do that also. I mean, I don't think there is anything conceptually preventing you from doing this. Only thing is you have to be careful about which context vector you are extracting at the end. In one case, you will extract 0th and n+1th context vector. In another case, you will extract 0th and first context vector. That's the only difference. But here, let's keep it as the original data efficient image transformer paper. So class, comma, CLS token, comma, x, comma, distillation token. So you are concatenating and comma 1, but this concatenation happens along the I would say first dimension, because 0th dimension is batch, first dimension are the tokens. But then to this you have to add a position embedding. So in the last lecture, if you remember, we had expanded the position embedding also, but it's not strictly necessary, because if you simply add this self.position, this will automatically, Python will automatically do something called broadcasting. So see the issue here. Position has not been expanded. So position is still, it is assuming that the batch size is 1, number of items are n+2, and last item is embedding dimension. But here CLS token is taking B. B is mostly 12. So here the dimensionality is 12, comma, n+2, comma, 32. But position embedding is 1, comma, what was the second one? n+2, comma, 32. So now you might wonder, how do you add two tensors where one tensor is of dimension, the first dimension was the B, batch size 12. Second dimension is number of tokens, which is n+2. Third dimension is embedding dimension, which is 32. How do you add that with position embedding, whose dimensionality is first item is only 1, second item is n+2, third item is 32. So Python automatically does something called broadcasting, where even if you have not expanded the self.position along the batch dimension, when you are adding, here that broadcasting will automatically take care of it. So you don't have to explicitly expand this along the batch dimension. Then x equal to, so this is where you now have all the tokens with position embedding. Now you pass it through your transformer. So now you say x equal to self.transformer blocks of x. And here actually you have to pass it Here you don't have to pass it 3 times because you are not calling multi-head attention. If you were calling multi-head attention, you will do x comma x comma x. Why? One for creating query, one for creating key, one for value. But here, this is the whole transformer block itself. So you don't have to do it explicitly. So self.transformer blocks of x. Then you do layer normalization. So x equal to self.layer norm of x. Now you are ready. Now by this time, you will have both tokens ready to be extracted. So CLS underscore token equal to 0th item x of 0 for every batch. It's the 0th item. And similarly, distill token underscore token for every batch, it is the last item, which is -1. Very good. I'm glad you are paying attention. Then, so now you have distill token. Now you have CLS. Now what you should construct? You can construct logits. So CLS underscore logits is this extracted CLS token now has to pass through your this head self.head CLS self.head CLS of CLS token. And similarly, distill logits. So this is before the softmax. You're just taking the logits equal to self.head distill head distill, and here you pass the distill token. So now you have the CLS logits and distill logits. I think that's all you need. You can now simply say return these two logits. Softmax you can calculate later. Return CLS logits and distill logits. So by this point, you will be ready to have the logits used for loss calculation. So loss we have not defined yet. The KL divergence loss we are yet to manually define. But before all of that, let's just run this to see if there are any syntax issues or not. I'm pretty sure something or the other might. Okay, luckily it has run. I don't think there are any issues. Now, one thing we should write is define student model. So student equal to, now what is the name of the class? ViT of dot to device. So just like how we pass teacher into CPU or GPU, same thing we do for students. And optimizing parameters are all the parameters in the student. So torch.optim.addmw student dot, so this is the same student I'm pasting here, basically dot parameters. So I'm optimizing these parameters. And how am I optimizing? I'm optimizing it at a certain learning rate. It was LR underscore learning rate underscore student, if I remember correctly. This was the variable that we used. Okay, so that is also done. Now we can perform the distillation, the KL divergence loss. So let's say define the loss function. So in the loss function, define, this is just a function. So KL divergence loss is, so here what are we passing? We have to pass some logits from the student. So let's say student logits. We have to pass some logits from teacher. So teacher will make some prediction. So teacher logits, and alpha or lambda for defining how much weightage we should give to both losses, loss due to difference between distill token and teacher, and loss due to difference between ground truth and CLS. So alpha equal to alpha. We had defined alpha as 0.5 earlier. Temperature also we need temperature equal to temperature. Then we need to define two losses, KL divergence loss and second one. So this equal to something, KD equal to something. Second was cross entropy, CE, cross entropy loss. And when we finally return, we will return something like alpha multiplied by, so it was alpha multiplied by KD and 1 minus alpha multiplied by cross entropy. So plus 1 minus alpha multiplied by cross entropy. So this is the final combined loss. So now we have to calculate individual loss. Out of this, cross entropy is the easiest. So that is f dot cross underscore entropy. And what should I pass here into cross entropy? What are the two things that I'm passing? Oh, one thing I forgot here is y. Y is the actual ground truth. We are passing CLS, the logits from the S from the student and the actual Y, which is the ground truth, right? So S logits, comma, Y. Y is the ground truth. We are yet to define the ground truth Y because we have not extracted it yet, but that we will come to in a bit. So in the S logits, we will selectively pass one of them depending on, S logits dot, yes. It should be, should I pass each of them separately? Maybe. No, I think this is fine because see, in student logits, depending on what I'm passing, I can simply pass the logits corresponding to CLS token here while calling the function. So this is fine. Writing like this is okay. Okay, now KD is f dot, there is a function called KL underscore div, KL divergence. And here we have to use softmax because so far we have not touched softmax. In cross entropy, softmax is inherently coming. So we can pass the logits directly. But here we have to do softmax. So softmax of S underscore logits divided by T dot dim equal to comma dim equal to -1. Now is T defined? No, it's only temperature. And so this is the softmax for student and comma. So KL divergence is calculated between students, this and teacher. So teachers is f dot softmax, teacher logits, temperature is temperature, dimension -1. So here, when I say student, it can be CLS or it can be distill. It can be either. Maybe one way to remove your confusion is, let's say, I call it this as CLS logits and I pass distill underscore logits. And then CLS logits I use here. Distill logits I use here. I think now it's cleaner. Am I missing anything? I think that's mostly it. Let's run. Okay. Now we can run the epochs. So at hash title epochs, and running epochs is independent of code. So I can directly take my epoch code from the what I have already written. Okay, so for E in epochs underscore, I'm not sure if epochs underscore student is the variable. Okay, it is. So for E in range of epochs underscore student, student.train. Student we have defined over here. So student.train means our vision transformer will be trained. For X comma Y in train underscore data loader, for X comma Y equal to X dot to device, Y dot to device. So images and corresponding labels. And with torch no grad means you are purging the existing gradients instead of letting it accumulate. This is something that standard you do if you are running on small data sets. T underscore logits is teacher of X. So teacher we had defined up here and we had passed teacher to device right above this block. So teacher equal to teacher dot to device. So we are passing into that our input X. And then CLS underscore logits and distillation logits are output from the student. So why am I writing this comma this? Because in the return, if you remember, we are returning CLS logits and distill logits from the ViT class. And then my loss is KD loss, but here I'll make some change. Here, instead of distill logits, I will pass CLS logits, distill logits, teacher logits, and Y. So CLS logits, dist logits, teacher logits is T logits, and Y. So this is the CLS token logits. There's a distillation token logits. This is the teacher's logits, and this is the ground truth. 4 things. And if you remember from our diagram, we had mentioned that you need 4 things for calculating the loss: from distill, from CLS, from ground truth, and from the prediction of the CNN, which is the teacher. So now we have all the 4 items. And I think we are ready to just run this. Let's see. I hope. Okay, some issues there. Name student is not defined. Maybe because I have not run that block. So I'm just running the whole thing once. Got an unexpected argument dim. Somewhere I'm using dim instead of embed dim. Okay, dim equal to -1. Not -1. This should be 1. Because for each batches, we are calculating this for that particular token, that particular context vector token. Maybe that is the issue. Got an unexpected self.transformer blocks equal to, okay, its issue is there in this line, I think. Maybe I just need to pass like this. Yeah, I think now it's working. So the issue was here I was passing it as dim equal to query key value space dimensionality. You just need to pass the query key value dimensionality. You don't have to say dim equal to that. So this one line was the issue. I think it is running. Let's see. Yeah, I think it's running. This warning, I know what fixes this warning. There is some extra parameter that we need to add here, something like reduction equal to batch mean. Although I don't know what exactly it does. I know that it can get rid of the warning, but let's run it without that anyway. So this is just the training epoch, and then after this we can run validation. So let's paste that so that once this is finished. So test DL. I don't think test DL is defined. I think this is validation data loader, val DL. I think rest of the things are fine. And once validation is done, we can display some sample image from our predictions. So this is again not anything specific to data efficient image transformer or vision transformer. It's like for any deep learning. So I don't want to write this code and spend time here. Let me try stopping and asking Gemini to explain this. Or let me just try adding that extra parameter here. Reduction equal to batch mean. Oh yeah, I had forgotten this temperature raised to 2. Yes, this was missing. I think Gemini gave me the suggestion. This was completely missing. As we discussed, if we take the softmax derivative, 1 by square of temperature term will come. So to nullify that, you should have a temperature square term. So I hope this may fix the issue, the warning, but let's see. Yeah. We can ask actually GPT, what is this batch mean thing actually doing? And meanwhile, my code is running. Let me know if you guys are also able to run the code on your end. I am running this on, I'm not sure if this is GPU or something. I think this is just CPU. Maybe I'll change the runtime. I'll use this TPU. but this code was small enough. I had one extra line here just to try with a smaller data set. So I think this original MNIST data set had 60,000 images or something. So I just wanted to try with 6,000 images. So I had written one extra block of code for splitting my data set into just 60,000. Then this training will be faster. But anyways, this is not too bad. But let's bring the splitting part of the code. So this was a splitting part. If I say n equal to 0.1 times len of the training data, then I'll only pick 10% of the data for training and validation, just the total 10% from my data set. Actually, let's try that. Actually, this is a bit slow. I don't like it. So train, okay, n equal to int of train ds. Then subset is that of this, and we have to import subset. And train ds equal to this. And this is train underscore full maybe. And validation, yeah, validation can remain as such. I think most of the things are fixed now. And n equal to 0.1 times. So only 10% of the data is used for training. Let's see whether this works. Okay, this is faster. Has anyone managed to run, guys? Is the code working for any of you? I'm pretty sure you can see the latest version of the code with you. Okay. We can do some interesting things. So here, the loss, or rather in prediction, let's see what kind of token are we using. So just look at the prediction. So prediction is, actually, let me comment this out and let me only use distillation token. So right now, if you look at what we are using for prediction, I'm just using the argmax of the distillation token. So in the paper, they had tried distillation token separately for prediction. They had tried class CLS token separately for prediction, and they had tried combined. So combined is simply I can just add CLS logits, distillation token logits, and divide by 2. Okay, test accuracy 3.3%. Let's see what's going on. First, let me do one thing. I will uncomment this, and then I will use CLS and distillation. That's the first thing I want to do. Second thing is I just want to make sure that in my validation batch size is not too big. So I'd be much safer to directly use this block of code. So train DL, data loader, and now I just need to use test DL and train DL and wherever I'm calling my model. So this should be test DL. Yeah, I think that's all. Just let me know the accuracy you guys are getting. Earlier I was getting 95%, 88%, something like that. But let's see. Has anyone managed to obtain pretty good accuracy, like 80% or above yet? Okay, okay. So right now, maybe I can just reduce the whole architecture size a little bit. I just want some results to be initially seen, and then we can see. Epochs is 5 only, and this is a reasonably small architecture, so I don't think running should take so much time. I don't know why is it a bit slow right now. Earlier when I was trying to run, it was definitely much faster. I may have the residual output from it's not there. If any of you have Collab Pro, I also loss need not be log softmax. Log softmax is just used for preventing the things from blowing up, the softmax exponents from blowing up. But here, I don't think you are talking about here, right? This should be log softmax, and this should be. I don't think it's needed because the actual formula is softmax. It's not log softmax. And KL divergence will automatically take care of the rest of the things. But the arguments that you are passing into the function is the softmax of the logits, right? Logarithm is taken within the KL divergence formula. So to my understanding, we don't need this. We don't need to use log underscore softmax here. For anyone, is it taking this much time? I was trying this, but it was much faster for me earlier. For some reason, right now it's very slow. Okay. Let me actually pause this and maybe I can try over here. Okay, one difference is here embedding dimension is much smaller. So of course that will make things a bit faster. And let me keep just one epoch. How about that? Yeah, it's already one. So at least we can see the last result, how it looks. Test accuracy 10%. Wow. Yeah. Here we took one out of 10. Yes, yes. We split the data set by saying n equal to 0.1. So test accuracy 10% is completely, it's the worst possible model. But let's see. I was able to get 95%. I just don't remember what hyperparameters I used, but I'm pretty sure we can get there. Here I'm not sure if I think you were mentioning whether this n is, yeah, this should be 0.1, then it will be a bit faster. Okay, so now we are using only 10% of the data, only for one epoch. Hopefully this should get executed in a reasonable amount of time. Okay, it is done. Test accuracy 43%, not bad for one epoch. And these are my predictions. So since only 40% is correct in test here, 7 is correct. 7, this is wrong, this is wrong, this is wrong. Only 1 out of 5 are correct. But now let's increase the number of epochs. Oh, 1 is too less. At least 2 or 3 we can keep. Let's keep it 3. And let's see if this runs faster. I'll actually share this code link. I don't think anything is in principle different between this, my previous code and current code. It's just that hyperparameters, maybe I have messed up something. I just cannot figure out what. But just try this code. I have just pasted the link. Okay, slightly improved, 56%. And one thing I can do is, instead of using distillation token alone, maybe I can use both CLS token and distillation token for predicting the testing. 45%. Okay, so clearly I need more epochs. So let's keep it 10. And the rest of the things can stay as such. And let's run. Yeah, I think in one of the lectures, or maybe on Discord, we can discuss about importance sampling. I'm not planning it as part of a lecture, but probably we should discuss about it at some point. Yes. But try this code with 10 epochs. I hope you will reach close to, I don't know why am I not getting, what did I do different to not get a good classification accuracy yet? I'm doing everything correct. So the loss is taking into consideration both while making the prediction. So CLS underscore distillation. So both are being considered. So I'm taking average of the logits from CLS and distillation and then taking argmax of that. And that is what I'm denoting as the prediction. I know one conceptual thing that we should do better, which is we should do fine tuning of the last layer of CNN. Okay, now test accuracy is much better, 83.24. Now let's see what would be the test accuracy if I use only CLS logits instead of CLS and distillation. What do you predict? If I just use CLS logits, will it be worse or will it be better if I run the code? The test accuracy, will it become better if I use only CLS logits instead of CLS plus distillation? Better or worse, in your opinion? Should be probably worse, right? Because, yeah, ideally the same, of course. But I think it will be worse because, no, I don't know why I think it will be worse. Maybe let me run and figure out. 7. Oh my God, there is something definitely wrong. If it is 7%, it's the CLS logits is not doing anything. What about distillation logits? The distillation logit is 85.85%. Okay, so clearly distillation is doing most of the things, although my CNN is not very, last layer I have not trained at all. So this last 10 node classifier is like a really bad layer. Actually, I should do a little bit of fine tuning by freezing every single layer to make sure that this last 10 nodes are also not random. So even without doing that, right now teacher is doing most of the work. Ground truth is not helping me with the class token. But here are my predictions, display predictions. All of these are now, except I guess this one, all of them, other rest of the ones are correct. So clearly the code is working. It's just that we have to figure out why CLS token, if I just use CLS token, why the testing accuracy is so low. Maybe let me test on more number of samples, I guess. Len of samples. I guess that's not changing anything. So what we are observing is distillation token is performing the best. CLS plus distillation token is performing somewhere in between, and CLS token alone is performing the worst. That's what we are seeing here right now. But this is extremely surprising to me because when we implemented Vision Transformer, we were getting very, very good results. How will you freeze other layers? Oh, that part is actually very easy. The code is actually very easy. I don't even have to write from scratch. I can just ask Gemini. Here, freeze all the layers and train just the last classification layer. It's only like 3 lines of code or something. Yeah, CLS logits are actually trained with ground truth. So it doesn't make sense to me why the accuracy for CLS token is very bad. I have to check a little bit in depth why this is happening. Yeah, I think that's it. So for param in teacher.params.require_grad is false. So every layer except the last fully connected layer, you are not passing the gradients through that at all. So now, okay, let's try this. Let me train the teacher. This code is already shared with you, but let's see what happens if teacher is slightly better. I don't think it should make any difference, but maybe it does because teacher not just influence distill token, right? Teacher, the loss that is present, the global loss is influenced by teacher as well as ground truth. Global loss influences the all the weights, and if all the weights are changed, basically both CLS token as well as distill token, both of them changes. Not necessarily, right? So if we change the teacher model is influencing the final loss, and it doesn't matter where the loss is coming from, whether it's coming from distill or CLS. Finally, it's influencing the weights. So learning rate is 3 times 10 to the power of -4 in this case. Yeah, that's true. Learning rate could be it could be higher. I should probably do a grid search of different learning rates. I'm happy with 85%, but I'd be happier if we got something similar to Vision Transformer. In Vision Transformer, we got 90, 96, 98%, if I'm not wrong. But here, let's see with a teacher whose last layer is also trained. Let's see what's the output looking like. Okay, definitely something is wrong here. It can't be 4%, whatever it is. So, but if I use CLS and or if I use only distillation token, 81, somehow a better studied teacher is performing worse. Let me do one thing. Let me play with alpha a little bit. If I keep alpha as 0.1, So what does that mean? It means 0.1 means scale divergence is only 0.1. Ground truth, I am paying 90% of the attention. Not attention, I mean weightage. So let's see now what happens if I run. So now it should be more like a normal vision transformer, because in my loss, 90% of the loss is due to cross entropy loss between CLS token and the ground truth. 10% is the loss scale divergence loss between distill token and the teacher's prediction. If this experiment is not giving us better result, we'll stop at this point anyway. I highly recommend you guys to play with the hyperparameters like learning rate, play a little bit with maybe the number of attention heads, embedding dimension. I'm using 16. Maybe do we need 64? Just try that. Just play with a little bit of hyperparameters in this, like an ablation study, and just come up with what works best for this particular data set. For whatever reason, I am not able to replicate the like 95% results, which I got for the same code for a different set of parameters earlier. But now we are able to get only till 85%. One thing that is missing is we haven't written the training loop for teacher. So how come teacher will learn right now? We have just mentioned the condition. I forgot to write the training loop for the teacher. So that is missing. So maybe my thinking is maybe the teacher is not at all giving good predictions right now because the last layer is not trained. And because of that, the model is really bad. Okay, so now test accuracy is 85 with distillation. With CLS, it's again very bad. And CLS dist 80. Okay. All right. Anyways, that is all right. These are some of the tests. In these tests, most of them seem to be correct, except this one. Prediction is 4, ground truth is 1. These are actually simple images to make prediction on. I don't know why 1 is getting predicted as 4. So it clearly shows that the model is not very good. Because if the model was good, it would get confused on, okay, you got CLS. Oh, really? CLS logic 95%. I'll be very glad to see your hyperparameters, what changes. I have never managed to get CLS logic. I mean, I have not spent too much time on this, but whatever time I spent, my CLS logic was always performing the worst. Himanshu, you can feel free to share your code on Discord. We'll take a look at it. But I hope, guys, you understand the basic idea. The whole point is you can use a teacher that is well trained on your data set, and I mean on a global data set, and then you can fine tune it if needed on your data set. If your data set and the public data set on which the big teacher model was trained on are completely different, and then use the teacher model to guide a distillation token's loss, and thereby the weights and bias parameters in your model, right? And that way you can get the student to mimic that of a teacher. So here it's sort of like compressing the teacher's abilities. You are compressing it into a smaller model, sort of. So, and this idea is not introduced by data efficient image transformer for the first time. There are other papers that explore this idea so much, but this DEIT paper came out at the right point in time, because vision transformer showed that it can achieve state of the art, but people did not like it too much, mainly because firstly, the data set, the JFT data set was not publicly available. So replicating exact results was not possible. Secondly, to run it itself, an individual cannot run. Like you and I cannot probably run train a vision transformer completely from scratch, just like how Google did it. So that was another thing. But this data efficient image transformer, this is something we can replicate from this paper. Whatever results they have, we can definitely replicate it ourselves, because it's reasonably small. You don't need insane computational resources. Dataset is also publicly available, and still you are able to get something close to state of the art. So that was the significance of this paper. I really encourage you to okay, learning rate is smaller. So I am using a higher learning rate, I guess, right? 3e minus 4. Instead of that, maybe just 10 to the power of minus 5 or 1e minus 4 or something like that. If I use, perhaps it'll be better. So this I should change. Okay. While I wind up, I'll just run it in the background and let's see. So please have a look at this paper. I'm sure you are going to have a relatively easy time understanding this paper if you have understood how vision transformer work and how the architecture of data efficient transformer is. It looks like long paper because it's 22 pages, but in fact it's short because look at, it's just one column. The margins are so huge. Some pages are just tables, like one of this page or not this, where is that? This one of this page is just a huge table. Yeah, this one. So, and last few pages are anyway references. So this paper was, I had a relatively easy time reading this paper. Usually papers drain a lot of energy from you. You need multiple hours to sit, but I have maybe read this 3 times at this point, the paper. First time it took me maybe 3.5 hours. Last time I read, maybe I could finish it in 1.5 hours or something. So I know that as a scientist, we should not think about length and all those things of the papers, but as a human, of course, when you see a giant paper, you always get intimidated and you probably have less motivation to read it. But this paper, from that point of view, this paper is easy. So please have a look at this. Please try to replicate the code, try to achieve a better accuracy than what I have showed you, because clearly you can play with the rest of the numbers to get good accuracy. It's just that I haven't played with it. You guys can play with it on your own time. I hope you enjoyed today's lecture. In next lecture, most likely we'll be learn about shifted window transformer. It's another approach where people try to bring the idea of CNN convolution into vision transformer. So it was a beautiful paper, very high number of citations. We will hopefully build that also from scratch. One thing I want to address is these lectures, of course, are going longer simply because I have decided to add coding from scratch as much as possible. So I know that it's not ideal for many of you. Maybe you want to leave earlier, but I think you will have the best learning experience through deep work and long thoughts, right? So you have to sit down and code. So I could do this lecture with just the theory and very little coding from scratch. I could just run the code myself, and I could stop the lecture at 12 p.m. But if I do that, I don't think it'll be fun for any of us. So thank you so much. We will meet again next Saturday. Take care until then. I will try to post 3 assignments this week for all the guys in Pro. One for Vision Transformer, one for Nano VLM, and one for DEIT. But I will not impose like a 1-week deadline, because that way, you guys can take your own time to wrap up the assignment. So just have a good time coding these models from scratch. We will move on to detection transformer after this. So far, we have not discussed about object detection or segmentation using transformers. We have only discussed about classification, but detection, as you know, is the, I would say, classification is the gold standard, but detection is, of course, more difficult and more useful task. So we will come to that. And Pro is not different. These are all part of the Pro, but Pro folks have access to my files, handwritten notes, etc. But anyways, see you next weekend. Take care until then. Try your homework, and let's meet by next Saturday. Welcome to a new lecture. Today we'll be learning about Swin transformer architecture. Swin transformer is a natural extension to the 2 transformer architectures that we learned in the last few lectures, especially vision transformer and data efficient image transformer. So I originally thought we will first try to understand an intuition and then coding from scratch today. But Swin transformer architecture is actually a little bit more complex. So I'm splitting this into 2 parts. In today's lecture, we'll be understanding an intuition, which I will also remind you to kind of brush up once before the next lecture. And next lecture, we will code a Swin transformer from scratch. And code will be a little bit more complex than anything that we have done so far in this course. So I really want you to be on your full attention today and next week, because there are a few things about the implementation of Swin transformer that are not so straightforward. I will also be putting out a video on a review of the Swin transformer paper. So I have been going through the Swin transformer paper in detail. The paper is really dense. It's from Microsoft. The paper has around 38,000 citations. I think it came out in 2021, and it's from Microsoft Asia research team. And they showed, probably in the most convincing way for the first time, that transformer architecture can become a good backbone for pretty much any kind of universal image task like classification, detection, segmentation, etc. So that's the relevance of this paper. But one thing I personally found from the paper is not written in the best possible way. It's very dense, and I wish they were not so frugal in terms of number of words while writing. But in any case, that's the reason why we will spend a lot of time on the architecture itself. So with that, the Swin transformer architecture is basically a short form of shifted window transformer. So shifted, we'll see what is window and what is being shifted. It has a lot of things similar to vision transformer. So your past knowledge from how vision transformer works will be useful here, but there are also quite a lot of differences. And architecture, when I show you the architecture diagram, you will understand. So in vision transformer, it was doing this in a brief nutshell. You had an image of height, width, and number of channels. And then this image was split into patches. Patches are basically non-overlapping, and each patch is considered as a token. And then we flatten these patches into like an array. So in this case, you have 9 patches representing the image, and then 1 patch is added as a classification token. And all these, 1 token is added as classification, and all these tokens also are added with position embedding. And then that whole sequence of tokens is what goes into the transformer architecture. And transformer architecture is something with self-attention without masking, because here the task is not next word prediction, because of which masked multi-head attention is not needed. It's unmasked. And then after going through attention, the CLS tokens context vector alone goes into MLP Classification Head. And then here you decide what class this particular image belongs to. In data efficient image transformer, we had some differences. One was an extra distillation token. Distillation token was appended at the very end, and distillation token was trained on the predictions made by the teacher model. Classification token was trained on the ground truth. In the last lecture, we saw how data efficient transformer can be much more lightweight. It was trained on just ImageNet 1K dataset. Now, a vision transformer, although this was great, it had a bunch of issues, specifically with respect to computation. So just look at this. If you have an image of, let me not show you this first. I'll just ask you, let's say you have an image of size I, or image of height H and width W, and let's say patch size is P. Totally, how many patches do you have in this whole image mathematically based on these 3 parameters? If you can mention in the chat the total number of patches. It should be, you have H by P patches along the height and W by P patches along the width. Total number of patch will be H by P multiplied by W by P, right? These many patches are there. And which means number of tokens is same as this. Number of tokens is same as number of patches, because each patch is converted into 1 token. Now, if we were to construct self-attention, in self-attention, you have to do the dot product between query and key. So q dot key transpose and bunch of other things also. But when you perform this calculation, the order of magnitude of complexity is proportional to what? So if I were to say order of complexity of attention is proportional to what? Is it proportional to the number of tokens, or is it proportional to something else? It must be proportional to the square of number of tokens. Why is that? Because you will have n queries and you will have n keys, and every single query is taken as a dot product with every single key. So the order of magnitude of this attention's complexity, attention computation complexity, will scale with the square of number of tokens. Now, what is square of number of tokens? What is HW actually? What is the product of H and W? HW equal to what? In terms of image, what is this? It's a total number of pixels. You have H pixels along the height, W pixels along the width. So HW is basically image size if we were to denote image size by the total number of pixels. So from that point of view, in vision transformer, okay, vision transformer is great because you can construct global attention or long range dependency between tokens that are geometrically far away. You can have a strong attention score between top left token and bottom right token. It's possible, but the complexity of attention calculation will scale with n square. N square is proportional to HW square, which is basically image size or number of pixels in the image. So basically, if you double your image size or if you double your resolution, your order of magnitude of the attention score calculation will go up by 4. The complexity will go up by a factor of 4. This is why it's called quadratic complex. So this was one issue with self-attention. It becomes immediately challenging for high resolution images. And if you want to perform tasks which are like semantic segmentation or instance segmentation, where every single pixel is classified instead of classifying the whole image, or instead of drawing a bounding rectangle around the object, for such tasks, you need high resolution images. And high resolution images are always problematic for vision transformers. So here in this image, I'm showing you an example. So you have, let's say, number of tokens n equal to 5. Then you have 5 queries and 5 keys, which means your attention score or attention weight matrix will be 5 by 5. So basically it is scaling as n square. So if you have an image of height 80 and width 80 and patch size 16 by 16, you totally have 5 patches along the height and 5 patches along the width, which are 25 patches. If you increase the image size from 80 to 160, I mean, total number of pixels are becoming 4x, your attention complexity actually becomes 16x, because you have 10 tokens along the height row and 10 tokens along the height. So totally now you have 100 tokens as queries and 100 tokens as keys. So 100 queries are attending to 100 keys. So 100 by 100, 10,000. So 625 order of complexity will become 10,000. So 4x increase in number of pixels result in 16x increase in complexity. So 16 is the square of 4. This is the problem with vision transformer. So what vision Swin transformer does is it basically limits its attention to some local windows. So what I mean by local window is attention is not constructed by considering all these patches at once. It will construct a local window which may look like this. Something like, let's say this is a window of 2 by 2 tokens or 2 by 2 patches. So inside this window only attention is calculated. Then inside this window attention is calculated. Inside this window it's calculated like this. So we will see why this leads to a better computational efficiency, because in the paper they claim that they have linear computational efficiency. We'll see why it is linear and not quadratic. And we'll also see some issues by converting attention from global thing into a local thing. So this Swin transformer paper, it had 38,000 citations. And one of the biggest claims that they are making is, we know that transformer has now become the backbone of NLP tasks. And CNN is considered to be the backbone of computer vision tasks. Transformer is still not like a general purpose backbone, but they are saying that based on what they show, you can imagine transformer to becoming a general purpose backbone for computer vision. What do we mean by general purpose? Any tasks, whether it's classification, image, object detection, or segmentation. For any of those tasks, it is possible to consider transformer. And they accomplished something really, really amazing. So for all the 3 tasks for image classification, they achieved 87.3% top 1 accuracy. This was actually close to state of the art or the state of the art at that time. Then on object detection, they achieved 58.7 average precision for box average precision, and for mask average precision 51.1. We don't have to go into the details of how exactly average precision is calculated, I can share some lecture videos of my own where I have explained in detail what is average precision, what is mean average precision, etc. on another data set. And for semantic segmentation, they achieved mean IOU. IOU means intersection over union, which was better than the state of the art. So in short, they achieved or surpassed state of the art. Then they showed that attention complexity can be reduced from being quadratic to being linear. And they also showed that for broad level of tasks, because you can use this model, it can be considered as a general purpose model. One more important thing is the hierarchical nature of the vision. So hierarchical nature meaning, we'll come to this when we discuss the architecture, but vision transformer considered in all the transformer blocks 16 by 16 patches. So if the image had a resolution of 160 by 160, there were 10 patches along the row and 10 patches along the column. Here, on the other hand, patch size was different in different blocks of the transformer. So because of this, it could construct something called hierarchical feature construction. This is universally seen. I don't know how many of you know about UNet architecture. So if you search, if you look at this UNet architecture, which I had discussed in detail in one of the lectures, not part of this series, but separate. But here you can see that they are considering features of high spatial resolution and less channel dimensions. Then in the next layer, they are considering lower spatial resolution and more number of channels. Then lowest spatial resolution and even more number of channels, and then even lesser. So basically, they constructed UNet in such a way that features at different scales or different resolutions were used for making the final masking. UNet was primarily used for image segmentation. It is still being used in models like the equivalent of UNet architecture is still being used in models like stable diffusion. We'll see that towards the end of this series. But coming back to the paper, what they did, this was the architecture. Now, architecture is quite complex. You can see that. Okay, first of all, let me draw a line to distinguish two things in the architecture. Everything to the right of this is figure B. Okay, so this is not a continuation. What is shown here over here is this Swin transformer block, Swin transformer block, block. So there are 4 stages. In each stage, there is something, either a linear embedding or a patch merging. We'll discuss what those things are. Then in each stage, there is one Swin transformer block. One Swin transformer block consists of 2 things. One is a transformer block consisting of regular window. So this WMSA is regular window based multi-head self-attention. Second is something called shifted window based multi-head self-attention. So among this whole thing, the most difficult thing to understand, in my opinion, is this small thing. This is the most difficult thing, and this is where you should pay your most attention to. Now we have to understand a few things. First is, how do we construct windows? Second is, how do we do, let's say, position embedding? Then there is a question like, how does window-based multi-head self-attention work? Fourth is, how does shifted window work? Fifth is, let's say if this was a classification task, do we use a CLS token or is it something else? And how exactly is hierarchical features coming into picture? So if you can understand, or if you can answer these questions, you basically understand the Swin transformer architecture. So we will go through it sequentially. Figure A and B. Yeah, of course it's confusing. I'm yet to go through the figure, right? So figure A is the architecture. Figure B is the expansion of the Swin transformer block. This thing is expanded over here, and that consists of 2 things. But we'll come to that. I have not explained the architecture yet. But we have to understand how do we construct windows from patches? Because in vision transformer we had patches. Here you had patches and windows. how do we do position embedding? How do we construct these transformer blocks? Because if you look at the transformer block, if you zoom in, it's mostly similar with any other transformer block we have seen. You have layer normalization, followed by multi-head self-attention, followed by residual addition, followed by another layer normalization, followed by multi-layer perceptron. This we know, but only difference is now this is window multi-head self-attention and this is shifted window multi-head self-attention. Whatever output comes out of here, of the block number 1, so this we can call as block number 1 and this is block number 2. This output goes into the block number 2 as input. So we know these individual elements. We know what is MLP, what is linear layer normalization, what is multi-head self-attention, but we don't know what is window-based multi-head self-attention. How is it implemented in practice? We definitely don't know how does shifted window multi-head self-attention work, and we really don't know how it is implemented in practice. Now, I want to bring your attention to a few things. Let's start from the initial part. What is this image? Image is an RGB image with a certain height, certain width, and 3 channels, RGB channels. First thing that is done is this image is converted into patches, just like vision transformer. So an image of H, W, and number of channels equal to 3 is divided into spatial patches of dimension 4 by 4. So every patch, so in vision transformer, what was the patch size, if you remember? Do you remember the patch size of vision transformer paper used in the vision transformer paper? It was 16 by 16, right? The paper title itself was an image is worth 16 by 16 words. So it was 16 by 16 patches. Here, the patch size is 4 by 4, which means how many patches are there in my image total? In my image, in this case, how many patches are there totally? The total number of patches will be, I have H by 4 patches along the height multiplied by W by 4 patches along the width, because each patch is 4 by 4. So total number of patch will be H by 4 multiplied by W by 4. Now, if I were to represent every single patch by a vector which is constructed by concatenation of the values in my input image. My input image is this, okay? I have H as the height, W as the width, 3 is the number of channels. If I wanted to convert a patch into a vector where I'm just doing flattening operation, no other operations doing, what would be the dimension of my vector? How many numbers will my vector contain? I'm not talking about, yes, number of dimensions. Yes. Basically, my question is, let's say I'm considering every single number which is there in the input image. Okay. I'm not removing any number. I'm not adding performing any other operation. The only operation I'm doing is patching and flattening. At the end of it, I want every single patch represented as a vector of certain number of dimensions. Like that, you guys said I have H by 4 multiplied by W for these many patches. Now my question is, okay, I have these many patches and each patch is like a vector of certain number of dimensions. How many dimensions will my vector have? No, I just want a number. I want a mathematical number because you have all the information available for you here. I just want a number. What is the number of dimensions that my patches have? So whoever said 48, why is it 48? So think about this. What is one patch? One patch is 4 by 4. But then I have 3 channels, RGB. Okay. So every patch has this much information. It has spatially 4 by 4 pixel worth of information. And channel wise, it has 3 channel worth of information. So the total number of pixel wise information for every patch is basically 4 times 4 times 3, which is 16 times 3, which is 48. So if I were to not take pooling or any operation like that, if I was simply flattening it into a vector, then I will have 48 dimensional vector corresponding to every patch. So now I have H by 4 patches multiplied by W by 4. So total number of patches is this multiplied by 48. This will be the total, representation of my whole image after patching and converting it into a concatenated vector. So that is the first thing that you should notice here, h by 4 multiplied by w4 multiplied by 48. So this 48 is the dimensionality of every patch. This is the number of patches along the height. This is the number of patches along the width. So these two, product of these two is the total number of patches. This is the total number of features in every single patch. Now what is done is, so that is what is done in the patch partition. So this, now patch partition does this. And now you also understand this. Now let's look at what does linear embedding do. What linear embedding does is, now you have a 48 dimensional vector. Linear embedding converts it into a C dimensional vector. C, I think they are using the character C to just denote channel dimension or something. But I don't think C was a good choice of dimension, good choice of variable. They could have picked something else. But anyways, whatever it is, 48 is converted into C. How do you convert 48 dimensional vector into a C dimensional vector? You use a matrix, right? You use a weight matrix, which basically looks like a linear projection. How does linear projection look like? In the layer number 1, you have 48 nodes. Layer number 2, you have C nodes. C can be whatever, and you have a fully connected network here. And the value of these connections are basically the weights. The dimension of the matrix will be 48 by C, which means the input dimension is 1 by 48. Output dimension is 1 by C. So that is what this linear embedding does. So linear embedding converts 48 dimensional embedding into a C dimensional embedding. So by the time things come out here, this guy, what is going into the Swin transformer block will be h by 4 multiplied by w by 4 multiplied by C. This is the total number of patches. This is the dimensionality of each patch. Now, within the Swin transformer block, usually we know that dimensionality of the token is retained. Tokens do not change their dimensionality as it passes through the transformer block. Exact same thing happens here also. We are yet to look at the detail of the Swin transformer block. And here the reason why they have put multiplied by 2 is because Swin transformer block, there are two blocks. One is the regular window block and second one is the shifted window block. So please note this x2. It means just the block is repeating 2 times. Here the block is repeating 6 times. 6 times meaning regular, then shifted, then regular, shifted, like that. I have no idea how they came up with this 6. I can imagine why they came up with 2. 2 makes sense. 6 is probably empirical. Anyways, so what comes out of the Swin transformer block is also of the exact same dimension. Swin transformer block does not change the dimensionality. It simply converts every tokens into context vectors. So yeah, how many context vectors do you have here at the output of the Swin transformer block? Total number of context vectors, h by 4 multiplied by w by 4. Basically, that many context vectors are there. Each context vector is of dimension C. Now, here something is done called patch merging. So before we go through patch merging, let's just discuss what is going into the input. So the output that comes out of the stage 2 Swin transformer block is h by 8 multiplied by w by 8 multiplied by 2c, which means what should go in here? What should be the input? Input should be the same, right? Because Swin transformer does not change the dimensionality of the token. So input should be the same as h by 8 multiplied by w8 multiplied by 2c. So from that, we can imagine what patch merging is doing is something where these tokens are converted into this somehow. We'll discuss how. But first tell me, are the number of tokens increasing or decreasing after patch merging? Number of tokens are obviously decreasing because total number of tokens here was HW by 16. Here it is HW by 64. So total number of tokens became 1/4, right? But the dimensionality of every single token became 2x. From C, it became 2x. This is kind of analogous little bit to what CNN does, because you know that in CNN also, as you go from layer 1, layer 2, layer 3, the spatial dimension reduces and channel dimension generally increases. You might remember that from vision language nano VLM lecture also. In general, spatial dimension reduces as you go from layer 1 to layer 2 to layer 3. Channel dimension increases, and you can see that that is what is happening. So spatial dimension, height is reduced by half, width is reduced by half, channel is increased by doubled. I mean, increasing by 2. In the stage 3 also that is happening. Stage 4 also that is what is happening. So here it is h by 16, w by 16, 4c. Here then 4c becomes 8c, h by 16 becomes h by 32. Now, what we have to understand is what exactly does patch merging do to make this happen. So what patch merging does is, if you have, let's say, 4 neighboring patches, I call this as patch number 0, 1, 2, 3. And let's say the dimensionality is C, channel dimensionality is C. What patch merging does is a simple concatenation where all of these things are converted into a single token. Okay. Let me not put any number here, a single token, but if I'm just doing concatenation, what should be the dimensionality of this token? Channel dimensionality of this token? It should be 4C. So what happens is, here I had 2 by 2 patches. So this is not a pixel, it's a patch, please remember. So this 2 by 2 patch with C dimension, if I concatenate it into just a single patch dimension, my channel dimension will become 4C. Now think about my total image. My total image won't be just having 2 by 2 patches. My total image may have how many patches? Initially it had h by what? H by 4 patches. Here I had w by 4 patches. And then this was C. Okay. Now what will this become? Every 2 by 2 grid of patches will become just one patch. So h by 4 will become what? What happens to h by 4? See, along the height, 2 patches are getting merged into one. Along the width, 2 patches are getting merged into one. So height will get reduced by half, width will get reduced by half, meaning number of patches along the height gets reduced by half, number of patches along the width get reduced by half, right? Because every 2 by 2 patches, area of patches are getting converted into one patch. So what will happen is, this will become w by 8, just like how 2 by 2 became just 1 by 1, w by 4 will become w by 8, sorry, the h by 8. This will become w by 8, and this will be what? What will this be? Why do you say 2C? It should be 4C, right? Because every 4 patches are getting converted into one patch effectively. So this should be 4C. Because think about it. Here, let's just put some value for h. Let's say h is 16. If h is 16, this was 4 by 4. Okay. And 4 by 4, 2 by 2 became 1 by 1, which means 4 by 4 should become 2 by 2, correct? So this will be 2 by 2. And what is h by 8? H by 8 is 2 by 2. So in the process of this 2 by 2 becoming 1 by 1, your C became 4C. Why? Because you are simply concatenating these 4 items of each C dimension one after the other. So C plus C plus C plus C, 4C. So this will be 4C only. The channel dimension will be 4C. Now, you might still be wondering, but we did not discuss 4C. We were in the architecture, you did not see 4C. In the architecture, actually, you are seeing 2C. How do you get 2C? How do you go from h by 8, w by 8, 4C to h by 8, w by 8, 2C? How do you do this? How do you go from this to this? What is happening here? You have h by 8 multiplied by w by 8 number of patches. Every patch had a dimensionality of 4C. Essentially, you are reducing the dimensionality, right? you are reducing the dimensionality of a token. Number of tokens reduced by 1/4. Now every token, every token is now reducing in spatial dimension also from 4C to 2C. How do you do that? Simple, linear embedding. Same thing, exact same thing what we did here. Whatever converted 48 dimensions to C dimension, same thing you can do here to go from 4C dimension to 2C. So you will have a linear projection layer where the first layer number 1 is of 4C number of nodes, layer number 2 is 2C nodes, and you will have fully connected connections going. And then that weight matrix of 4C, 2C dimensions will convert the channel dimension from 4C to 2C. Here, don't imagine an image. Just imagine you have h by 8 multiplied by w8, that many number of tokens. Each token is of 4C dimension. If you want to convert those tokens into 2C dimension, simply what will you do? You will simply use a linear projection. Exact same thing is happening here. So this is how you go from the h by 4 w by 4 C to h by 8 w by 8 2C. And this step with this intermediate 4C concatenated layer is what is happening in the patch merging. And now look at what has happened. You originally had how many tokens? H by 4 multiplied by w by 4 tokens. But now you have only h by 8 multiplied by w by 8 tokens in your image. So the number of tokens are now decreasing, right? So this is where the hierarchy, and here h by 8 tokens, w by 8 tokens. Although in each token you have now more information because you have 2C dimensions. So you can potentially add more information, but you have only less tokens. So you are looking at your whole image from a little bit more, I would say, abstract perspective, because the less number of tokens you have to represent your image, you are making it more and more abstract. If you remember from convolutional neural network, if your spatial dimension decreases tremendously, the image will become more and more abstract. So similar thing is what is happening here. And same thing repeats. In this patch merging, first h by 8, w by 8, 2C. After concatenation, what will this become? Just after concatenation, what would be the dimension of this? You are concatenating every 2 by 2 patches, which means h by 8 will become h by 16. W by 8 will become w by 16. 2C will become initially 8C. But then you do a linear projection from 8C to 4C such that over here, after linear projection, it will be 4C dimensional. Each token will be only of 4C dimension. It will not be 8C. So that is the input that goes into the stage 3 Swin transformer block. That is the output that comes out of the stage 3 Swin transformer block. And in this paper, they had these 4 stages, but in their ablation studies, you can see many different variants, but this is the best variant that they found. So this partially explains some things. I think partially you understand why there is a hierarchical nature, perhaps because the spatial dimension in terms of number of tokens is reducing, channel dimension is increasing. So in some blocks, in some stages, you are looking at more finer features. In some blocks, in some stages, you are looking at more coarse features. And then you are combining all of those to make your final prediction. So this is where the hierarchy comes. But you must have a question. Okay, patching also, I hope you understand. Patching part is simple because patching part is you just divide image into patches. If we concatenate h by 8, should it go to h by 4? No, we are concatenating. We are splitting. See, what we are doing is this is 2 by 2 by C. Now, if I concatenate this along the channel dimension, each of them will be one patch, and every patch will now have a dimension of 4C because you have 4 patches here to concatenate along the channel dimension. Now, like that, if I look at every 2 by 2 patch sets, so this is a 2 by 2 patch set, another 2 by 2 patch set will be here, another 2 by 2 patch set will be here. This will become like a 1 by 1, basically one patch of 4C dimension. This will become one patch of 4C. This will become one patch of 4C. Essentially, width will get reduced by half. So h by 4 will become h by 8. Height will become half. Similarly, width will also become half. So basically, h by 4 and w by 4 will become 1 by 8. C will become 4C. We are taking 2 by 2 patch merging. Is this a standard? I don't know why it should be a standard or whether it's a standard. I don't know the answer to either of that. I'm sure they might have tried maybe merging of more number of patches. Maybe the reason why they went with 2 by 2 patches, if you really want to if you really want to reduce the dimension spatially after h by 4 by h by 4, let's say you had to go to h by 6 and w by 6, something like that. I don't think it will be possible, because how many can you merge along the row? Minimum number of things you can merge along the row is 2, right? Minimum number of things which you can merge along the column is also 2. So if you do that kind of merging, the minimum patch merging is basically a set of 2 by 2 patches. So I think they are just doing that minimum. I'm not sure if they tried merging a set of 3 by 3 patches. I have to check their ablation study, or merging a 4 by 4 patch. But you agree that you can't merge less than this in a symmetric way, because if you want to do it in a symmetry, width and height symmetry way, minimum is 2 along the width and 2 along the height. Now let us look at the, so you understand patches. Windows I have not explained yet, but I'll come to that. Now, the two things you understand from this is, you understand that image is divided into patches. Patches are converted to tokens. Tokens are, number of tokens reduced from one stage to another, and dimensionality of the tokens increase from one stage to another. And that is what is essentially creating the hierarchical nature. So these two you understand, but this is now remaining. What are windows? How are they created? Where is the position embedding coming into the picture? What is window-based multi-layer self-attention? What is shifted window? Are we having CLS token? How is finally, let's say, classification done? We will not be discussing detection yet or segmentation yet. Let's just stick with classification. How are these things done? So let's now move on to those aspects. Example with number of tokens. Yeah, for sure. If you have a 224 by 224 by 3 image, and let's say your patch size is 16 by 16, then what is 224 by 16? 224. 14. So basically, your input image will be converted to 14 by 14 patches, each of dimension. So if your patch is actually, let's not pick 16 by 16 because that is done in Vision Transformer. In this paper, it's 4 by 4. So let me keep it consistent. So 4 by 4 means you will have total 112 by 256 by 56 by 48. This will be your initial patch dimension. And let's say my input embed dimension is, let's keep it as 16 initially. Then after the linear projection, this will become 56 by 16. Now this 56 by 16 will go through stage 1. And what comes out of stage 1 is also 56 by 16. Now I need to do patch merging. Initially, after patch merging, this 56 by 16 will become 28 by 64. But then this 64 is projected into 38 dimension. Then it will become 28 by 32. And then this goes through stage 2. So this is what is the input into stage 2. What comes out of stage 2 is also the same, by 32. And then happens patch merging. So after patch merging, this will become 14 by essentially 2C. I'm skipping the 4C step. So this will become 64. And then this goes into stage 3 and so on. We are yet to discuss after all of this, how is the final representation used for classification, that we will come to. But essentially, this is what happens. This complexity part I showed you. Okay, now, I don't think I showed you. Well, let's discuss the complexity. Why do they say Vision Transformer is quadratic and Swin is linear? Vision Transformer being quadratic, you understand. Now let's focus on Swin. In Swin Transformer, they do not construct attention between every single patch. So here, look at this. You have 224 pixels along the width and 224 along the height. And each patch, let's say if it is 16 by 16 pixels, I know that 16 by 16 is used in vision transformer, but let's just keep it that way. There are total 14 by 14 patches, right? 14 patches along the width and 14 patches along the height. If it was vision transformer, you will have total number of tokens equal to 14 multiplied by 14 equal to 196 tokens. In vision transformer, in this, according to this example, you will have 196 tokens, correct? Which means the complexity will be proportional to n square, which is 196 square, if this was a vision transformer. In Swin transformer, however, you construct something called as windows. So this red color thing is a window. In that window, in this one window, you have 7 by 7 patches. So now, if attention is constrained within this window, inside those window, how many tokens do I have? What is n inside this window? N equal to 7 times 7, right? There are 7 patches along the width, 7 patches along the height, 49 tokens or patches are there in my window, which means my attention complexity will be proportional to 49 square. Now let's keep this all in terms of some variables so that I can show you the linear and quadratic complexity. Let's start with vision transformer. Width, height, then patch size is P. Number of tokens equal to width WH by P square. Complexity of attention is order of n square, which is WH the whole square by P raised to 4. This is the order of magnitude. And if I just want to say it in terms of image size, basically complexity is quadratic with respect to image size in terms of number of pixels, right? This is clear. Now let's look at Swin transformer. In Swin transformer, let's say width is W, H is height, and patch size, let's keep it, let's say P or 4. Let's say patch size P equal to 4. And window size is M by M. Okay. Totally. And M by M is like number of patches along the width and number of patches along the height in one window. So by that logic, for one window, to calculate the attention, the number of tokens n equal to m square, correct? Because every window is consisting of m times m, that many number of patches or that many number of tokens. So for one window, I have total m square number of tokens. Now, that means the order of magnitude of attention complexity is again order of n square because I have n queries and n keys. And what is this? This is m raised to 4. But this is for one window. Like that, how many windows do I have? How many total windows do I have? In my whole image, how many windows are there? First, let me calculate how many patches are there. The number of patches, H by P multiplied by W by P. These many patches are there. So this is, let me keep it separate. Along the height, I have H by P patches. Along the width, I have W by P patches. Now, we said that one window along the width has M patches, which means how many windows are there along the width? This number divided by M. These many windows are there along the width. How many windows are along the height? These many windows are there along the height. How many are there? How many total windows are there? Product of these two. So total number of windows in my image will be HW divided by P square M square. This is the number of windows. How do I call this? Num windows. This is complexity per window. So then what is the total complexity? Total complexity will be complexity per window multiplied by number of windows. So M raised to 4 multiplied by HW divided by M square P square. This will turn out to be M square HW by P square. This is the attention complexity for the whole image in case of window based self attention. Now, is this linear or quadratic? It is linear because HW is the total number of pixels. So if you compare this with vision transformer, for vision transformer, it was HW the whole square. So if you compare the complexity, as the number of pixels double, the complexity here will become 4 times. Here, as the number of pixels double, total number of pixels is product of H and W. As the number of pixels double, the complexity does not becomes 4 times, it only becomes 2 times. But it becomes 2 times with a linear factor in front of it. But essentially, the scaling is linear. It's not quadratic. That's the important thing, right? So this is what I wanted to show you in this figure. I'll just show you quickly, but I have explained it already anyway. So in Swin transformer, what they took is every window is 7 by 7 patches, and one token is basically equal to 1 patch. So every window will have that, for that reason, 49 tokens. And if there are 49 tokens, then attention complexity per window is simply n square, which is 49 square. And you have to multiply that with total number of windows. How many total number of windows will you have? Total number of windows will be roughly total number of patches along the width divided by number of patches per window. So it will be W by 7 times P. So here I should ideally put P also, but I was ignoring P. So ideally the divided by P square will come, and along the height H by 7P. So total number of windows will be WH by 49 P square. Multiply that with the complexity per window, which is 49 square. You will get 49 WH divided by P square. So that is what I have written here, 49 WH. I mean, P square, when we are talking about order of magnitudes, you don't have to say these things. You just say it scales with WH. It scales linearly with WH. So this is the one of the biggest advantages of Swin. Now let's see, we discussed how the linear, I don't think I mentioned it here. Okay, windows I mentioned, right? So now you understand how windows work and how linearity comes. And this, let me put as 0th item. So now out of these things, you understand how patching works, how windows are there for making things linear, how hierarchy is coming in the from stage 1 to stage 2 to stage 4. And now we need to focus a little bit on these things. Okay. So first, let's discuss a little bit about one more thing, just the idea of non-overlapping window. Window is different from patches. Patches were non-overlapping, of course, but pixels form patches, patches form windows, windows form the full image. Okay, just remember that. So maybe 4 by 4 pixels form patches. Then okay, if I write it as pixels, 4 by 4 pixels form patches, 7 by 7 patches form windows, and then depending on the image resolution, something by something, let me call it as W by PM multiplied by H by PM. Those many windows form the full image. In Vision Transformer, we stopped at this stage. We just had patches. We did not have windows. The patches themselves created the full image. Here, that's not the case. Okay. Because window-based attention, is it weaker at capturing global attention, global context? It is definitely weaker because full global attention, full patches are not considered, but it cleverly fixes it. I'll show you how it fixes the issue. That's the whole reason why there is a fixed, there is a shifted window. So that is where I'm coming next. So you see that, if attention is restricted only to a window, okay, let's say I have, let me go back to this image. Let's say I have a patch here and another patch here, and I have another patch here. So A, B, and C. Is there an attention between these two? Or if yes, what is that value? Let's call it as alpha BC. If B is query and C is considered as key, what will be alpha BC? right? But what should be the value? It will be 0 here. The reason is in Swin transformer, attention scores are constructed only between patches belonging to the same window. B and C, although according to the image, they are geometrically very close to each other, and perhaps there should be good attention between them. In Swin transformer, it does not care about the geometric proximity. It only cares whether those patches belong to the same window or not. So B and C, although they are very close to each other as a query key pair, the attention score between them will be 0. Alpha B C will be 0. However, B and A, although they are far away patches, the attention between those two will not be 0. So alpha B A will not be 0. There will be a finite attention between these two. Then you might have a natural question. Isn't this a problem? Because how come attention between B and C being 0? This is not very helpful, right? Of course, this is helpful to reduce the number of computations, that you understand. Computations became linear. So for bigger and bigger resolution images, this is good. But then, of course, this patch may have some dependency on this patch. So some long range dependency has to come, right? B and C, B and this patch number D, there should be some way for them to interact. How does it do that? This is, in my opinion, one of the worst written parts in the paper. Their choice of words are very frugal. It's very poor. And I struggled the most to understand exactly how it works. Then the only thing which helped me is I opened Figma and I tried to create a diagram of myself. And when I created it, then everything fell into its place. So I'll show you that figure basically. I'll first show you the figure and then I'll come back to all of this. So don't get frightened by seeing this. Let's just keep it simple. Okay. 0, 1, 2, 3. They are the window ID or patch ID. What are those? 0, 1, 2, 3 are window ID or patch ID. Window ID. They are 4 windows. A, B, C, D are patch IDs. Now we know that in Swin transformer there are 2 transformer blocks repeating again and again in alternately, regular window and shifted window. So in regular window, creation of window from your patches are very straightforward. If you have 14 patches, you will have first 7 along the width forming the first windows, 7 to 14 forming the second window. So it's very clean like this. Now A and B are close to each other. A and C are close to each other. A and B are 2 patches belonging to with the same window ID. Window ID of A and window ID of B are 2. Window ID of A and window ID of C are different. Window ID of C is 0, which means attention between them in regular window in the block number 1, it's null. However, when it comes to shifted window, what happens is imagine that your original window was here. Let me just fill some color. Imagine your original window was here. This window is shifted by m by 2, where m is the width of the window. So by half of the window's height and half of the window's width, it is shifted. And the shifting is done in an interesting way. So if this gets shifted by m by 2, essentially all windows get shifted by that. So now the windows will be over here, over here, over here, here, like that. So essentially, to cover the whole image, right? How many unique windows do you need? Earlier, to cover the whole image, you needed 4 unique windows. Now, how many unique windows do you need to cover the full image after shifting? Forget the numbers. Ignore the numbers. Just follow the logic that I'm just mentioning. If you shift the window by m by 2 or width of the window by 2 by that factor, just look at this picture that I'm showing in front of you. Based on that, how many windows do you need? How many unique windows do you need to cover the whole image? You need 9 windows, 3 by 3. But this window, there is a problem. Firstly, some only one of these windows are looking like the previous window. So this window number, which I have ID'd as 3, that window looks fine because it has 4 patches inside it. But window in which I have put ID 1 for now, ignore the ID, but this top middle window, this guy has only 2 patches inside it. This corner window has only 1 patch inside it. The rest of the things are empty. Maybe then what you could do is, a logical thing which you could do is, you could do padding. You could pad some empty, zeros or something here. And then while constructing attention, you can say that if it's a padded patch, if it's a patch created during padding, the attention score between that patch and this should be 0. Between that and this should be 0. Between that and this should be 0, because padding is anyway something that you add extra. But to mathematically implement this, you could technically add padding so that the span of those 9 windows and the total span of your image are same. And then you say this is your window number 1 or 0. This is your window number 1. This is your window number 2, 3, 4, 5, like that up to 8. You have total 9 windows. And then you say that the local attention is constricted only to window number 0, or only to window number 1, or only to window number 2, and so on. In this, for window number 4, there is no problem because it has 4 patches. But for rest of the windows, the number of patches are less. That is one problem. Plus total number of windows increased. When you go from 4 windows to 9 windows, it's like what? 2.25x, right? Your total computation cost increases by 2.25x. Plus, it's not a clean thing because number of patches per window is not 4 anymore. In the previous regular window, number of patches per window was 4. So every window had 4 patches. Here, this window has only 1 patch. This window has only 2 patches. This window has only 2 patches. This has only 2. Only one window has all the 4 patches. So this is also a problem. So what is actually done in shifting is called as cyclic shifting. Cyclic shifting meaning whatever comes out of here is assumed to be come back up here. So if you are losing, essentially from 4 patches inside this window, only 1 is retained. Remaining 3 are going out of the frame. Then you are assuming that those 3 which are going out of the frame is rolling back and coming back here with the same ID. So I'm not talking about pixel values. I'm just talking about window IDs. Okay. Pixels are remaining the same. Picture is not rotating or anything. Just the window ID I'm talking about. So this window will have an ID of 0. This window will also have an ID of 0. This will have an ID of 0. This will have an ID of 0. And now if you look at this window with ID 0 altogether, it will have total 4 patches. I'll repeat. So what is done is, if you consider what has happened to this window after shifting, originally it had 4 patches, but now it has only 1 patch. But it will be great if window number, the top left window has 4 patches. It will be great because then computation will remain very similar to regular window. Regular window computation was easy because every window had 4 patches. Then you could construct attention score between 4 patches as query, 4 patches as key. Here, after shifting, the problem that has happened is some windows have only 1 patch, some have only 2, some only 1 window has all the 4 patches. Now, how do you fix this? Is padding a good answer? No, padding is not a good answer, mainly because if you pad, then you are adding some unnecessary extra computation. Instead of computing with 2 by 2 windows, you will end up computing with 3 by 3 windows. So that is one thing. So here what is done is something called as cyclic shifting, where let's say I have a window here. Okay. And if I shift it by half of the height up here, and whatever comes up it's like a snake game. You might have played this snake eating apple game, right? There, if the snake disappears up here, it comes back up from the bottom, right? Similarly, if snake disappears from the left, the snake comes back from the right. And if snake disappears like this in the corner, it comes back from here also, right? I hope you understand what I mean by that. So just like that, these walls, just imagine that if I am shifting the window up here, or for example, if I had a window like this, if I am shifting it up here, whatever goes out will come back from the bottom. If window is shifted to the right, whatever goes out from the right will come back from the left. If something is shifted to the left and right and to the corner, so here I am shifting this window essentially ended up reaching here. So I had a left shift, I had a top shift, then I had a top left shift essentially. So which means something will come out from the right because there was a left shift. So the 0 is coming out, it is appearing here also. Because you are shifting a little bit to the top also, a 0 is coming here. So to repeat, let me repeat once more. How do you go from here to here? You have to do top shift. You also have to do left shift. When you do top shift, what happens is, let me just draw here. And if this ID was, let's say the ID of this green color thing was 0. Okay. When I do top shift, these two patches will be 0, 0, and two patches are going up, which means this will become 0 and this will also become 0. Logic is clear, right? Then I have to do a left shift. When I do a left shift, this guy who was at 0 position will come here. And this guy who was at 0 or with ID 0, that will move here, which means whatever is going out here as 0 will reappear here as 0. Similarly, this guy who was having ID 0 would have gone here, and this guy with ID 0 will shift to the left. And what is gone outside, this 0 will come back here from the right. So that way, at the end of the day, by the time you do the shifting, and if you track the patch IDs, the green patch ID, if the original patch ID of this green color thing was 0, finally, this patch will have a window ID of 0. This patch will have a window ID of 0. This will have a window ID of 0, and this will have window ID of 0. And same thing happens to the rest of the patches. So you can follow this logic to understand that finally what will happen is these 4 corner patches will have same ID. This 2 patches over here at the bottom and these 2 patches at the top, they will have the same window ID. These 2 patches on the left and these 2 patches on the right will have the same window ID. Now look at what's the magic that is happening. Originally, I had, if you were to consider this if you were to consider these 4 patches, they never interacted with each other. Why? Because their window IDs were completely separate. Now, if you consider the same 4 patches, right? Now look at the same 4 patches. The ID of all those patches are now the same. The window ID of those 4 patches are 3, which means the patches that were not able to interact with each other or not able to attend to each other before in the regular window, they are now able to attend to each other in the shifted window. In the regular window, these patches were geometrically close to each other, but they were prevented from attending to each other because their window IDs were different. In the shifted window, those 4 patches, they are geometrically close to each other and their window ID are also the same. Now look at the next set. In regular window, if you were to look at this patch, this and this, it will be great to construct a long range dependency, right? It would have been great to construct a long range dependency, but because these happen to be in different patches, different windows, these 4 patches, there was no possibility of constructing a dependency between them because there was no attention score between them. But now look at shifted window. In shifted window, those 4 patches are far away from each other, but a long range dependency is constructed between those patches because now they have the same window ID. So this is how shifted window attention will help different sections from your image to interact with each other by the combination of regular window and shifted window. Not because in one single window interaction between every single patches are allowed. That is not allowed. But by combining regular window first and then with shifted window, this indirectly allows for faraway patches also to communicate with each other. And that is the reason why Swin transformer performed as good as it performed, while maintaining the linearity of the complexity scaling with respect to the image size. So now from this eye, if you, with this idea, if you look at, yeah, you can think of it as rolling on a cylinder. There are many ways to visualize this rolling, but basically it is like whatever goes out on one end comes out on the other end, instead of having like an infinite canvas or anything, right? The whole canvas is your image. So that is the idea behind window-based self-attention. Now there are a few more details which I want to explain. So let me show you two equations first, and then I'll explain everything else. So focus on just the regular window. Regular window is this block number 1. It's not called as regular window block. The only reason why I'm writing regular window here is because the multi-head self-attention is regular window based. So this is not called as regular window block for just today's explanation purpose. I'm calling it as a block with regular window. In that, your windows are like this. There is no shifting. How do you calculate attention score or attention weights? Attention is softmax of query times key transpose divided by square root of D. So you are considering ith query and jth key. You are taking dot product between them, square root of D softmax. But there is one extra term here, which you have never encountered in this course, at least yet. This extra term is the term that provides position information. This is called as relative position bias term. It's not called as position embedding. In Swin transformer, they don't by default, I mean, at least the one that is written in the paper, they don't do position embedding, but rather they add something called as position bias. I will explain what this position bias is. But think about the main difference between vision transformer and Swin transformer now. In vision transformer, where is position information added? At what point is position information added? It's added before transformer block. It's added at the tokenization step. You have patches. Patches are converted to tokens. To those tokens, you add the position information, correct? But here, look at where the position information is added. It is added within the multi-head self-attention, just before calculation of the attention weights. Now, this position term is a learnable term, so it's a learnable parameter. Now, this is for the regular window. Now, in regular window, all of these ij pairs come from the, let's say it's either from pixel patch number 0 to patch number 7 or patch number 6 along the row, and patch number 0 to patch number 6 along the column. So this ij, all of these ij pairs will come from the same window of the regular window. But if we apply the same logic in shifted window, that there will be a mistake. Why? Because in shifted window, patch number 0 to 6 do not all belong to the same window, because after shifting the window, this window would have shifted like, let me just delete this. If this is my window, this window would have shifted like this, which means in my shifted window, I cannot simply follow, just randomly take dot product between Qi and Kj, or I cannot randomly do this calculation and expect to get good weights and bias values. Good attention weight values. But what is done instead, in shifted window block, the formula is slightly different. There is one additional term called mask ij. Now, what does mask ij term do? Very, very simple. Mask ij value, the value of this term will be 0 if the patch I and patch j have the same same dash. The value of mask ij will be 0 if they have the same window ID. Basically, here what are tokens? Tokens are patches. If two patches belong to the same window, we don't need to do any masking or anything. Let them create attention between them. So if I and j are the IDs of or indices of two patches whose window ID happen to be the same, then the value of mask ij token is 0. Otherwise, if the query I and key j, which are two different patches, if they have different window IDs, then your mask ij value is negative infinity. Can anyone tell me why negative infinity? I mean, in Python, we can implement this by saying minus inf, or basically a huge negative number. Why? Because when you take softmax of a large negative number among a series of numbers, that value will be close to 0. That way, alpha ij, which is the attention score between query I and key j, will be 0 or close to 0, very close to 0, if the mask token is negative infinity. And if attention score will be, mask is not multiplied, it's just a number that is added. Look at this, it's just added. Please don't, this mask term is slightly different from the masking that is done in, let's say, mask dropout or something. Here is just a term that is added. So mask, yes, mask is one way to implement the shifted window. So this is just an implementation detail. You have to know this, because otherwise in the next lecture, when we actually implement this, you will not understand why is this random mask term coming. So mask term is a nice mathematical, clever way to make sure that, if you have a large negative number, it will be, the numerator will be erased to minus infinity. Denominator will be erased to minus infinity plus bunch of other numbers, which means the softmax value corresponding to token, the query I and key j will be 0, because query I and key j do not have the same window ID. So this is how, in practice, masking is applied to prevent patches from two different window IDs from interacting with each other. Okay, so that being said, what else do we need to discuss? Let me just go back to our list of things. So you understand patches, you understand windows, you understand that there is something called as relative position embedding, but it's not complete. So this is next what I'm going to discuss. It's not position embedding, it's position bias. Here we are not adding anything to the token embedding. We are adding a bias at the query key inside the multi-head self-attention. You understand window-based multi-head self-attention, because it's exactly same as self-attention, except it's constrained to windows. Bias term is added, mask term is not added. Inside the shifted window multi-head self-attention, there is bias term as well as the mask term. Mask term is minus infinity if two tokens have different window ID. It is 0 if they have the same window ID. Now, two more things we have to discuss for our understanding to be almost complete. One is, okay, position bias. I mentioned that it's a learnable term, but there is one more detail. And then about classification token. So after the context vector comes out of here, it's a 8C dimensional context vector. What happens? That also we need to discuss. So first, let me go into the detail of position embedding or position bias. So we are first of all constructing attention within a window, and I said that the window is 7 by 7, 7 by 7 patches, which means how many query key how many query key pairs can I construct for my window? Number of query key pairs. I'm not talking about number of query or number of key. I'm talking about query key pairs. All of you are making mistake. Number of queries is of course 49, right? Because there are total 49 tokens. So there are 49 queries and 49 keys, which means when I take query and key dot product, I can take any of the 49 queries and I can take dot product with any 49 keys. So totally I have 49 times 49. These many unique query key dot products available. What is this? I think this is 2401 or something. Let me. Yeah, so this is 2401. So in my attention formula, alpha ij equal to softmax of query I dot key j transpose divided by square root of d plus bias term plus the mask term, depending on whether it's shifted window or regular window. Here, how many bias terms do I need? How many learnable bias terms do I need? Because bias term is added with every query key dot product, which means ideally, if I have 2401 query key dot products, I need that many bias terms. So this is how we will think naively. But in the paper, what they show is something even more amazing. What they say is that you don't need 2401 bias terms because the exact positions, absolute position is not an issue. You just need the relative position. So if you look at the window, okay, inside this window, let's say I have some patches. So patch number 1, 2, 3, and 4. So let's say for simplicity, my window is 4 by 4 patches. And let's say my query is this guy, and key is this. What is the relative shift if I were to say delta x comma delta y between key and query? In this case, it is something like 1 comma 0. There is one position shift. Now, how many such query key pairs have such a 1 comma 0 shift between this query and this key is also delta x comma delta y equal to 1 comma 0? That is true. Between this and this, it's true. Between this and this, it's true. So for all of these query key pairs, if you look at relative shift between the query token and key token, it is the same. So you can somehow pass some sort of relative shift as the position bias. Now let's see how many such unique relative shifts are available. What are the range of values of delta x possible? If my window size is 7 by 7, not 4 by 4, it's 7 by 7. How many unique delta x values are possible? What is the minimum value of delta x? Minimum possible value of delta x. No, minimum value of delta x is what, 1 or 0 or something else? Minimum possible value is -6. Why? Because let's say my query is the last item and key is the 0th item. So this is 0 and or vice versa, but this is 0th item and this is the 6th item. So if you consider it like this, if this is query and this is key, from query to go to key, the shift is -6, correct? You have to jump 6 positions to the left side. So delta x can go from -6 all the way till what? Till +6, because now key can be this and query can be this. Similarly, delta y can also go from -6 to +6. So how many numbers are these? These are 13 numbers counting 0, because query and key can be literally the same token. Like this can be the query, that itself can be the key. Like, same token can be used to construct query and key, as we know. That's the whole reason why it's called self-attention. You are paying attention to yourself. You have 13 unique relative shifts in y also, which means how many unique delta x, delta y pairs are possible? You have 13 multiplied by 13, which is 169 unique delta x, delta y pairs are possible. So what is done in Swin transformer is it constructs a table of 169 such unique delta x, delta y pairs, but those 169 values are learnable parameters. So what is done is, let's say this is delta x, this is delta y, and this is bij. Okay. Then what is done is, now delta x can be 0, delta y can be 0, delta x can be -1, delta y can be 0, this can be -2, this can be 0, and many such values are possible. This might be -2.413, this might be -0.82, this might be +9.17. Bunch of these biases. These are now learnable parameters. So what is done is, if the model is looking at token number I and j for query and key respectively, based on the I and j value, you can calculate how much is the delta x and how much is the delta y. Now, let's say the delta x and delta y happen to be -1, 0. Then what is done is it will look up this table to pick this learnable value as the bij bias. If delta x, delta y happen to be like 7, or 7 is not there, but 5, -6, then there will be some value, some learnable value associated with this. Like this, there are 169 unique learnable bij values corresponding to 169 unique delta x, delta y pairs. And delta x and delta y is determined based on the ij values, because if I equal to, let's pick a random example. Let's say I is the row, j is the column. So let's say I comma j is, let's say I is this guy, and j is this. Then what is delta x? Delta x is equal to, in this case, -2, and delta y is 0, equal to 0. And then you look at the table. This is -2, 0. Then you say bij value is +917, right? This is plus 0.917. This is how the bias values are calculated in the Swin transformer. In the paper, actually, they show 4 different cases. I'll show you one table. Yeah, so in this table, they have tried many different things. So they tried without position embedding, with absolute position embedding, not relative. Then they tried combination of absolute plus relative later. Then they tried relative position embedding without, I don't know what is this, without appending maybe. I don't know what is this appending referring to. I forgot. Then last is relative position embedding, which we discussed just now. And they saw that and you might wonder, like, the difference in accuracy between no position embedding and the best is like 10% or something. It's not like that. It's like 1%. This is 80.1 in ImageNet and this is 81.3. It's like 1.2%. So, but in the domain of computer vision, this is a huge deal. In computer vision, even 0.5% improvement or even 0.2% improvement is a very, very big deal, because that's how the field evolves. But you should be surprised to see this, because you might think like, oh, this is such a major thing. If I don't have position embedding, I'll have maybe 50% accuracy. That's not the case. Accuracy is still there, but it's few percentage points lesser. So they have tried everything. They have tried the normal absolute position embedding also. It's just that they found this to be better, relative position embedding to be better. So this is why it says, you can't predict which one will be better. If nobody had tried this before, it's impossible to predict beforehand whether relative or absolute, which one would have been better. Someone would have said based on past experience that, oh no, absolute position embedding is always better. But then somebody tried this and they figured out that relative position embedding is better. And then you can only explain it after the fact. So that is one interesting thing about, all these models. So that is about what? Position embedding bias. So we now know all these things. We now know how patching is done. Windows 7x7. Relative position embedding bias is bij. It is injected during the calculation of attention score. Window-based multi-head self-attention is normally calculated. The only thing is mask term is not there for this, but it will have a bias term inside the attention score calculation formula. Shifted window will have bij term plus mask ij term, whose value is 0 or minus infinity or a big negative number. CLS token, this is the last thing, but before that, hierarchy is coming because your number of tokens are reducing from stage 1 to stage 2 to stage 3 to stage 4, but the channel size or dimensionality of each token is increasing. Linearity is coming because you are looking at attention scores within one window. So within one window means it doesn't matter if the image resolution increases, your attention calculation complexity goes linearly with the image dimension. Now the last part. What do you do with this in Swin transformer? What comes out of this? How do you utilize it for, let's say, image classification? That they explain in the appendix section of the paper. So yeah, look at this section. This is the appendix 2.1 section, image classification on ImageNet 1K. So 1K class classification. The image classification is performed by applying a global average pooling GAP layer on the output feature map of the last stage, followed by a linear classifier. we find this strategy to be as accurate as using an additional class token in Vision Transformer and DEIT. In DEIT, in fact, class and distill token was also there. In evaluation, the top one accuracy using a single crop is reported. So basically what is done is global average pooling, which is like, it's not max pooling, but it's basically a pooling operation that reduces the spatial dimensionality. So whatever comes out of this, a global average pooling is applied, which hopefully reduces the spatial dimensionality to 1 by 1. And the number of channels, I'm not sure. I think it will remain as 8C itself, if I'm not wrong. This I have to double check. This I'll check by the time we actually implement. And then there will be a linear projection layer, or like a multi-layer perceptron. I don't know if they have a hidden layer in the linear projection or not. They just say a linear classifier. So I guess there is no hidden layer here. It's just 8C dimensional space to what will it be projecting to in this linear layer. Whatever is the number of classes. So if you are working on MNIST 10 class, if you are working on ImageNet 1K number of nodes. So let's say we work on MNIST next in the next lecture, you will have 10, which is the number of class. So this will be basically a matrix of dimension 8C multiplied by 10. If C is 16, it will be 16 multiplied by 8, whatever that number is, by 10. That will be the dimensionality of the matrix. And for this is for classification. For detection and segmentation is completely different. But we have not yet looked at transformers for detection, which we will look at after the Swin transformer is done. The detection transformer is yet to come. But this is essentially how Swin transformer works. I do plan to give you a couple of qualitative assignments, nothing, no coding assignment this week. I had posted, by the way, on Tuesday, 3 assignments. I hope you have seen on the dashboard. But this week's assignment will not be related to coding the Swin transformer, but it will be related to your conceptual understanding of the Swin transformer architecture, because I will need your conceptual understanding next week to kind of not repeat the same things which we discussed today in the next week's implementation lecture. So we will see that. Next week, we most likely will not have a lecture. We will have a break. After that, we will start with detection transformer. So far, we have not implemented a single transformer for image object detection. We have only done image classification, but we need to look at DETR, detection transformer, which is probably one of the most famous transformers for detection, although there are better ones. And before that, please go through this lecture video. I'll be posting this as soon as it is compiled, and I'll be posting lecture notes. So go through all of that, plus go through the assignment. Then you'll be fully prepared for the next lecture. Next lecture, please expect some heavy coding. The code is, as you can imagine, because so many things need to be implemented outside of Vision Transformer, it'll be much more complex. But I think since we know the intuition now, we at least can save some time on the intuition part next lecture. So see you in the next week. Looking forward to seeing your assignments, and I hope you understood some things. If you have doubts, post on Discord. If you want clarity on some particular sections, just pause and rewatch those videos. Thank you so much. I hope you enjoyed today's lecture. In the next lecture, I'll also give you an overview of where the course is headed, like what all we have covered so far and where we are at right now. But from this point, transformers for classification, we will not be doing anymore, most likely. This will be the last model which we are discussing for classification. Now we will be moving into a bit more complex things like detection. So see you again in the next lecture, and take care. Bye. Awesome. So welcome to a new lecture. Today we'll be coding a Swin transformer from scratch. So in the last lecture, I had given you an intuition about what is the architecture of Swin transformer and how is it different from Vision transformer. So I hope you have gone through the lecture as a recap, which I had mentioned yesterday. So you will require some prerequisite knowledge about the Swin transformer architecture itself. I'll try to give you a brief recap, but most of the time today will be spent on coding itself. So that's the reason why I decided to split Swin transformer into an intuition part and coding part, because combining both into one single lecture would be very difficult. And another comment which I want to make is today's coding, unlike Nano, VLM, or Vision transformer models, it'll be much more difficult, simply because the architecture of Swin transformer, when we go through it, you will see that there are many modules that we have to build from scratch. So it will not be easy. So you should be on your full attention, and most likely it may so happen that you will not understand certain parts, and that would definitely require a second round of you going through it or revising through it. So just expect that, but I'll try to cover as many questions or doubts as possible in today's lecture itself. So first, let's do a quick recap of what exactly is Swin transformer. So Swin transformer was introduced as a generalized transformer-based architecture for images. So they showed that in the paper, they showed that you can use Swin transformer for image classification, object detection, semantic segmentation, etc. Although we will not be doing object detection or segmentation in today's lecture, we'll be focusing on classification. And the architecture is as shown in this diagram. So here, what is not shown is what happens to the context vector after it comes out of the transformer block. Then it has to go through something like a global average pooling. And then only the classification head comes. So if it's a 10 class classification, whatever is the number of nodes in the first layer, it will be connected to 10 nodes in the next layer. So this will be like a fully connected network. So this part is not shown in this architecture, simply because this will depend on whether our problem statement is classification or object detection or segmentation. But let's go through the architecture once very quickly. So you have images of height, width, and 3 channels. It can be 3 or 1 channel. Today we'll be looking at a 1 channel image, MNIST. So it will be H by W by 1. Then we convert the image into patches. So you know what patches are. Patches are splitting the image into non-overlapping small segments. And then patches are converted into flattened layer so that every patch will have spatially only one dimensional, 1 by 1 as the spatial dimension, but number of channels could be something like 48 or whatever. And then a linear embedding layer basically projects all your patches into a dimensionality, embedding dimensionality of C. So from 48, you will go to whatever your embedding dimensionality is. And then what happens is you have Swin transformer stages repeating. So this is stage 1, stage 2, stage 3, and stage 4. Today, we will not be having 4 stages. The main reason is that, the resolution of the MNIST image itself, if I'm not wrong, it's 28 by 28 or something, which means it's pointless to, divide the spatial dimension further to H by 16, H by 32, etc. So we won't be needing all the stages. We'll code 2 stages and we'll see. Then inside these stages, you have the Swin transformer block, and that consists of these 2 things primarily. So this is the regular window on the left-hand side, regular window Swin transformer block. And on the right-hand side, we have the shifted window transformer block. And just to refresh your memory, I have one question. So what's the difference between regular window and shifted window while calculating attention? So if attention is alpha ij between query I and key j, usually it is like this: softmax of qi kj transpose divided by square root of d. This is how usually attention weights are calculated. And then to get the context vector, you multiply it by value. But let's talk about attention weights. Alpha ij, this is your usual self-attention. But what is there extra in this regular Swin block? Is it the same as this formula, or am I missing something? There will be a relative positional bias term, right? So it's a relative position bias, meaning you look at every single patch inside a window and see how far away they are from each other. So there should be a bias term. We call it as Bij. So that is okay for regular. And for shifted window, is this enough, or am I missing something? For shifted window, we discussed about a mask term. So mask term is we do not allow patches belonging to 2 different windows to pay attention to each other. So how do we prevent this whole thing? We introduce a masking term. So we can call that as mask ij. So if you don't have Bij and mask ij, you have your normal attention. If you have this term, dot product of query and key, plus the relative position embedding, you have your regular window. That too, regular windows, multi-head self-attention. I'm only talking about this part right now. Everything else remains the same, just like the transformer. You have layer normalization, multi-head self-attention, skip connections, layer normalization, multi-layer perceptron. So everything is the same. The only difference is how does this window, regular window multi-head self-attention and shifted window multi-head self-attention look. So this is the normal multi-head self-attention. These two terms form part of regular window-based multi-head self-attention. And if you have these three terms, then you have shifted multi-head self-attention, shifted window multi-head self-attention. All right, so that is another thing. Now, I just want to show you a few things about what happens to our image. So let's take MNIST as the example. We have input image of height 28, width 28, and number of channels 1. It's basically black and white. So the original shape of an individual image will be C, H, W. C is channels, H is height, W is the width. So 1, 28, 28. This will be a single image. Now let's say we have a batch. I'm not going through the code right now. This is very familiar, but let me show you this image of one batch. So let's say my batch size is just 2 for simplicity so that I can show these batches as actual visuals. So my batch size is 2, meaning every single batch will have 2 images. So let's say these are the 2 images. Then it will add one more dimension, the batch dimension. So individual images height 28, width 28, number of channels 1. But then I have 2 images per batch. So those are these 2 images. Now, what do we do when we pass a batch into our Swin transformer? What is the first step that we do? What do we do with our images? First thing, we convert to patches, right? Because in vision transformer, in all types of in vision transformer, data efficient transformer, everywhere we have to first convert image into somehow into tokens. The way of tokenization is patching. So we have to first convert to patches. So patch embedding, if you remember from the convolutional neural network lecture, was done using a line of code like this. So nn.con2d. So it will be basically a 2-dimensional convolution operation with learnable parameters, where if it is like con2d of 1, 48, 2, 2, can you tell me why is this value 1? What does this 1 mean? It is the number of channels in your input image. What is your input image? Input image is MNIST. MNIST has 1 channel. So this is the number of channels in the input. This is the number of channels in the output, which is equal to the number of filters. So why is this set to be 48? If you look at the Swin transformer architecture, after patching, you end up with a 48 channel set of images or 48 channel patches. So that's why we set it to be 48. Then this 2 is kernel size, and this is also stride, which is 2, which means now we will create non-overlapping patches. And what will be the patch size according to this? The size of each patch. It has to be 2 by 2, right? Because your kernel size is 2 and each kernel becomes 1 patch. So at the starting, each patch will be of 2 by 2 size. So now if my image has height H originally and width W, how many total patches will I have? I should have H by 2 patches along the height multiplied by W by 2 patches along the width. So total number of patches will be HW by 4. So what will happen is, so here after this con2d operation, the 2 images which I had, so this is image number 1 and this is image number 2. These are the 2 images that I have in my batch. Its spatial resolution will shrink by half. It will become 14 from 28. Why? Because each patch is 2 by 2. And number of channels will increase to 48 because number of channels in the output is equal to number of filters which I define in my con2d. So now I have 2 images of spatial resolution 14 by 14 and channel resolution 48. All right. Now after patch embedding, what do we do? In the Swin transformer, I can actually show you the image. So after patch embedding, what is the thing that we do? We do linear embedding, and in linear embedding, what exactly are we doing to each patch? We project it from a 48-dimensional space into a C dimensional space. The value of C is variable, but so we can see what value we can use for C. But basically, it's a linear projection, right? So you create the token embeddings of C dimensions. And how many such tokens are there? You have H by, in this case, they are using H by 4, W by 4, but here I'm showing you a different example. Okay, so here I'm showing H by 2, W by 2. The only reason why I did that was, otherwise, if I use H by 4, W by 4, in this case, it will be a bit difficult. I may have to draw more items. So let's keep it this way. So don't get confused. Here, I just showed you an example where my dimensionality at the output is 14 by 14. But according to the paper, it is H by 4, W by 4. I'll also show you why we are doing this. Because when I divide my MNIST image too much, even after 2 times you divide by 2, 28 will become 14, 14 will become 7. And after that, it's not perfectly divisible by 2. So it's just an artifact of MNIST being a low resolution image. So that's the only reason why I'm not dividing by a bigger number at the starting itself. Okay. So that will be, so now output will look like this: 2, 48, 14, 14. Now tell me, what is this 2? It's the batch size. What is 48? 48 is the number of channels in my output image just before linear embedding. Then 14 by 14 is what? This is the height of each patch and width of each, height of each image and width of each image after con 2D operation. And then we will project this from a 48 dimensional into a C dimensional vector. But for simplicity, we can assume that C is also equal to 48. So after projection, ideally, this should become 2, C, 14, 14, something like this. But if C is equal to 48, we'll say this will remain as 2, 14, 48, 14, 14. This is just for simplicity. Okay, so that we are not using too many variables in our visualization. While coding, of course, we can mention C as a separate variable. Then, so this is the flattening operation. So flattening operation happens so that, so this happens actually just before linear embedding. I should have shown you this first. So flattening operation converts every patch. So what is my patch size? It was 14 by 14. My image size was 14 by 14 after con 2D operation. And this had 48 dimensions. All right. And then like this, I had 2 images. And what will happen is I will have now each patch will be, I just want what each image should be a certain number of patches. And in the flatten operation, what I will do is all the 48 channels I'll pick. And then I have one image here, right? So this one pixel, sorry, not one image. This one pixel has 48 dimensions. Then what I will say is, sorry, not one pixel, a 2 by 2 pixel. It will have 48 dimensions. So if we were to think about a 28 by 28 image and a 2 by 2 pixel patch here, okay, this will have 48 dimensions. And ideally, my token, one token is equal to one patch. So what should I say? What I should say, I should somehow be able to extract all these patches as independent tokens so that now I have a sequence of tokens, because finally what goes into the transformer is a sequence of tokens. It's not an image. And how do we get sequence of tokens? By performing a flattening operation. So if I had 2 by 2 patch, and if my image size is 28 by 28, and if the channel dimension is 48, how many total number of tokens are there, or how many total number of patches are there per image? Per image, I will have 28 by 2 multiplied by 28 by 2. So 14 by 14, which is 196 tokens or patches per image. And the dimensionality of these tokens just before linear embedding will be 48. So every image, so this is image number 1 and this is image number 2. Image number 1 will now be split into 196 patches equal to 196 tokens. Okay, so each image will become a sequence of 196 tokens, and each token has a dimensionality of 48. So now if you look at this, this is basically now one patch. Something that looks like this with 196 dimensions. And so now we have these things. We have batch size. So this was the input that was going into the flatten operation. I have batch size of 2. I had 48 as the dimensionality. Actually, this will be converted into a one single number. But if you were to look at one single patch, if you were to just imagine that you have one single patch, I'm just talking, okay, without flattening. Just before flattening, if you were to look at what exactly are each of those components are spatially one patch of channel dimension 48. Flattening operation will make sure that it has only the channel dimensionality. Spatially, it will be 1 by 1. And then it will be treated like a vector of 48 dimensions, right? And then that 48 dimensional vector is what is projected into a C dimensional space. So when you go from the input of this linear embedding to output of the linear embedding, you are converting each vectors of spatial dimension 1 by 1 and channel dimension 48 into a vector of dimensionality C. All right. When we code, this will be much more clearer now. So what we want to do is, we had 2 by 48 by 14 by 14. We'll go from this to something like this. So what has happened is, this 14 by 14, if you multiply 14 and 14, you have 196. So totally, you have 196 tokens. How did we get 14 by 14 in the first place? 14 was the number of patches along the height. This 14 was the number of patches along the width. So you basically have a 2D grid of patches. Now those 2D grid of patches, you convert into just a one-dimensional set of sequence. So this 14 by 14 will be combined into become just a sequence of 196 patches or 196 tokens. This 48 will remain here. So this 48 is the dimensionality of each patch. And then first item is the batch size. So now just read this. What we are saying is, in my batch, I have 2 images. Each image is consisting of 196 tokens. Yes, it is flattened. So the code here is x.flatten of 2, meaning this dimension will be flattened. Everything after this. So this is dimension number 0. This is dimension number 1. This is dimension 2, 3. So everything after this will be flattened into one single thing. So you will have only 0, 1, and 2 dimension. And then you transpose dimension number 1, 2. Why did you take the transpose here? What is the purpose of this transpose 1, 2? What you want is, you want the dimensionality of your token as the last dimension. So if your token is 48 dimensional token, that should come at the very end. So that's the reason why you first flatten and then you take the transpose. So just to reiterate, the sequence of tokens that you have are, you have a batch size of 2. So you had 2 images. Each image you split into patches of 2 by 2 size. So totally, since you started with 28 by 28 images, you ended up having 196 patches or 196 tokens per image. And each token is of dimension 48. And now you can project this into from 48 to, let's say, C dimension. So C 2, 196, C from here. And here we can assume that C is equal to 48 or whatever we want to use, right? So this is what is happening. So now you have 2 batches, 196 tokens per image, and C is the dimensionality of each token. Now, this sequence of tokens is what is being passed into the Swin transformer block. Now let's look at what happens inside the Swin transformer block. So inside Swin transformer, just imagine, what is the input to the Swin transformer block. There are 2 blocks, by the way. You have regular window block and you have shifted window. I don't want to call it as block. Maybe a better term is a regular window MSA based transformer block and shifted window multi-head self-attention based transformer block. So first is you are getting the feature map. Feature map meaning you don't have the image in its original shape. It has passed through a few layers, so you have a bunch of features that is being passed into the Swin block. And before going into any of this, just think about what these 2, 3, 4, 5, 6 steps are. If we are in a regular window block, there is no shifting, right? In regular window, there is no window shifting. So window shifting, I hope you vaguely remember. So window shifting is nothing but, we said that in the regular window, the windows are consisting of patches. So here in this example image, each window is a 4x4 patch. So pixels make patches, patches make windows, and windows make the full image. So here, this is a patch. 4x4 patches make a window. So now this is a window. In this case, 2x2 window make the full image. And this is what is happening in regular window. In shifted window, what happens is you perform something called as window shifting. So if the window size was, let's say 4, your shifting will be done by a magnitude of 4x2. So now what you will have is you will have a window here. You will have a window here, a window here. So instead of now having 4 windows, you will have 9 windows. But you don't want the number of windows to increase. So I had shown you a figure in the last lecture. Yeah, so this figure. So you don't want the number of windows to increase. So what you will do is you will assign IDs to the windows. So in the original regular window, the ID was, this whole window was of ID 0. This whole thing was ID 1. This whole thing was ID 2. And this whole thing was ID 3. In shifted window, what we do is this window is ID 0. This window meaning basically this particular part of the window. This is ID 0. This is 0. This is 0. This is 0. Then this is 2, this is 2, this is 1, this is 1, and this is 3. So in shifted window block, we have patches that are far away from each other having the same window ID. Now, what is so special about window ID? Why did we do this? So when we pay attention, when one patch pays attention to another patch in the image, attention scores are only constructed if their window IDs are the same, meaning this window can pay attention to this window, although they are far away from each other. I mean, this patch. But this patch cannot pay attention to this patch, although they are close to each other because their window IDs are different. The window ID of the left-hand side patch is 0. Window ID of the right-hand side patch is 1. But that is not a problem. Why is that not a problem? Because in the regular window, they were anyway paying attention to each other. So because those two patches belong to the same window. But in shifted window, now the shifting is allowing patches that were far away from each other to pay attention to each other. So this is how you are able to construct long-range dependency in shifted window setup of the Swin transformer. And we also discussed why this is so beneficial. It was because the complexity of attention calculation was dash. Complexity of attention calculation was growing in dash format with respect to the image size. No, it was linear, right? In Swin transformer, it was linear. In normal transformer, in vision transformer, it was quadratic. So that was the main reason why we went with this shifted window idea. I mean, not we, the authors of the paper went with the shifted window idea, because the window size inside which tokens / patches pay attention to each other, it remains the same. Window size does not change, even if the image size changes. All right. Every attention is caught by both regular and shifted window. It's not like every attention is caught. In regular window, attention is paid by patches that are physically close to each other or geometrically close to each other. In shifted window, you don't necessarily have patches that are geometrically close to each other. So you have localized attention as well as kind of global attention. I don't want to say it's a perfectly global attention. If it was perfectly global, we will not restrict the patches to be inside windows, but the patches can technically be very far apart in the shifted window. So this is the shifting that we are doing. So now, if we are using a shifted window, we apply this window rolling. So window rolling is just the term that we use to describe the fact that you are shifting the window by W by 2 and W by 2 to the left and to the top. So if we are in a shifted window block, we will apply rolling, but this step will be skipped if we are in a regular window. Now, in a shifted window, if we are rolling, we have to, after applying attention and everything, we have to roll it back, because if you go to the transformer architecture, see here there are multiplied by 2. Multiplied by 2 meaning you have one regular window and one shifted window. But in some stages, it's like multiplied by 6, meaning you have regular window, shifted window, regular window, shifted window, and one more repeat, which means whatever comes out of the shifted window, right? You should not have that shifted window now again going back into a regular window. So the shifting you have to reverse once your attention computation is done. So we'll come to this attention computation part, this 2 and 3, 4, and 5. But basically, if we were in a shifted window where this shifting operation was applied, we have to roll it back so that window comes back to regular. Now we can pass this. So these operations will happen in regular window, and then same operations will happen in shifted window, except in shifted window, this window rolling and rolling back is not needed. It is not done. But if it's a shifted window, the rolling is done before attention calculation and rolling back is done after attention calculation. Now, this part is easiest, I would say. 7th, you will know. I mean, multi-residual adding and multi-layer perceptron. So this part, I don't have to explain too much. But let's come to 3, 4, and 5. Now, think about this. I have an image of certain dimension, and or I have a set of patches of certain dimension, and but I am not paying attention inside the total image. So if I have a sequence of 196 patches or 196 tokens, I'm not going to use all these 196 windows, 196 tokens in each of my attention calculation, right? I want it based on window. So for attention calculation in the regular window block as well as in shifted window block, it is not very helpful to me if I get the whole sequence of tokens as one sequence. What I want is I want tokens based on windows. So something called window partition we will be doing, which partitions the whole set of tokens into different windows, and so that we can only focus on one window at a time. Then within each window, we will calculate the attention. So within each window, I'll have multiple patches. Those patches will attend to each other. And then I will do something called window reverse, so that my dimensionality, if the dimensionality is like batch, tokens, token dimensionality, if that is the dimensionality that was there before we did the window partition, we will reverse that operation so that my original dimensionality is back. Okay, there are a couple of questions. Suppose the object is in right corner, another is in left. How to capture global? Yeah, so just check this. Where is my visual example? So if the object was in the one was in the right corner and another was in the left. So this, you look at in the shifted window, this has window ID 2 and this has window ID 2. So in that case, it is automatically paying attention to each other. So it's like shifted window is like a complement of regular window in the sense that in shifted window, if you look at this patch, this patch, this patch, and this patch, although they are all 4 patches very close to each other, there was no attention between them because their window IDs were different. But that problem is solved in this case. Conversely, you had 4 corner patches which were not paying attention to each other at all. That problem is also fixed. So basically, the problem of objects being far away from each other or closer to each other, none of that is an issue. By shifting by half window, will we find attention to all patches in the shifted window? Is there a chance that we miss a few patches in attention? Yes, there is a chance that we miss a few patches in attention, of course. I can already think of an example. So let's say I take an example of this patch. Let me first delete all this annotations. Okay, let's say I am considering this patch, and maybe this one. Okay. And now look at the same two patches in shifted window. In regular window, am I drawing the same? Yeah, I think this is correct. So in regular window as well as in shifted window, those two patches are never able to pay attention to each other, because in regular window, the ID was 2 and 3. In shifted window also, their ID happened to be 2 and 3. So here, obviously, this patch will never be able to pay attention to this patch in regular window as well as in shifted window. But that's the, I would say, the downside of Swin that we have to live with, right? We will not get everything. So if we are getting the benefit of linear progression in complexity, there must be some downside. The downside is this: it's not a perfectly global attention. It's not like every single patch will pay attention to every single other patch in shifted window attention, but it solves the problem to some extent. And the hope is that when you go through, if you look at the feature dimensionality, I mean, not the feature, the spatial dimensionality, you go from h by 8, then h by 16, h by 32. There's already a lot of abstractions that we are capturing, and we are hoping that by keeping the same regular window and shifted window, we are hoping that somehow all the features will be captured in multiple stages. So maybe the reason why people thought of multi-stage Swin transformer is because in one stage it may not result in good accuracy, probably because of the exact same reason that some patches never get to see each other in the attention. All right, so that is the whole idea of the Swin block. Now, what else is remaining before we move ahead? This I showed you already. Yeah, so now this is the part where we convert sequence of tokens into windows. So let's say my window size is 7 by 7. So let's say my window size is 7 by 7. What does this mean? Does this mean that I have 7 pixels by 7 pixels in my window? Are these the number of pixels or something else? These are the number of patches per window. So if I say that my window size is 7 by 7, it means each window has 49 patches. Now, look at this image. So this is what we have after our embedding. So let's say my embedding dimension is also C is equal to 48. Okay, so don't get confused. So this here, I'm assuming that C is equal to 48. Each image number 1, I have 196 patches. Image number 2, I have 196 patches. Now, if I'm splitting this into windows, tell me how many windows will be there in each image? (196) divided by 49, which is 4. 49 times 2 is 98. 98 times 2 is 196. So basically, each image will now be split into 4 windows, correct? And the channel dimension will not change. Channel dimension will remain the same. It will be 48. So after converting my patches into windows, now I have a window size of 7 by 7, which means I have 7 patches along the row and 7 patches along the column, consisting 49 patches. Like that, image number 1, this is the image number 1 in my batch, will have 4 windows. So this is window number 1, window number 2, number 3, and number 4. But the channel dimension will remain 48. Similarly, my image number 2 will also have 4 windows, channel dimension remaining the same. Now, are we paying attention like this? Is attention constructed from here to here, between this window and this window, and between this window and this window, and between this window and this window? Is that how it works? No, that is not how it works. Attention is restricted to just the windows. Attention is not there between windows. What that means is, within this window, I said I have patches, right? So I have patches inside this window. Those patches will pay attention to each other. So my regular window, shifted window, etc. are being applied within these windows. So if my regular window was like this, my shifted window will look like this. I mean, I just drew it on another window, but basically I just want to show you. So attention is constructed within window number 1 separately, within window number 2 separately, number 3 separately, number 4 separately. There is no attention between the windows. So for that purpose, although I have, so what is the batch size here? Batch size is 2. So if we were to write the dimensionality, it is 2 comma, then how many windows I have? 4 windows I have. And that too I can write maybe something like, okay, let's keep it like this. Then each window is something like 48 dimensionality, right? So 4 windows and I have 49 tokens. Yeah, 7 by 7 tokens per window. And then each token has a dimensionality of 48. So let's say this is my batch dimension. This is my number of windows per image. This is the number of patches along the width, number of patches along the height, and this is the dimensionality of each patch. I don't have to now make this batch-wise separation anymore, because anyway, it doesn't matter. Within the same batch itself, I am considering windows separately. Within the same batch itself, I have 4 windows. Those 4 windows are counted separately, which means I can count all these 8 windows by saying that totally I have 8 windows. Each window has patches of size 2 by 2, or rather dimensionality of 48. And what else? Yeah, I have 7 patches along the width and 7 patches along the height per window. So 7 by 7 is not the, it's already flattened. Please note, 7 by 7 is the patch number. It's not the patch dimension. It's not the pixels per patch. It is the total number of patches in the window. Total pixels in the patch was already flattened before, right? So what this says is, in my current batch, in my total batch, I had 2 images, but then when I split the image into windows, each image became 4 windows. And because I'm paying attention within the window, I don't care about batch separation anymore. For purpose of calculating the attention, I can take all the 8 windows, out of which 4 windows are coming from first image and 4 windows are coming from second image, but I can group them together because I'm anyway considering windows separately for my attention purpose. And then here I'm saying I have 7 within each window. So I have totally 8 windows. Within each window, I have 7 patches along the width, 7 patches along the height, and each patch has a dimensionality of 48. So now this is what will go through my attention head, multi-head attention. And for each of these 8 windows, attention will be calculated separately. And once it comes out of the attention, we will reshape it back into this, because the batch dimensionality has to be preserved outside of the multi-head attention when it goes to multi-head, multi-layer perceptron and other modules. But for the purpose of calculating attention inside the attention head, we don't need to preserve the batch dimension. We'll see that the implementation of this in the coding. Window attention. Yeah, this we already discussed. I'll come back to this if needed. I think now we are ready to start coding. I don't think that I have missed anything important. If I have, I will explain it during the coding. So now please open Google Colab. Let's start from scratch. We'll take a 2-minute break and let's reconvene to start coding. And here, please pay full attention because the code is a little bit long, but I hope we can get it working by the end of today. All right, let's continue. So the things that we have to code today, we need to code importing. Then we have to define certain functions. For one is window partition functions, one for window. I mean, all of you can see my collab notebook, right now? Just to confirm. Okay, awesome. So we need to do window partition. Where do we do this? Just before we go to the attention stage. Then after attention, we have to put the windows back into image format. So then we have to code something like window reverse. Then I'll paste the link. And then we have to code some classes. So one class for window attention, which is basically calculating attention scores or self-attention within each window. Second is we need one for the swin block. This will include both the regular swin window and shifted window. Then third is we have something called patch merging. This is something which I did not discuss today, but we had discussed in the last class. So do you remember what we were doing in patch merging? In patch merging, what we did was, let me go back to the diagram, was something like this. So we wanted to go from a dimensionality of, let's say, h by 4, w by 4, and c to h by 8, w by 8, and 2c. So if you look at the Swin transformer figure, you see it goes from h by 4, w by 4, c to h by 8, w by 8, 2c. But we also had discussed in the last lecture that the dimensionality does not change as the patches go through the Swin transformer block, which means if the output that is coming out of the Swin transformer is h by 8, w by 8, 2c, the input that goes in also has to be h by 8, w by 8, 2c, which means this patch merging is doing something which is converting h by 4, w by 4, c to h by 8, w by 8, 2c. And there what we did was there was an intermediate stage which first divided the h by 4 and w by 4 into patches of size 2 by 2 or groups of patches of 2 by 2. And then it performed a flattening of those individual groups. So then what happened was, instead of now having h by 4 and w by 4, it got divided. The height became one more factor of 1 by 2, which means h by 4 became h by 8. Width was divided by a factor of or multiplied by a factor of 1 by 2, which means w by 4 became w by 8. But then these 4 items, right? There are 4 items inside each group of patches. They were concatenated to increase the channel dimensionality from C to 4C, because you have 4 items each of dimensionality, channel dimensionality C. So they were concatenated after each other to form 4C. And then after this, there was a linear projection. So the way you go from 4C to 2C, they had a linear embedding where each item was taken separately and each item had a channel dimension of 4C. And after a linear embedding, you get 2C. So this is what they did. And this is what we called as patch embedding, patch merging, not embedding. So we have to have something for patch merge. And then we can have a final, let's say, multi-stage Swin transformer class. So this is just for the Swin block, but this is for the whole transformer with MNIST data. We'll use MNIST. So these are the classes we have to define. Then we have to download the data set. Then we do the training and testing. So these are the things we are going to implement today. Okay. So let's start with imports. So first, always we import PyTorch. Then import torch.nn as nn. And this is for passing into the classes so that classes can inherit properties from nn.module. Then import torch.nn.functional as f, which will be used while performing layer normalization. Then from torch vision import datasets for importing PyTorch, importing MNIST from PyTorch library. Then we need some data transformations like mean value normalization and standard deviation shifting from torch.utils.data. Import data loader for converting the images into batches. Then this is optional from TQDM. Import TQDM. I always knew what is TQDM. It is for displaying the progress bar, but I did not know the full form. Does anyone know the full form of TQDM? It's a weird word. TQDM, it's like some Arabic word. TQDM PyTorch full form. This is the Arabic word. I don't even know how to pronounce this, but basically in Arabic it means progress. So this is how TQDM came. Anyways, so this is for just displaying the progress bar while downloading the data set or displaying the progress during epochs. So that's all the imports. I don't think we need any more. I have Collab Pro, so I will be connecting to TPU. You can feel free to connect to whatever resource available to you. It's reasonably fast even without Collab Pro. The training is not too slow. Now, after imports, we need to implement these two things, window partition and window reverse. So let me just, these two functions, let's define. So define window partition, and some input should go. One is, of course, the input batches itself, the image batches. Second is some window size, because to partition something into window, we need to know what is the window size. So this is the first function, and something we need to return at the end of it. Second function is window reverse. After partitioning, the partition thing goes to the attention, and after coming out from attention, we have to put it back into image format. So we can define window reverse. And here, the input here will not be X, because we won't have the original X anymore. Input will be whatever windows we have. The windows that went through the attention block and that is coming out of the attention will be one of the inputs here. Another input will be how many windows we have, that we will know, then width and height. So this information we'll have, and then at the end of this, we have to return something. So what we are returning in both cases, we can return just X, and we just need to perform some computation before returning. So first is, I need to know what is my batch size, what is my height, what is my width, what is the channel dimension, and all of this is simply available from x.shape. So this will give me what is my batch size, what is my height, weight, and height, width, and C, channel dimension. Then what we do is x equal to x.view. So now think about what we want to do. The height we want to split into windows, width we want to split into windows, right? That's what we want to do. So I want to reshape this such that b comma height divided by windows, but here instead of using simple divided by, I'll use 2 bars, which means it will consider the integer. Then but then the total dimension has to remain the same. So what I mean by that is, if I do something like w by win comma c, this is not possible, because in my original input, I have total number of items equal to b into h multiplied by w multiplied by c. That many items we have. So we cannot reshape something of b times h times w times c, that many elements, into b times h times w times c divided by number of windows square. We can't do that, which means the dimensionality should match. So I have a win here, windows here. So what is done is, we are simply saying that this h is now split into, let's say the number of windows is 7. Now my height is split into 7 windows, where number of patches along each window will be, along the height will be h by win. So these two, if you multiply h divided by win, you get h back. If you multiply w divided by win multiplied by win, you get w back. So first is this viewing function. Second is, okay, let me also run this so that all these functions are available. Okay, this is functional. X comma. Yeah, indentation is missing, but there is one more thing, one more step I have to do. Let's do one thing. Just don't forget about all the things that I showed you from the image, because in coding there are a few differences. So don't keep some of the things confuse you. So let's follow this. So x dot view, I don't know what is missing here. Bracket was not closed. Where is it not closed? Okay, Windows C. Yeah, okay, now it's fine. Okay, now we have to do one more thing, which is I'm converting my image into Windows, which means I will have something, I need something like this, x equal to x dot permute. Okay, so I somehow have to combine batch dimension, then h by win, so b comma, so batch dimension is 0 dimension, then h by win is dimension number 1. Then this ideally I want to bring here, because think about what is the input that goes into my attention. The input is these three things combined, followed by certain number of windows, certain size of windows. So window size is 7 by 7. So what goes into my attention is 8 comma, according to the example we discussed, 8 comma 7 comma 7 comma 48. How do you get 8? 8 is nothing but your batch dimension, which was 2 multiplied by number of windows per image. Number of windows per image was 4. So the way you get that is, what is h by win multiplied by w by win? H by win is the total number of windows along the height. W by win is the total number of windows along the width. B multiplied by H by win multiplied by W by win will give you total number of windows in your entire batch. So you somehow want to bring these two items close to each other. This H by win and W by win, you should bring closer to B. So the second dimension, so 0, 1, 2, second dimension you want to move here, and third dimension you want to move into the second position. So 0, 1, 2, 0, 1, 3, then following by that 2, then 4 and 5 can remain as such. I will show you how this looks like. And 0, 1, 2, 3, 4, 5. Yeah, this is fine. X equal to x dot permute of that. Now what we want to do is we want to combine these three things. Meaning I want to combine B, H by win and W by win into one single dimension, and remaining things can remain as separate dimensions. So x equal to x dot reshape of, so I want to retain last three dimension, which will be windows, comma C, but the first dimension will be whatever results from these three. So I can just put -1. Python will automatically calculate what this number should be. But basically, I am reshaping x. Let me actually show you a picture that will be much, much easier for you to visualize. Yeah, this is window partition. So the input that I'm sending into my window partition is the batch, then it has height, width, and channel. Now, I don't want the batch dimension to be preserved when I'm going into attention. What goes into attention should simply be the fact that I have 8, something like 8. I'm just putting actual numbers so that you can understand. I have 8 number of windows. Each window consists of 7 by 7 patches, and each patch is 48 dimension. So this is what I want. I just want 4 dimensions. Now, first what we did was to convert something like this into this. This is also 4 dimension, but here batch dimension is there, height of the image is there, width of the image is there. None of this I want, right? So what I instead want is size of the window along the width, along the height, and the dimensionality. So C needs to be preserved, of course. C is coming as such. but B, H, and W, I have to reshape it into some other format. So first step which I did was I divided H by win and W by win. So then I'll say if win is equal to the width of the window, then I'm saying along the height, I have these many windows. Then along the width, I have these many windows. But then since the number of items in the x dot shape and x dot view, I mean, in the x before and after this view function should be the same, I have to have this win and win because I'm dividing by win, which means I have to multiply by win. And then I'm rearranging the items such that B, H by win, and W by win comes close to each other, which is why 0th dimension, 1st dimension, and 3rd dimension are now close to each other. 2, 4, 5 will be win, win, and C. So those will be the last 3 dimensions. And then I'm applying a reshape function where last 3 dimensions are preserved and remaining 3 are combined into one single dimension. So this -1 will take care of the default number, whatever that should be. Here the default number would be B multiplied by H by win multiplied by H by width by win. So this is batches. Number of batches, number of images in each batch was 2. H by win is number of windows along the width. This was, if I remember correctly, this was in the example, I completely forgot. Number of items along the width was 2, 2, right? So this was 2 and this was also 2. So 2 times 2 times 2 resulting in 8. Then following that, you will have window dimension. This was 7. Window dimension, this was 7. Channel dimension, which was 48. So you will have 8, 7, 7, 48. According to this example, I'm not using these exact numbers, but that is how you finally get 8, 7, 7, 48. All right. So that is the window partition function. Now, window reverse function is relatively simple. First, you need to get the batch dimension back from your windows because now you don't have batch information here. Here, if you say B equal to, windows dot shape of 0, usually the 0th dimension is the batch, but this is not correct because what is the 0th dimension? 0th dimension is batch multiplied by H by window multiplied by W by window. So how do I get batch back? I simply have to divide by those two, right? I divide by the product of H by win and W by win. So if I divide the 0th dimension of my windows, which was the product of B and H by win and W by win, if I divide that by H by win and W by win, I get B back. So this is how I can get the batch back. Then X is equal to, now we have to reshape of, actually no, we can just view windows dot view. So first dimension should be batch, second should be H by win. Then we are now unpacking. So third will be W by win because we are unpacking B times H by win times W by win into 3 separate items. Following that, we had win, C. And then do the permutation once again. So now X equal to X dot permute. Now to get back this kind of a format, I have to once again bring with this guy to the 3rd position and this guy to the 4th position. So I just say 0, 1 can remain as such. 2 and 3 will be flipped. So 3, 2, 4, 5. Okay, C is not defined. I also have to know what to see. But if you don't know what to see, just put this as -1. Python will automatically calculate what the last dimension should be. Because Python knows that if you multiply all these items multiplied by an unknown number, you have to get back whatever was the values of B times H times W times C. So Python can automatically, even if you don't explicitly mention one of these, Python knows what that value should be. That's pretty much it. X dot permute. And then you have to get this into the shape of your tokens. So you say h dot reshape of batch, comma, w, comma, sorry, height, comma, width, comma. I don't know the channel dimension because the channel dimension will depend on which transformer block you are in, which transformer stage you are in. If you are in stage 2, your channel dimension will be 2C. If you are in stage 4, it will be 8C. So I really don't know what exactly is the channel dimension. It depends on the stage. So I can simply put -1. So now I get back something in the nice format. So here I have B. H by W is now the number of patches along height and number of patches along width. -1 is it will automatically calculate what should be the channel dimension. So ideally, if, according to our example we follow, we can just say batch will be 2, H will be number of patches along the height, which was 14, right? W was also 14 and C was 48. So we get back what originally we wanted. Window reverse first line. Window reverse first line is basically this. Our X which was going in was B multiplied by H by Win multiplied by W by Win. That was the 0th dimension, because that is what goes into the attention function. And then after this function, we will not immediately call this function, because after performing Windows partition, we have to calculate the attention. Only then we will calculate Windows reverse function. But by the time some input is going into Windows reverse function, you don't know the batch size, because by looking at this number 8, how do you know what is the batch size? How do you back calculate batch size from 8? 8 divided by total number of windows, total number of windows along the height divided by total number of windows along the width. That is your batch dimension. So 8 you have to divide by 2 and then again divide by 2. Only then you can get back batch. Just by looking at this 8, you don't know what's the batch dimension. So just like that, here, since you don't know the batch dimension, you take the 0th index item, then you divide by total number of windows along the height multiplied by total number of windows along the width to get back what was the batch size. In this case, it will be 8 divided by 2, basically 8 divided by 2 times 2, which is equal to 8 by 4 equal to 2. So 2 is the batch size. So that is how you get back batch size. All right. That is all about window partition and window reverse. I hope this should be fine. Then next part we can code the class, window attention class for calculating attention inside or inside each window. So this we call as window attention. And of course, we have to pass nn.module so that it inherits properties from nn.module. Define underscore init, underscore bracket self, comma, bunch of things we'll have to pass, but we'll figure it out. Then super, so that we are calling the init constructor from the parent class, underscore. Then we need, first of all, the embedding dimension. So self.dim equal to dim, which means embedding dimension we have to pass. This we decide what that should be. Self.number of heads equal to this also we can pass. Then self.head underscore dimension equal to dim, self.dim divided by self.number of heads. Because total dimension divided by total number of heads will be the dimension of the token inside each head. And then self.scale. This is the 1 by square root of d thing, which we basically do query times key transpose divided by square root of d. So self.scale equal to whatever is the head dimension raised to minus 0.5, which will be 1 by square root of 5. And self.number of windows or the not number of windows, size of each window equal to win. And win we have to pass. So we are passing win number of heads and dimensionality of the input embedding. And then we can say self.query equal to nn.linear, because query we are projecting from dim comma dim, because what comes out of query is also dim. So we don't want to use the hidden dimension, which one, this head dimension explicitly, we don't have to use it here. We could have used it if we wanted to calculate query key value separately, and then in the non-efficient way, we could have said that for each query key value, there are n number of heads. So calculate the context vector for each head, and then using a for loop, combine them. We could have done that. But then all of that will be simplified if we simply say what the input that goes into the multi-head self-attention is dim. What comes out of multi-head attention after concatenation is also of the same dimension. Then self.key equal to the same thing. Now nn.linear, whatever comes after nn.linear, these are all learnable parameters. Then self.value is also equal to nn.dim. So basically, key, query, and value are all three separate, the matrices corresponding to these three are three separate learnable matrices. Input dimension is dim, output dimension is also dim. Then after concatenation of the context vectors coming out from different heads, you project it into the same dimensional space, so that if you have head number 1, head number 2, head number 3, etc., you can perform appropriate mixing of whatever comes out of it. So you have a projection layer. This is usually very less discussed in the transformer architecture. Of course, we had discussed it, but in case you don't remember this projection, you concatenate all the items coming from head number 1, 2, 3, etc. But it's not, you don't want to preserve that 1, 2, 3, that order. So you have to perform some kind of mixing. So this projection layer will help you perform that kind of mixing. So it projects from D-dimensional space into D-dimensional space itself. This is not the multi-layer perceptron. Now comes a bit tricky part. Now we have to code, because is it enough for us to have query key value or query and key to calculate attention? We need two more things, right? We need relative position bias for calculating attention. We need one more thing, depending on what window we are. We need mask value. So these two things we need. So first, let us look at relative positional bias. So I'll just first show you the code, and then I'll show you with an example what the code is exactly doing. Then you will understand what we are doing. So in relative positional bias, we had said that if we have bunch of tokens in the form of patches. So let's say this is one window. This is not the image, one window. And inside this, I have patch number 1, patch number 2, 3, 4. All we need to do is, and then let's say I have another 2 patches. The delta x between these 2 patches is 2. The delta x between these 2 patches is also 2. So all we care about is if this is the query and this is the key. And if this is the query and this is the key. For this query key pair, delta x is equal to 2, delta y is equal to 0. For this query key pair, delta x is equal to 2, delta y is equal to 0. So in the last lecture, we discussed that if this is win and this is win, where win is equal to, let's say, 3. Okay. If this is 3, my delta x can go from -2 all the way till +2, because my query can be here, can be the third item, key can be the first item. So from 3 to go to 1, you have to do -2. So I have total how many unique values for delta x? I have 5 unique values for delta x, -2, -1, 0, 1, 2. Similarly, for delta y also, I have 5 unique values. So the total number of unique delta x, delta y pairs is 5 by 5, equal to 25. So the total number of learnable relative positional bias items is only 25 instead of 81. What is the logic of 81? I have 3 tokens along the height, 3 tokens along the width. Total number of tokens is 3 times 3 equal to 9. Every single token can be there will be query corresponding to every single token. There will be key corresponding to every single token. So total number of query key pairs is 9 times 9, which is 81, which means ideally I should have 81 position embedding terms or position bias terms. but I don't need 81 unique position bias terms. I only need 25 unique position bias terms because there are only 25 unique delta x comma delta y values. So now all we need to do is create a table of learnable bias where this is delta x, this is delta y, and this is the bij term. And for any given patch pair, calculate the delta x. So let's say delta x is -1 and delta y is 2. I just need to have a learnable position bias term here. Let's say 1.81. Like that, I'll have 1, 2, 3, etc. 25 items. And basically, actually, I will have 81 items because I have 81 token pairs. But only 25 items will be unique because for this query key pair and this query key pair, the relative position bias will be exactly the same because their delta x is 2, delta y is 0. So although I have 81 rows in this table, so this is like a table of learnable relative position bias, only 25 rows are unique. Remaining are repetitions, right? So we need to now construct this kind of a table. So now let's come back to our code, relative positional bias term. So first is coordinates equal to torch.stack. I'll show you exactly what this code does. Then torch.meshGrid of torch.stack of torch.meshGrid of torch.aRange of windows, comma. So this will be a 2x2 grid. I will show you how this grid looks like. Then you will understand the code better. And I want my indexing to be ij, then that's it. So now I'll copy this and I will run it separately so that you can see. So now let's say my window value is 3. Now, what this means is I have 5 possible delta x values and 5 possible delta y values. And this coordinates will look something like this if I print. So delta x, delta y pairs. I have the 0th row number 1, row number 2. This is 0th column, first column, second column. Okay, it's not delta x, delta y value yet. That we are going to calculate. Then we flatten this. So coordinates flattened equal to chords dot flatten of 1. So after flattening, we can print it. So after flattening, it will look like this. So this is the row number 0, column number 0, row number 0, column 1, row 0, column 2. So you will have total 9 pairs here because totally you have 9 possible positions for, actually there will be total 81 pairs, but based on row and column index, you have either row number 0, row number 1, row number 2, or you have column number 0, column number 1, column number 2. And what is the 0, 1, 2? They are the indices of rows and columns of the patches inside your windows. Your window size is 3x3, which means totally you have 9 patches. And 9 patches are aligned as a grid of 3x3, which means totally there are 3 unique rows and 3 unique columns. Okay, so this is the flattened coordinates. Then we say relative coordinates is coordinates underscore flat of colon, comma, none minus, I'll show you what this code does. So now this is the array for storing my relative coordinates. And if I print this, it will look like this. So now look at the total number of items. I have 9 items along the row and 9 items along the column. And I have 2 such things. This is the first and this is the second. So now these are the all possible values of delta xy pairs. So delta xy pairs is this. So delta x is one of the delta xy pairs is 0, 0. Another delta xy pair is 0, -1. Another delta xy pair is 0, -2. So these are all the possible delta x values. These are all the possible delta y values. And if you pick the 0th item here and 0th item here, it is the delta xy pair. Like that, look at how many pairs are there. I have total 81 pairs. And I should have 81 pairs because not unique pairs though. I have total 81 query key value pairs, query key pairs. So my window size is 3 by 3, which means I have three tokens or 3 patches along the height, 3 patches along the width. So total number of tokens is 3 square equal to 9. So which means number of keys is equal to 9. Number of queries is equal to 9. So total number of query key pairs I can construct is 81, right? Which means I can totally construct 81 delta x comma delta y values. What are the delta x delta y values? The physical separation between query and key. Are they far from each other or are they close to each other? Now, out of these 81 delta x comma delta y pairs, everything will not be unique. That's what we're saying. You will have only 21 such pairs. So for example, here you see the delta x delta y value is 0, 0. But now look at this item. This is 0, 0. So many delta x delta y pairs will be repeating, because the total possible delta x delta y pairs you can have is the maximum value for delta x possible is +2, because you have only 3 windows. So +2 will be, this can be query and this can be key, or vice versa. So this is like at position number 0, this is at position number 2. So the distance between those delta x is 2. Minimum value possible is -2. The range of possible delta x values are 5, -2, -1, 0, 1, 2. Similarly, range of unique delta y values possible are 5. So totally unique delta x delta y values will be 25. Okay, so if you count all the delta x 81 delta x delta y values as per this, you will see that only 25 of them are unique. Okay, and then we say rel equal to rel dot permute of 1, 2, 0, and I'll show you what this does. This simply rearranges the pairs in this way. So now you have pairs close to each other, 0, 0. So this is delta x delta y. This is another delta x delta y. This is another delta x delta y. So now you have all the delta x delta y pairs. Then you say rel of 0 is equal to, so of 0 means this is the delta x value is equal to that plus number of windows -1. I'll tell you why exactly this is done. So you are adding some constant to your delta x values, and then you are adding some constant equal to this plus some constant. So the reason why this is done is my original range of delta x values were from -2 to +2. If window equal to 3, what is window -1? It will be 2. So what happens if I add a constant value of 2 to all possible delta x values? My delta x values will now range from what to what? My new range of delta x values will be from 0 to 4. So basically, this is just to avoid negative numbers in the relative, because I don't care about the absolute value. I just want unique set of numbers. So my relative positioning will be 0 to 4. So that is done for delta x and delta y. Now one more thing is done, which is this comma 0 equal to whatever is that number multiplied by 2 times window -1. So here what I'm doing is the x values. So these are delta x values. These are delta y values. So I added a constant number called 2 to delta x. I added a constant number called again 2 for delta y. So delta x values range were from -2 to 2. Now it will become from 0 to 4. Delta y will also become 0 to 4. Now I'm multiplying every single delta x value with 2 times window -1. 2 times window -1 is 2 times 3, which is 6. 6 minus 1 is 5. So now every single delta x value I have multiplied by 5. So what will be now the new range of delta x values? it will be from 0 to 20. Very good. Because my original range was from -2 to +2. That I shifted to be 0 to 4. Now I am scaling it such that it will be from 0 to 20. I'll tell you why this is done. So first, let me show you when I print the value of relative, you should understand what is the cool thing about this. The cool thing about this is, let me do one more thing. Rel of 0 equal to, okay, this is fine. And now index equal to rel dot sum of -1, and maybe I can print index. Now, what I have done is a range of delta x values will be now 0 to 20. Range of delta y values will be from 0 to 4. And I'm saying that I'm adding the delta x and delta y value to get some numbers. And look at those numbers. The number that is resulting, I have now 81 positions, right? I have 9 tokens total as query, 9 as total as key, which means I have total 81 unique, not unique, I have total 81 query key value pairs. And somehow I should be able to say, if I were to pick query key pair from index 0, 0, it has an index of, let's say, 1. Then if I pick another query key pair from somewhere here, let me repeat by drawing a new picture. My goal is this. I should be able to just tell with one number that if my query key value pair query is this and key is also this, or if query is this and key is also this, then when I'm looking at my table, I should look at ideally the same item in the table, right? So I'm basically converting my query key pair into one single index. So the index corresponding to this, if this is 3, index corresponding to this will also be 3. Now let me ask you what exactly should be the index. So what we did was, this was 3 and this was 3. Now let me just delete this. Now assume that my query is this item, key is also that item. Okay. Now, what was the original delta x and delta y in this case? Delta x, delta y was 0, 0, correct? After shifting delta x, what happened to delta x? We shifted the delta x by window -1, correct? Window -1, which means 0 will become 2. So this will become 2, 0 after only shifting delta x. Now, after shifting delta y, what will this become? 2, 2, correct? Because delta x and delta y both we shifted by 2. Now we did scaling for the delta x. We scaled the delta x by a factor of what? 2 times window -1, which is 2 times 3 -1, 5. So this will become 10, 2. So now my new, after scaling and shifting, after shifting and scaling, my delta x new, delta y new will become 10, 2. Now what I'm saying is, my index will be simply the sum of these two. So my index will be 12. So now look at this. What does 12 mean? If the index is 12, it means query and key have 0 shift relative to each other. They are at the exact same position. Correct? Now, let's take this example. Let's say my query was here and key was here. What is the delta x in this case? Delta x was originally 1, delta y was 0. Delta x I will scale, I will shift by 2. So 1, 0 will become 3, 2 after delta y shift. Then I will scale by multiplying with 5. So this will become 15, 2. So now what is the index corresponding to this? 15 plus 2 equal to 17. So these two pairs will have an index of 17. These two pairs will also have an index of 17. Every pair that with a delta x shift of 1 will have an index value called 17. Every query key pair with no shift, meaning query key at the same place, will have an index of 12. What about index of 0? Which pair will have an index of 0? I don't know if any will have a 0, but they will. Please don't assume that just because index is equal to 0, don't assume that delta x comma delta y equal to 0. That's not the case. The original delta x delta y was 0, but then delta x we shifted, delta y we shifted. This is just to create unique indices. So I'll just print the index and just have a look at this. So these are the printed indices. Now look at all these numbers. What does this mean? This means these are all the different query key pairs where query and key are the same index. So those 9 items are basically, this is the query, this is the key. Similarly, this is the query, this is the key. This is the query, this is the key. Like that, how many items you have? 9 items you have, because it's 3 by 3. So if query is the item number 1 and key is also the item number 1, meaning the index of query is corresponding to token number 1, key is also corresponding to token number 1. Similarly, query is corresponding to token 2, key is corresponding to 2. So you have such 9 items. All those 9 items will have the index of 12. Something will have index of 0 if they are farthest apart along, I would say, the probably the diagonal. Maybe we can calculate it. So let's say delta x delta y was 2 comma 2. This is the farthest item, right? Delta x is 2, delta y is also 2. So after shifting, this will become 4 comma 4. After scaling, it will become 20 comma 4. So this index will become 24. So one of the farthest items will be 24. Is that correct? See, 24 is the farthest item. Now let's look at the other farthest item, minus 2 comma 2. Perhaps they are also far away. So minus 2, after shifting, minus 2 comma 2 will become 0 comma 4. And then after scaling, this will become 0 comma 4 itself. Then after adding, it will be 4. So this is not the 0 item. How about minus 2 comma minus 2? If it is minus 2, after shifting, this will become 0 comma 0. After scaling, it will remain as 0 comma 0. And then index will be 0 plus 1, 0 plus 0 equal to 0. Yeah. So basically, this item corresponds to the index where query is at the position 0 comma 0 and key is at the position 2 comma 2. So they are farthest away from each other. Delta x is 2, delta y is 2. This 0 corresponds to the item where query is at 2 comma 2 and key is at 0 comma 0. So basically, this is now the table of indices corresponding to delta x, delta y values. I mean, this is one small part of our code. I'm spending too much time, but I hope you understand. It's basically constructing a table of unique indices. So let me just copy this. 25 unique indices. I should not say unique, because when I say unique, you will think there are 81 unique indices. That's not the case. There are 25 unique indices. Okay. Then we call this function called register buffer. So the register buffer is defined in nn.module, and here we say position underscore index. So we store it in this variable. Is basically this index. We will use it later, not right now. Then self.relative bias. So this is where we define the relative bias, relative position bias term. Self.relative bias is equal to, this should be obviously a learnable parameter. So nn.parameter of torch.zeros. And how many position bias should I have? I should have a range of values from 2 times win minus 1, comma 2 times win minus 1, which is 3 times Windows is 3. So total, my spelling mistake. And then I need position bias separately for different heads. So number underscore heads. I'm sure there is some syntax error. So there should be this is a 2D array. Okay. 2 times win minus 1, comma 2 times win minus 1. And so total number of values should be, its range should be from 0 to 0 to 24, basically. So 2 times win minus 1 is 2 times 3, 6, 6 minus 1, 5. 2 times 6 minus 1, 5, 5 times 5, 25, which means the range will be from 0 to 24. Okay, so this is fine. I think I'm missing one bracket somewhere. I'll see. I think torch.zeros of this, and yeah, number of heads should be here. All right. So that is the relative bias. So now we have relative bias. One thing we have not defined yet is the mask. So mask we should define a little bit. We'll define a little bit later. So that is the window attention class. And now we can define the forward pass function. So define forward, and into this usually we pass self comma x. And if anything else is passed, we can pass that also. So here actually we can pass, mask, and mask by default, there is no mask, which means none. And this is only for regular window. Regular window does not have any mask. Shifted window has mask. And then we say batch underscore, which means we don't know what is the batch dimension. So we just say the calculated batch dimension, comma n, comma c is equal to x dot shape. So this is what comes into the x is what is there available in the window attention. And then we say query is equal to self dot q of x. Key is equal to self dot q of self dot key of x, and same for value. And now we can take the dot product. So q is equal to q times scale, which is 1 by square root of d, q times self dot scale, because we scale the queries before multiplying with the transpose of key, and the attention before adding the relative position bias and before adding the mask term is q matrix multiplication followed by k dot transpose. And when we are transposing the last two dimensions. So -1 is the last dimension, -2 is the second last dimension. So this we are transposing. Basically, we are doing k dot t. The only thing is k also has batch dimension. So just to make sure that this can be, I think, k dot transpose of 1, 2 also. This can be written as 1, 2, which means it will take the first dimension number 1 and dimension number 2. But ideally, what we are trying to transpose is the last two dimensions, which means last dimension is -1, second last dimension is -2. And then we calculate the relative position bias. So RB equal to self dot rel underscore bias. And this is for a certain position. So self dot position underscore index, which we have passed here into the function, and dot view of -1. Basically, all the 0 to 5, all the list of values will be seen as one single table. When you say -1, we are basically looking at it from just one dimension. Let's not go into the detail. If you just simply print this, you will see what the position index dot view does. Then dot view of n, -1. I'll explain after a little bit, after we proceed a little bit, why exactly are we expanding it into n, -1. Then attention equal to attention plus relative position bias, which is RB dot permute of 2, 0, 1 dot unsqueeze of 0. Let me show you why exactly are we doing these things. Maybe I can do it after masking is also added. So just understand that here that this is just to take care of dimension, all these indices thing. I'll explain that in a little bit. But broadly understand what we are doing. We have the query key value. Then to add to that, we add the relative position bias. Now we have to add the mask. So if mask, basically if mask is none, then we don't have to add anything. If there is no mask, we add nothing. But if mask is not none, by default, we are passing mask equal to none. But if mask was not none, which will happen in the case of shifted window, the number of windows is equal to mask.shape of 0. So these are the total number of windows. And then we say attention is equal to attention.view of whatever was this B divided by number of windows, comma, number of windows. So whenever we divide by this, if we are viewing, we have to multiply with the same thing, which is why when you divide by number of windows, you add extra dimension, comma, number of windows. I'll explain this part also in a bit. Self dot number of heads, comma, m, comma, n. Then attention is equal to, so now attention is in the right dimensionality, attention plus mask dot unsqueeze of 1 dot unsqueeze of 0. And then attention, I know that there are a lot of matrix manipulations here, but let's go through that once we write the code so that coding is not delayed. I just want to make sure the code works at the end of the day, comma, n, comma, n. So now we have the attention with the bias term added, and mask, if it is there, mask term also added. After this, what do we usually do? We take softmax, right? So then attention, n is the total number of tokens. N by n is the total number of tokens in each window. I'll come to that. Then attention equal to attention dot softmax and that too along the column dimension. So dimension equal to -1. So we take the softmax, and then after this we matrix multiply with value matrix. So then we say the final output we have is attention matrix multiplication with value. But whatever we get, we have to take a transpose. I'll say exactly why we are taking the transpose. 1, 2 dot reshape of bash, comma, n, comma, c. Then we say output equal to self dot. So we have to now do this projection, which I mentioned earlier. After calculating the attention, we have to use this projection layer to mix different outputs from different heads. So self dot project of out, then return out. So this is the part where attention is calculated. Now let me show you the details of these lines, because I'm pretty sure several things are unclear here. Before that, let me just run this to ensure that there is no syntax issue or anything. Okay, this is running. Okay. Okay, this you understood. Window partition you understood. Window reverse also we explained. Window partition is done just before attention. Window reverse is done just after attention. Now what we are discussing is attention. So in attention, these are the things we did, right? We have query key values. We have relative position bias, which is the Bij term. We have the attention mask Mij term. Then we first calculate Q by square root of D. Then we multiply it with the transpose of key. Then we add relative bias. Then if mask is there, we add that. We apply softmax. Then the final context vector matrix is softmax of attention multiplied by the value vector. This is conceptually, this is what we are doing. But code wise, okay, window reverse part we already discussed. But yeah, let's quickly go through relative position bias. Let's say my window is 3 by 3. I have totally 9 tokens, which means I have 9 queries and 9 keys. So total query key pairs are 81. This is very clear. So the range of values of delta x will be from -2 to 2, which means there are totally 5 possible delta x, delta y values, which means total 25 unique delta x, delta y pairs. So this we have to now construct into a sort of like a lookup table. So in this lookup table, what we are doing is we are constructing indices, which is just one number. That number ranges from 0 to 24, where 0 means it will mean a particular delta x delta y value. 24 means it will be a particular delta x delta y value. Here we discussed that 24 is resulting from plus 2 comma plus 2 delta x delta y. 0 is resulting from minus 2 comma minus 2 delta x delta y, and 0 comma 0 delta x delta y value was resulting in what index? What was the index corresponding to this? 12. All the columns, all the diagonal values were 12. Okay. So this is the position bias. Then what we did was we had a line like this, self dot relative bias. So in the code, this was the line. RB equal to self dot relative bias of, then we were calling the items in the table. Then we were kind of adding more dimensions to it. So what we are doing is position index. You might have seen this was n by n, which was 25 by 25. Correct. This was the table size, because table size was 2 into window minus 1 multiplied by 2 into window minus 1. These many items were there. So this was, window was 3. So 6 minus 1, 5, 5 by 5. So it was 5 comma 5. 25 comma 25, if I'm not wrong. 5 comma 5. Then what we are doing is we are creating the position index as a list of values ranging from 0 to n by n, 0 to, so totally 25 indices ranging from 0 to 24. So position index dot view of -1 will ensure that if you had two-dimensional grid of values ranging from 0 to 4 and 0 to 4, you will be converting that into an index consisting of 25 items, a one-dimensional array consisting of 25 items. Those 25 items will correspond to the 25 relative position bias items. Then what we have to do is we actually have multi-head self-attention, not single head. And if you remember the part where we defined this relative bias, there was a comma number of heads. So comma number of heads means for each head, we have separate relative position bias learnable parameter. So for example, if my window size is 3 by 3, right, I have totally, instead of 81, I have 25 unique position bias values. But if I have 4 such attention heads, I have to learn 25 for attention head number 1, 25 for attention head number 2, 25 for attention head number 3, and so for 4. So for each head, I have to learn it separately. So here what we are doing is self-relative bias is basically, by default, it was 25 comma number of heads. And what we want to do is we want to go from, if I had 25 items that are unique in a table, I actually have 81 items because I have 9 queries and 9 keys. But then like this, I need one for each head. So I need one table like this for head number 1. I need one table like this for head number 2. But within each head and within each table, only 25 items will be unique. So what we are at the end of the day doing is we are converting this relative bias into something like n by n for each head. So n by n will be 5 comma 5, and it will repeat for each head. So total number of learnable parameters will be 5 times 5 times number of heads, basically. So if number of heads is 3, I will be learning 75 unique items. So in short, that is what we are doing. And then finally, what we get out of this, attention equal to attention.rb.permute of 201. So 201 means the original dimension was, this is 0 dimension, this is first dimension, this is second dimension. We switch it like that, like this, in such a way that you go from n comma heads, you go to heads comma n, and then you add a batch dimension also. So then you try to add a batch dimension also. So now what this means is, you, for every batch, so you have 2 batches, let's say, for every batch, you have n number of heads. And for every head, you have a lookup table, which has n by n unique items. And these items will now be added with the self attention. So that is that is happening at the end of the day. If I end up spending a lot of time on this line, it will take me another 1.5 hours to code the rest of the code. But let's understand this from a broader level. From a broader level, we are simply trying to add mask value and relative bias value to the query key dot product, scaled query key dot product. From a slightly zoomed in perspective, the reason why we are doing this unsqueeze or this view operation is just to make sure that the dimensionality when we are performing addition and multiplication are all matching, because we have batch dimension, we have numbers associated with number of heads. So all the dimensionality should match each other when we are adding or multiplying these matrices, which is the reason why we are often doing a permutation of the indices or performing this unsqueeze. Unsqueeze meaning you add one extra dimension. In mask also, we are doing, okay, we have to calculate normal self-attention for each head. Exactly. So self-attention will be, self-attention is already calculated over here. Attention is equal to query times key transpose. And this is done for different heads separately. And then at the end, the output is concatenated. PyTorch will take care of it. We don't have to do it because we did not define the query weight matrix as something of dimensionality head dimension. Like usually, if we were implementing simplified self-attention, we would have said that the dimensionality in the query space is head dimension, dimensionality in the key space is head dimension, and in the value space is also head dimension. For each head, like that, we will have num heads. So ideally, we'll have to calculate for each head context vector matrix and then manually concatenate it using for loop. So, but then I hope you remember from one of our earlier lectures that we can do it in a much more efficient way by just considering one query matrix, one key matrix, one query weights matrix, one key weights matrix, and one value weights matrix. That is basically what is being done here. So query key value being in multi-head attention is automatically taken care of here. And then after you have query key values, you calculate first the attention scores. Then to the attention scores, you add the relative bias. Then optionally, you add the mask value. If you are in the shifted window, if you are in the regular window, your mask value will be none, which means this entire if condition will not be applicable. Then you multiply with value to get the final output. I will come back to this, why we are doing this unsqueezing just to match the dimension in a little bit. But what I will do is I will anyway share I have written detailed reasoning why we are doing a certain unsqueezing operation here. So I recommend you to go through it, but let's just go ahead with the coding part. And if we have time a little bit, we will come back to the this unsqueezing operation. It's actually very simple, but let's rather spend time on coding the next part. Okay, so now we have what? We have the attention defined. So now after this, we need to define the Swin block. So this, let me delete. This is just for the example purpose. We don't need this anymore. Coding Swin block. Now class Swin block of nn.module define underscore init underscore, then we pass self. Then we have to pass bunch of things here, but we'll see that. Then super init. So we are initiating the init constructor in the parent self.dim equal to dim. So we have to pass the dimension, embedding dimension here. Then self.resolution. So here we are passing the image resolution. The only reason why that is done is different stage. Depending on which stage the Swin block is, the resolution is different. I hope you remember that from here. So in the stage number 2, the resolution was h/4 going input resolution. Sorry, h/8. In stage number 1, it was h/4. So the resolution truly depends on which stage of the Swin transformer we are at. So Swin transformer block needs to know what is the resolution of the input. So that is why we are defining this self.res equal to res. So we pass resolution here. Then self.number of windows, that also passed here. Then self.shift. So shift is the amount by which we are adding the shift. this, I hope you remember the shift value was m by 2, where m is the width of the window, or integerized m by 2. So if m is, let's say, window size is 7, the shifting will happen not by 3.5. There is no 3.5 patches. Shifting will happen by 3. So we have to pass the shift value. For regular window, shift value will be equal to what? What will be the value of this variable for regular window? 0. For regular window, there is no shifting. For shifted window, the value will be whatever is the window size divided by 2. So if window size is 7, divided by 2 is 3.5, rounding down to the integer is 3. Then inside the Swin block, look at what all things are there. You have a multi-head self-attention, you have 2 layer normalization and 1 multi-layer perceptron and residual connection, right? Same as the normal transformer. So let's define 2 layer normalization. So self.norm1 is equal to layer norm of, layer norm should be along what dimension? What should I pass here for both layer norm actually? Self.norm2 equal to layer norm of what? I'm normalizing along embedding dimension. So every single, I just need to mention the embedding dimension. That's it. So first will be dim. This also is dim. But here it should be nn dot layer norm, because it's inherited from nn module dot nn dot module. So those are the 2 layer norms, but let me not confuse you by writing them together because they are not applied together. So after the first layer norm, I have my attention. So self dot attention equal to, here is where we define, where we use this thing which we have defined, window attention. So we copy paste that window attention off, and into the window attention, I have to pass bunch of things: dimension, number of heads, and win. So dimension, number of heads we have not defined yet, so that perhaps we can define here as h heads, and then heads we can directly pass here, and win is the window size. So these were the 3 things we needed to pass. Then after this comes the self layer norm 2. So layer normalization 1, attention, then layer normalization 2, and followed by this multi-layer perceptron, self dot MLP. So MLP will be nn dot sequential. Then first item will be nn dot linear, and it is projecting from dimension to what? Usually what is done, if you remember from the transformer, we project it to a 4x dimensional space, right? 4 times dimension. Followed by that, we have an activation function, which is JLU. We can use RayLu also, does not matter. Then you project it back from 4x dimensional space into your original dimensionality. So this is multi-layer perceptron. Okay. And depending on whether your Swin block is with or without shifting, you have to define a few things. So firstly, h comma w equal to resolution, which means resolution we can pass here. Actually, resolution we are already passing here. So this can be called as res. Then h comma w equal to res. Then if shift is greater than 0, meaning if this is not a regular window, if this is a shifted window, only then we have to define a mask. So then self dot mask equal to, then here we have to define like a create mask function, but let me first write it, self dot create underscore mask of, where we have h patches along the width, along the height, along the width, number of windows, and what is the quantity of the shift. So this we have to pass into the mask. This we are yet to define, but I will define that soon. Else self dot mask equal to what? What should be self dot mask? None. Because if shifting is not there, if it's a regular window, we don't have any mask. So default value of mask will be none. Now we can define the create, define this create mask function. So define create underscore mask, into which we pass self, comma, rest of these things. Oh yeah, thank you so much. Yes. These minor things will cause issue, and we'll have to spend a lot of time figuring this out. Where is the issue? Okay, and image mask equal to torch dot zeros of so we don't need we just need 4 dimensions, h comma w comma 1. This is okay if this is 1. In broadcasting in Python, there is something called broadcasting. If we are adding mask to something, and if that something has a batch dimension of B and channel dimension of C, automatically Python will broadcast this into the rest of the dimension. So we don't have to explicitly mention the value here. Then count equal to 0. I'll show you why this count is done. Now we need some we need some indices for our window ID. Basically, we said window ID for patches belonging to the ID of the patches, if they are belonging to the same window, should be the same. So what we are going to do now is we are creating something called slice. So for h in, so we have totally 3 slices. So h in slice of 0 comma minus shift, or no, not minus shift, minus win. I'll explain what this is doing, comma minus win comma minus shift. So that is in h, and so basically I have 3 patches along height and 3 windows along height and 3 windows along width. So w in 0 comma win, I think this is fine. Count or image mask equal to image mask of comma h comma w comma this equal to count, and then count plus equal to 1. So what is done here is pretty simple. So basically what we are doing is we have 3 vertical slices and 3 horizontal slices when we are shifting. Something that looks like this. There is this corner items, there is this corner item, this item, these items. So originally there were 2 by 2, but after shifting we'll have 3 by 3, and then we have to just mention ID. So totally we have to go through 3 items along the row and 3 items along the column. So basically there are 3 vertical slices and 3 horizontal slices. So this is the first vertical slice, this is the second vertical slice, and this is the third vertical slice. Similarly, this is the first horizontal slice, second horizontal slice, and third horizontal slice. Now, depending on which slice you are in, you can mention the ID. Then count. So basically you maintain a variable called count, and the image mask value for that h comma w will be the count value. We can print this to see how it looks. Then mask equal to window. So mask also we have to pass through window partition, because mask is added inside the attention. So inside the attention, by the time your inputs reach the attention, you had already passed the inputs through window partition. And that is the reason why you could process it on a window basis inside the attention. So same thing you have to apply for mask. So we apply window partition for mask also. Window partition you had defined here, window partition and reverse partition, window reverse, window partition and window reverse. We have not touched window reverse yet. Of img mask comma windows, then mask equal to mask dot view. This is just to adjust the dimensionality, -1 comma win times win. So here again there is bunch of dimensionality maneuvering that we have to do to make sure that we are this is not correct. We are getting correct dimension before we add the mask to the query key dot product. Mask dot mask fill where mask not equal to 0. And basically, if the mask is not null, we said that we usually add something like minus infinity, a huge number as the mask value. This, if you remember, we did. Why did we say that the value of mask ij is minus infinity if there is mask present? The reason is we want the softmax value to go to 0 if the ID of the window was different for two different patches, because two different patches from two different windows should not have attention score with each other. Their attention score should be 0 or a very small number. Here we can define it to be like minus 10,000 or some big number, so that the softmax value goes to a very, very small number. Let's keep it a floating point. And then we simply return mask. So we are still in the mask function. So from the mask function, we return this mask value. And now we can define the forward pass. Define forward of self comma x. Then you have batch comma L is the total number of length of tokens. B comma L comma C is the channel equal to x dot shape. Then height and width are okay. Something is missing. Define okay. Indentation was wrong. So h comma w equal to self dot resolution, because resolution we were passing in here. Then okay, so now we are in the window the regular self attention transformer block or shifted window self attention transformer block. So we have the inputs coming in. We have to store the residual. So residual equal to x, and we have to add it later. Then x equal to, first we do the layer normalization. So self dot norm 1 of x. We had defined norm 1 here. Then after layer normalization, we make it pass through attention. So x equal to or one more thing we have to do. Yeah, norm 1 of x, and x equal to x dot view of batch HWC. Now, are we ready to call the attention, or are we missing something? Before the attention, we have to do window partition, right? Then only we can call the attention, and after attention, we do window reverse. So then we can say if self dot shift not equal to 0 or greater than 0, meaning if we have a shifted window rather than a regular window, then we say x equal to torch dot roll. So this function allows us to perform that rolling operation, the cyclic rolling. Shifts equal to minus self dot shift comma minus self dot shift. So we are shifting by m by 2, by minus 3 to the left hand side direction, minus 3 to the top direction. I mean 3 by 3 points to the left, 3 to the top. And dimensions along which the shift happens is the first and second dimension, because first and second dimension are the height and width dimension. And so if self dot shift is greater than 0, then we do this cyclic rolling operation. And then we have to do the window partition. Win x equal to window underscore partition. This function was defined earlier. Into this we pass x comma self dot window size, and whatever comes out of window partition, we arrange it in a dimensionality like this. Comma C. Then once we do the window partition, we can do the attention output equal to something, and then we have to do again window rolling. So then we can say window reverse underscore reverse, and into this we have to pass a few things. And after window reverse, we have to unroll. So whatever rolling we did, we have to unroll. This is called cyclic reverse shifting. So for that, all we need to do is we shift it back, which means this minus we replace with plus. And so this we are yet to fill. Okay, we'll come to this. So attention dot out is self dot. What was the name? Self dot attention, ATTN of window underscore x. So whatever we get out after window partition, we pass that, and then mask we have to pass mask. But one thing we have to do is whatever CPU or GPU we were using, same the mask also we should convert to this. So whatever device mask was using, same device attention calculation should also use. So self dot to device dot device dot x dot device. And but this we need to do only if there is a mask, otherwise we don't have to do. So if self dot mask is not none, else none. So basically what we are doing is we are passing the mask as not none if there is a mask. Otherwise, if mask is none, we are just simply passing none. Okay, then x equal to window reverse. Into window reverse, we pass whatever output we get from attention. So after whatever output comes from window partition, we pass to attention. Whatever output comes out of attention, we pass to window reverse. Attention output, comma self dot win, comma height, comma w. These were the arguments to the window reverse function. And then this is the reverse cyclic shift. And then we have to add the residual. So after the multi-head attention, we have to add the residual. So x equal to x plus residual, or residual plus x dot view of bash comma L is the number of tokens comma C. And then we are ready to do the one more layer of self normalization, x equal to self dot norm2 of x. So this is the second layer normalization. Actually, I can store one more residual here. So residual 2 equal to x. And then I say x equal to self dot MLP of x. And then after MLP, I just say x equal to x plus residual 2. So now this is the part where the second layer normalization MLP and residual comes. I'm just storing the residual here. This is the part where, okay, let me just delete some space so that so this whole thing is the part where we do layer normalization number 1. We perform cyclic shifting if we are having a positive shift. Then we perform window partition so that we can perform attention within each window. Then we calculate the attention. Then we do window reverse so that the batch dimensionality which was lost during the attention calculation is coming back due to window reverse. And then if cyclic shifting we had applied, we apply a reverse shifting so that now we don't have a shift anymore. And then we add the residual. So this will complete the first part of the first half of the transformer block, this from here till here. And then we have one more layer normalization, MLP and residual. So that is layer normalization number 2, multi-layer perceptron followed by residual number 2. And then we can simply output this, return X. So that is the Swin block. Now a bit more is there to write, is class patch merging. So patch merging, if you remember, it is this guy where the dimensionality, spatial dimensionality was becoming half and half. The channel dimensionality was becoming 2x. So class patch merging nn dot module, then define underscore underscore init. Actually, let me try running the previous class just to make sure it works. Okay. Then self dot dimension, embedding dimension equal to embedding dimension. We have to pass that. Now, first is we reduce the spatial dimensionality by combining 4 neighboring patches. So self dot reduction equal to nn dot linear of 4x dimension. So first we will have a 4x dimensional thing. From that we'll go to 2x dimensional. And bias, yeah, bias can be false. There is no bias we are adding. Then in that layer, there is one layer normalization. We have not discussed this in the lecture, but a layer normalization is added. 4x dim. Then forward pass. So this is a relatively straightforward function. Self comma x comma height comma width. Batch L C. L is the total number of tokens, is equal to x dot shape. Then x equal to x dot view batch height width channels. Now we have to extract 4 patches and then concatenate them along the channel dimension. So patch number 0, patch number 1, patch number 2, and patch number 4. So these 4 patches we have to do, and we have to extract, and then after extracting we can simply reshape that into a dimensionality like batch comma -1, whatever that dimension is, comma C. I can do that for all the 4 patches. And then simply concatenate them along the channel dimension. We are yet to do this extraction, but that is just one line of code. Then we say x equal to torch dot concatenate. And here x0, x1, x2, comma x3, comma, this is concatenated along the last dimension, which is the channel dimension. And then we apply layer normalization, x equal to self dot norm of x. So this layer normalization comes inside the patch merging just before you get it out so that you can pass it to the transformer block. And x equal to, in fact, just before the reduction. So reduction we had defined here. This is where you go from 4x dimensional to 2x dimensional, because 4x dimension results from this patch concatenation, and 2x dimension resulting from a linear projection. Reduction of x, and then return. You are returning now x. You are returning the resolution. Your resolution will become half, h by 2 and w by 2. And here we have to extract the 4 patches. So x of to 2, then 2, and then this should be 1 to 2. Yeah, I think this will work. Basically, we are extracting 4. Yeah, I think this is correct. Let's run this and see if there is any error. We'll fix this. But basically, this extract is 4 patches, concatenates them along the channel dimension. After concatenating, we do one layer of layer normalization and then reduce it into 4x dimension to 2x dimension. So you go from 4x to 2x through a linear projection. Okay, that is patch embedding and seems to be working fine. I think now we are pretty much done. Now the last thing is we just have to define the full Swin transformer multiple stages, but we won't be writing 4 stages. 4 stages too much. We'll just write maybe 2 stages. So class 2-stage Swin MNIST for MNIST. nn.module and define init dot underscore init and self and a few other things. So first is we have to perform patch embedding. So we'll come to that. So first embedding dimension. So self dot embedding dimension equal to embed underscore dim, and we have to pass this. Then second is self dot patch underscore embed equal to, and this was how did we do this? Using nn.con2d. And input channels was 1, output was whatever was the embedding dimension. Initially we were doing one step we are skipping here. In actual transformer, Swin transformer, we first go from 1 to 48, and then from 48 you have a linear projection to whatever C dimension it's. We are skipping that step. Then kernel size is equal to 2 because it's MNIST and we don't need big patches. Stride equal to 2. So this is the patching, and then initial resolution after patching will be simply 14 by 14. Now we can define stage 1 of the Swin transformer and stage 2. Stage 3 and 4 we will skip because we can't divide the spatial resolution too much anyway for MNIST. Then self dot stage underscore 1 or stage 1 blocks equal to nn dot sequential. So what all do we need here? We need in each stage of the Swin, we have 2 Swin blocks, right? So we have to call this class Swin block class. And that too we have to do twice. So we have to call this twice, but there is some small difference. To this, the shift will be 0 because this is regular window. To this, the shift will be 7 if our size is window size is 7, shift will be 3. So to this, the shift will be 3. But then there are a few more inputs we need. First is self dot stage 1 shift equal to 0, embedding dimension. So that we'll pass to both. Then number of heads, that we'll pass to both, and heads we should pass here, and the window size equal to win. So we have to pass windows here. Then shift. Now we can also define the values, and there is number of classes also. So for MNIST it is 10, so we can just set default value. Window size, let's keep it 7. Heads, let's keep it maybe 3. And embedding dimension should be a multiple of 3, of course. So let's keep it 48 itself. Okay, these are the numbers. And then stage 1, you have Swin block. So in stage 1, you must note that there is no patch merging. In stage 1, you simply have this linear embedding. In stage 2, you have patch merging. In stage 1, there is no patch merging, because before you are for the first time you are getting the patches. Merging happens only after stage 1 onwards. So that is stage 1. In stage 2, you copy paste almost the same thing, except stage 2 resolution. Stage 2 resolution equal to initial resolution, whatever was the initial resolution of 0 by 2, because by the time you pass the first stage, the resolution would have reduced by half, which will be 7 by 7. Then stage 2 blocks is nn.sequential. But before that, we have to also do patch merging. So self.patch underscore merge equal to patch merging class. Embedding dimension and merged dimension equal to whatever was embedding dimension multiplied by 2. So the dimensionality after stage 1 to stage 2 goes from C to 2C. So embedding dimension multiplies by 2 after each stage. The spatial dimension divides by 2 after each stage. Okay, so that is almost it. We are pretty much ready. So we have to now pass okay, we forgot to pass the initial resolution. So initial resolution, because resolution is expected as one of the inputs in the Swin block as the variable name under res. Then we pass stage 2 res here. And I think that's pretty much it. And one more thing. Yeah, so window. So here there is one small thing you need to note. So if I divide win equal to win by 2, and this is win by 2, shift is equal to 0. And here shift equal to whatever was the window size divided by 4. This causes a bit of dimensionality issue, but we'll fix this at the end. Okay, so just keep a note of this. This will cause an issue because MNIST is a very small resolution image. Then self.layer norm of equal to nn dot layer norm, and that happens along whatever is the merged dimension. And self dot fully connected layer. So now we are out of the Swin transformers. After stage 2, we don't have transformer anymore. We just now want to perform global average pooling, and we also want to have a fully connected layer going from merge dimension to 10 classes. So self dot fully connected equal to nn dot linear from merge dimension to whatever is the number of classes, num underscore classes. So this is where the classification happens. Now we are ready to define the forward pass. Self. Yeah, we did not define yet because that we can do inside this forward function. Then x equal to self dot patch underscore embed of x. So this patch embedding, once we have the patch embedding, we want to know the batch height, width, batch channel height and width equal to x dot shape. Then x equal to x dot flatten of 2 dot transpose of 1 comma 2. So this is where we are flattening this whatever patches we get after con 2D operation, we are flattening it here. Then those flattened patches, the total number of tokens or patches is h multiplied by w. Then x equal to self dot stage 1. So this is where the stage 1 of the Swin transformer comes. Then x equal to self dot. So con2d is already applied in patch embed, right? This patch embed already applies the con2d operation. So I'm defining patch embed here, self dot patch embed of x. Then stage 1 blocks and x comma height comma w equal to self dot patch merge. So patch merge we had defined here with the patch merging. So it's the object corresponding to patch merge class, x comma h comma w. So h comma w will give us the new resolution after patch merging. Then the new number of tokens is L equal to new h multiplied by new w, whatever we get out of the patch merging. And new number of channels, this is very simple, C times 2. Then x equal to self dot stage 2 blocks of x. Then we do one more layer of normalization, norm of x. So this norm we have defined up here, then fully connected. But before fully connected, we have to do global average pooling. So the last step is x equal to self dot fully connected of x. But before this, we do average pooling. So x equal to x dot mean of dimension equal to 1. So the so that we basically have only batch dimension and just one more dimension for the tokens. Fully connected of x. I think that's it. Then we can just return x. That's a lot of code. I hope everything works at the end of the day. So now we are ready. We are pretty much, now everything is standard. I simply can copy the training part. So we get the training data from data load, this data sets, and then data loader is used for creating batches. These are the only two things which I have not used in the last lecture. These are normalization, standard, mean and standard deviation for MNIST. So these values are famously available on the internet. Then that's pretty much it. And then after this, we can just define the train test loops. So this is the whole code. Now let's keep our fingers crossed and let's see if it works or not. I'm sure there will be a dimensionality error at the part where we, yeah, argument size failed to unpack. I think somewhere we forgot to divide to make it into an integer. Let me ask. These h and w should be integers, but it would not happen if we simply divide by 2. We have to convert it into an integer. So I am sure somewhere I missed dividing. Swin blocks number 2, merge dimension. Yes, that is correct. It should be merge dimension. It should not be the embedding dimension. And because embedding dimension, whatever was there initially would be changed by the time you reach the second stage. Yeah, now this error primarily happens because your number of pixels in your MNIST is so less. So what I am going to do is, this is a little bit of cheating, but that's okay for demonstrative purpose. Here I will not divide the window size. And here I will say the shift is here also, it's window by 2. So I'm going to do that. And then hopefully dimensionality issue should be fixed. Tensor B. And then I will do one more thing. Let's ignore the stage 2. What if I did not have stage 2? So patch merging is not needed because I'm not using stage 2. And then if I run, we should pass embedding dimension to layer normalization. Of course. So that I am passing because here I'm saying merge dimension equal to embedding dimension and I'm passing merge dimension. So I'm just bypassing that. Yeah. So this part is fixed. Where else is the error? Let me do one thing. I have a working code which I just ran just before the lecture. We can compare these two. I'm sure while writing so many lines of code, somewhere some issue will come. So this code is working. It's pretty much, it's almost exactly same as this because I used this code. This code was built with the same purpose, but I just want to know where is the difference. So here I have commented the stage 2 block, but I forgot to comment these 3 lines because if stage 2 is not there, I don't necessarily have to do the patch merging and this resolution adjustment. So these 3 also ideally should be commented. But anyways, let's say I did not do that. And this I kept because although I'm defining the stage 2 resolution inside the class, it's not being used in the forward pass. So there is no harm in just keeping the code there. And here I had done the the shifting was windows by 2 and the window size I did not. Okay, here ideally this should be just window. This I forgot to add. So there are a few things. What I will give you as an assignment is instead of doing this for MNIST, because MNIST resolution is so less, there are 2 options. One is you can add a padding to MNIST to make sure that the resolution is slightly high so that by the time you reach second stage or third stage, your resolution is not becoming too small. Because I think somewhere that is causing dimensionality issue. The other thing which I conveniently skipped here is stage 3, stage 4. I completely skipped, of course. I did not try without relative position bias. You could definitely try without relative position bias because in the paper, when they did experiments without any position embedding and with normal absolute position embedding and with relative position bias, they got slightly different results, but not too different. So that is one thing you guys should definitely try as an assignment. So I will give you that along with the code. I'll give you this working code also. Just try running this on your end. I'm not sure if my code is working for any of you because I have made a minor mistake somewhere. I simply cannot figure out right now. So this code, please do try. But see, the accuracy is pretty good. I'm effectively only using one stage. And I mean, it's only MNIST, so it should be high. I mean, even any simple classifier can give good accuracy in MNIST. So that is basically it. So I know the parts where I had to go a little bit fast. One part is this squeezing, unsqueeze operation to expand the dimensionality of some variables. So that I have clearly denoted here, like mentioned in the notebook. If I get time, I will record a separate video so that you can go through it on your own time. Anyways, the broad overview, I hope you understand properly, but the main difficulty in the coding part of this is not about the broad overview. It's actually about the getting the code to work by matching all the dimensions. Second thing is, in my opinion, the most difficult part of this is, one of the most difficult parts is definitely the relative position bias. So this will take some time for you to understand. You can, but still here, if you just add a window, sample window dimension, you can just print and see what's happening. That is one part that is difficult. Another part that is difficult is this dimensionality adjustment of relative position bias. Another part that is slightly difficult is adjustment of dimensionality in the masking. Then inside the Swin block, most of the things are fine. Yeah, in the create mask function, there is a little bit of, I would say, finicky things going on in this slicing part. That is another difficult part. I won't call this as difficult. It's just like you will have to pay a little bit of attention to understand this. Another difficult part is window attention and window reverse is kind of easy. If you just write down the dimensions on a paper, you can understand. Patch merging, in patch merging, probably the only part that will be unfamiliar to you from a syntax perspective is only this. The rest of the things are pretty straightforward in patch merging. And in two-stage MNIST also, everything is fine. I don't think if the previous things are clear, I think all the things here are straightforward. Yeah, that's pretty much it. So the most difficult parts where you might want to spend some more time after this lecture is to fully understand the code, is the dimensions, why we are doing this permute operation, which I have explained in fairly good detail, but I'm sure you have forgotten it by the end of coding. So just go through the lecture once more to understand the logic behind this permutation and this view operation. Then go through the relative coordinate, relative bias, position embedding bias construction. Then go through this dimensionality adjustment once. Then go through the mask part also, dimensionality adjustment, and this line of reshaping. Why are we doing this reshaping exactly? Concept, I'm sure you all understand here, but the more important thing is this reshape operation. In Swin block, everything is pretty much fine except the slicing part for mask for window ID. This part, just go through this block, this lines of 4 lines of code a little bit, and I think that's mostly it. Everything else, I don't think you will find any difficult, unless some weird simple syntax issues come. But these are my results. 94% accuracy after 4 epochs, fairly good. I think it's a good point to stop. I wanted to finish by 11 a.m. but took longer than expected. But after today's lecture, I'm pretty sure half of the things you did not understand, mainly because the code is so complex. It's impossible for a human brain to comprehend and think about so many different concepts at the same time. I have gone through this code at least 6 or 7 times now. Even still, some parts still confuse me. I sometimes forget, oh, why did we do this expansion? Why did we do this view operation at this point? So ideally, for me to understand this, I need a piece of paper and write it down. So that's the reason why I put it on Miro. So I also recommend you to just have a piece of paper and write down the dimensions and see what happens when each operation is performed. That's the best way for you to understand dimensions. If your goal is just to have a working code, then I think none of this is needed. You can simply try with Gemini. I'm sure you will get a working code. Second thing is the concept itself, the Swin transformer concept itself, the window shifting part is a bit tricky. If the memory of the last lecture is not very clear in your head today, you might not have understood that. That was a bit tricky part. The third part is the patch merging operation. So there are some finer details in the patch merging operation, which we discussed in the last lecture, which we had to go through a little bit today, but I'm not sure among other details how much you remember, right? So that part you will have to definitely go through once more. But the beauty of learning all these things is that, in my opinion, among all the transformer models we have discussed in this course, Swin transformer is by far the most difficult one so far. In next lecture, so next Saturday, we won't have a lecture. We'll meet next to next Saturday, and we'll be starting fresh because now we are moving to detection. So we'll be discussing about detection transformer next Saturday. Detection transformer implementation will be, I think, in my opinion, will be much easier now that you have gone through Swin transformer. So if you look at 3 models which we discussed. Actually, we have discussed 4 models: Vision Transformer, Nano VLM, Data Efficient Image Transformer, and Swin Transformer. In that, Nano VLM was out of the sequence. I wanted to teach it, although I planned to teach it at the end of the course because it was so related with the transformer ideas we discussed. But Vision Transformer, Data Efficient Image Transformer, and Swin are like one after the other. So Vision Transformer came first, and Data Efficient was a slight extension of Vision Transformer. Swin Transformer was a truly, hardcore extension. So these 3 things, in terms of difficulty, also ViT is easiest, DEIT is the second more difficult, Swin is the most difficult. So if you understand those 3, you will have a fairly good mastery over usage of transformers for image classification tasks. And if you understand even Vision Transformer properly, I think you will have a fairly easy time understanding detection transformer. So detection transformer paper is super famous. I do plan to conduct a little bit of paper dissection sometime soon. But see you all next week. Next Saturday, please note there is no lecture. No, in Swin Transformer, there is no concept of CLS, at least in the main paper. But in the appendix section, they mentioned they have tried with CLS token also. Did not make any difference. But there is no concept of CLS token. They directly use the context vector that they get at the end of the 4th stage. Very, very good question, that is. But in Vision Transformer and Data Efficient, there is CLS token. All right, everyone. For those of you who did not get the email, please just put your email in the Discord. I will add you to your... if you just accept the Google Calendar invite, I think you should get an email. But in any case, just put your email on Discord. I'll send you an email. So thank you so much, everyone. Bit of a long lecture, but please go through this once more. I know that this is not the easiest of lectures, not for me to teach, not for you to learn. So I really want you to spend some more time, because the architecture itself is a little bit complex. So we'll meet again after 2 weeks. Take care until then. I'll post a bit difficult 2 assignments in the meanwhile. And if my lecture on detection transformer paper dissection is over before the next lecture, I will share it with you. Otherwise, you can go through it after the lecture. So thank you so much and take care. Bye.